वो चलाओगे तो वो बोल रहे थे कि इंटरनेट की प्रॉब्लम आएगी। कर दिया है, लाइव स्ट्रीमिंग हो गया है। कौन सा?
जो स्पीकर है ना,
हाँ
वो को होस्ट बना दो।
स्पीकर तो अभी अभी तो मैं ही बोलूंगी ना।
हाँ हाँ, मैं बुला के छोड़ दूँ।
चलो आप उसको बोल रहे थे कि इंटरनेट की प्रॉब्लम आएगी।
Hello, Monica, am I audible?
Yes, ma'am, you're audible.
You're audible. Yeah, thank you, thank you. Monica, ma'am,
Yes.
shall I call VC sir to join?
I think I'm already there.
Still there are only 18 participants, madam. Let everyone join.
Okay.
Maybe after another 1 minute or 2 minutes, 1 or 2 minutes, we can wait for him. Sir is there. Sir has joined. Good morning, sir.
Good morning, sir.
Good morning. Good morning.
Shall I start?
Yes, you can. Please start. As it is 9:30. Sir, shall we start, sir?
Yeah, if you're ready, you can start.
Yes. Monica, ma'am, let's start.
Okay. A very warm and pleasant morning to everyone present here. With the divine blessings of His Holiness Jagadguru Shri Shivaratri Deshi Kendra Mahaswami Ji, I, Dr. Monica Malik, Assistant Professor in the Department of Electronics and Communication Engineering, take this opportunity to welcome you all to this one-day online summit on quantum technology in security, organized by the Department of Electronics and Communication, JSS University, Noida. As we begin this event, it's a tradition to seek the blessings of Lord Ganesha. May I now request everyone to join us as we play the divine Ganesh Shloka to invoke his blessings.
वक्रतुण्ड महाकाय सूर्यकोटि समप्रभ निर्विघ्नं कुरु मे देव सर्वकार्येषु सर्वदा.
Let's move further. It's my privilege to invite Dr. Gayatri Shakya, HOD ECE and convener of the summit, to deliver the welcome address. Stop sharing.
Yeah, good morning, everyone. With the divine blessings of His Holiness Jagadguru Shri Shivaratri Deshikendra Mahaswami Ji, it is our privilege to present the one-day online summit on quantum technology in security, organized by Department of Electronics and Communication Engineering, JSS University, Noida. On behalf of JSS University, Noida, I extend a warm and heartfelt welcome to our Honorable Vice Chancellor, Sir, respected Registrar Ma'am, Controller, Examination, Finance Officer, sir, all esteemed deans, especially our summit chair, Dr. R.S. Jagdish, Dean of Student Welfare, head of the departments, distinguished speakers, moderators, and panelists, researchers, industry professionals, faculty members, students, and all participants joining us today. This summit has been organized to create awareness, promote knowledge exchange, and encourage meaningful discussion on opportunities and security challenges associated with quantum technologies. It brings together experts from academia, industry, government organizations, research institutions, and startups to explore practical strategies for building a secure, resilient, and quantum safe digital ecosystem. It's my privilege to welcome our distinguished experts, Professor Amlan Chakravarti, Professor, University of Calcutta, then Professor Ajay Singh, former HCL executive and quantum technology expert associated with National Quantum Mission Panel, Mr. Sumant Parimal, founder and director, Innograce Ventures, Dr. Mahesha Pandit, Chief Technology Officer, Canaris IT Solutions, Dr. Anirban Bhattacharjee, Professor Sardar Vallabh, National Institute of Technology, Surat, Dr. Anindita Banerjee, Scientist and Project Manager for Quantum Technology Project, CDEC, Pune Division, Maharashtra, Dr. R.P. Singh, former Scientist, Physical Research Laboratory, Government of India, Ahmedabad, and visiting faculty at IIT Gandhinagar and expert in quantum communication. Mr. Mayank Verma, Chief Executive Officer and co-founder, Q Crypt Shield. Dr. Abhishek Tiwari, Scientist Staff, CDEC Noida. Dr. Kumar Gautam, Founder, eGreen Quanta. Professor Pillai Emmanuel Shubhankar, Professor, Malviya National Institute of Technology, Jaipur, and Mr. Nikhil Mitalia, General Manager, Tabor Electronics Limited. We are happy to honored by the presence of such accomplished experts whose collective knowledge and experience will greatly enrich the deliberations of this summit. The program include expert talks and panel discussions on quantum threat to classical crypto post-quantum security. Quantum also examine the impact of quantum technologies on critical sectors such as banking and financial services, defense, healthcare, education, and research. Through discussion on the themes such as we are ready for quantum security era and building a quantum safe ecosystem, policy, industry, and academia, we hope to assess our present level of preparedness, identify existing capability gaps, and understanding the collective responsibility of policymakers, industries, universities, researchers, and technology startups. I take this opportunity to express my sincere gratitude to our Honorable Vice Chancellor, Sir, for his visionary leadership, constant encouragement, and unwavering support for academic excellence, innovation, and This summit has been organized in emerging areas such as quantum technology, meaningful networking among academicians, researchers, industry expert professionals, and startups working in this field. It will also strengthen the university research ecosystem and pave the way for future collaborations, the development of research laboratories, and the establishment of Center of Excellence in Quantum Technology and Security. I also express my sincere appreciation to our summit chair, program coordinators, organizing committee members, faculty, colleagues, and technical team for their dedicated efforts in planning and organizing this summit well. I am confident that today's discussion will inspire new ideas, strengthen collaborations, and contribute towards building a secure, resilient, and quantum safe future of India. Once again, I warmly welcome you all and wish the summit a great success. And now I welcome our Honorable Vice Chancellor, Sir, to inaugurate formally the session. Thank you, sir.
Yeah, thank you, Dr. Gayatri. So thank you for the overview of the summit. Seeking the blessings of His Holiness Swamiji for the success of this one-day summit, and who is also the Chancellor of the University. Respected distinguished speakers, industry leaders, researchers, faculty members, students, and participants from India and abroad, and also from our institution. A very warm good morning to all of you. It gives me immense pleasure to welcome you to this one-day summit on the quantum technology in the in security, organized by the Department of Electronics and Communication, JSS University, Noida. At the outset, I congratulate the Department of ECE, the organizing team, our distinguished speakers, panelists, and industry experts for bringing together such an important and timely topic in the forum. Your presence today reflects the growing significance of quantum technology in shaping the future of the digital world. Today, we stand at a remarkable point in human history. Maybe if you look at the even major technological revolution has transformed society, because just look at the large like a society, from the steam engine to the electricity, from the computer to the artificial intelligence, we are now entering the another transformation era, the era of quantum technology. Quantum computing promises unprecedented computational power. So problems that may take today's most powerful supercomputers thousands of years to solve could potentially be solved even in hours or minutes, future quantum computers. While this creates extraordinary opportunities in healthcare, in the material science, finance, climate modeling, and the scientific discovery, it also presents significant challenges, particularly in the field of cybersecurity. I mean, just to give an example, practical example. Recently, when I visited the USA, I was just near Seattle. We had just visited the Mount Rainier Mountain. Because basically there are 5 glaciers, which is very old, maybe thousands of years old. Maybe if that glaciers melt, the whole area or whole country will be demolished. Imagine this. So now, why I'm just telling that is how you do the climate modeling. That's exactly what I was telling. Climate modeling is maybe using a current computers or a previous computers. It will not able to model the thing. So if you don't model, then what will happen? Maybe because of the glacier, it becomes volcano. Volcano becomes exploding the complete ice. The entire thing will be submerged. Already one glacier is exploded, volcano happened, exploded, and the entire area has got an earthquake, and then the entire mountain was fallen. So now the point what I'm telling you is the climate modeling. We require the mathematical modeling, requires the powerful computers. So this way, these quantum computers going to help us, so especially cybersecurity. So many of the encryption systems that protect our the banking transactions, healthcare records, government communication, defense networks, and digital identities rely on the mathematical problems that are difficult for a classical computer to solve. Maybe if you look at, even though there is so much of security, the people will break that security, either in the banking or healthcare, anywhere. So now the mathematical models, whatever the mathematical algorithms are modeled, by a classical computer is very difficult. So however, the emergence of a powerful quantum computers could fundamentally alter the security landscape. So that's where this RBI or the Department of the Ministry of Finance in the Government of India focusing on the quantum security. Therefore, the question before us is not whether quantum technology will impact security. It's not what will impact, basically, but how prepared we are for the quantum future. Maybe if recently, I don't know whether how many of you seen the thing, DRDO has released the first version of the quantum security. Recently, just the few weeks back or few days back. So therefore, the theme of the summit is both relevant and forward-looking. It seeks to explore how quantum technologies can be harnessed not only by addressing the emerging threats, but also to build stronger, more resilient and quantum-safe security infrastructure. So I am particularly pleased that today's discussions span multiple sectors: BFSI, healthcare, defense, education, research. So cybersecurity is no longer the responsibility of a single domain. It is a shared responsibility that requires collaboration among academia, industry, government agencies, and technological innovators. So India is recognized strategic importance of quantum technologies. So though initiatives such as the National Quantum Mission and increasing investment in the advanced research, our country is positioning itself to become a significant contributor to the global quantum ecosystem. Then the universities have a crucial role to play in this journey by creating a knowledge, nurturing talent, and fostering innovation and build industry partnership. So just to know, take it like, for example, Gujarat, the Karnataka government, Andhra Pradesh government in the current India, they investing a lot in the quantum quantum technologies. At JSS University, Noida, we are committed to developing the future-ready graduates and researchers who can contribute meaningfully in the emerging areas such as AI, quantum computing, cybersecurity, semiconductor technologies, and the digital transformation. We firmly believe that interdisciplinary collaboration and innovation-driven education are essential for addressing the challenges of the 21st century. So in this direction, the summer break, we arranged about 20 plus online summit the summit with various technologies, this is one among them. I'm confident that today's summit will provide valuable insights into quantum threats to existing cryptographic system, post-quantum security frameworks, quantum communication and encryption technologies, industry use cases and innovations, policy perspective and India's roadmap toward a secure quantum future, because we have a various speakers lined up from the policymakers, researchers, professors, and industry leaders. So various people that I hope definitely they bring the different perspective for this particular summit. More importantly, hope this summit will spark new collaborations, research partnership, startup ideas, and innovative solutions that can contribute to a secure and sustainable digital society. So to our students and young researchers who are participating today, I would like to say that quantum technology is not merely a future possibility. It is a future career opportunity. So a lot of opportunities are available. The next decade will witness tremendous demand for talent capable of bridging physics, computing, mathematics, electronics, communication system, and cybersecurity. So I encourage you to engage actively, ask questions, explore the immense possibilities this field can offer. Before I conclude, I once again express my sincere appreciation to all the eminent speakers, various professors from various institutes and panelists for sharing their expertise and experiences in this one-day summit. Your contribution definitely will undoubtedly enrich the learning experience of every participant. I wish this summit a great success. Hope that deliberation today will contribute meaningfully to building a secure, innovative, and quantum-ready India. So let us innovate, collaborate, and secure the quantum future together. Namaskar, thank you, namaskar, and Jai Hind.
Thank you, sir, for your inspiring and insightful inaugural address. Your visionary words have set the perfect tone for today's summit and motivation for all of us, sir. Thank you very much, sir. It's now my privilege to invite our esteemed summit chair, Dr. R.S. Jagdish, sir, to address the gathering and share his valuable insights. Sir.
So, thank you, madam. Good morning to each and everyone. With the divine blessings of His Holiness Mahaswamiji, it gives me immense pleasure to welcome you all to this one-day online summit on quantum technology in security. Respected Honorable Vice Chancellor, Dr. H.R. Mahadev Swami, sir. Dean Academic, Dr. B. Manoj Kumar, Registrar, Finance Officer, Controller of Examination, eminent academicians, researchers, industry experts, faculty members, dear students, and participants from across India and abroad. My warm greetings to all of you. Quantum technology is poised to redefine the future of secure communication, cryptography, computing, and national security. As quantum computers continue to evolve, they bring both unprecedented opportunities and significant cybersecurity challenges. This summit provides a timely platform to explore innovations in quantum cryptography, post-quantum security, quantum communication, and the role of quantum technologies in building a secure digital ecosystem aligned with the vision of Atmanirbhar Bharat. I extend my sincere gratitude to our Honorable Vice Chancellor, the Dean Academics, Registrar, Deans, heads of the department, and entire management of JSS University for their constant encouragement and unwavering support in promoting academic excellence and cutting-edge research. I express my heartfelt appreciation to our distinguished keynote speakers and resource persons for generously sharing their expertise and insights. Your contributions will undoubtedly inspire meaningful discussion and motivate our participants to pursue innovation in this emerging field. I also congratulate the summit coordinators, conveners, and the entire organizing committee for their meticulous planning and dedicated efforts in organizing this event. My sincere appreciation goes to the faculty members, technical support team, student volunteers, and every individual working behind the scenes to ensure the smooth conduct of today's summit. Finally, I thank all the participants for joining us with a lot of enthusiasm and a spirit of learning. I encourage each one of you actively engage in the technical session, interact with the experts, and make the most of this unique opportunity. I wish this summit a grand success and hope it ignites new ideas, collaborations, and innovations that will contribute to a secure and technologically advanced future. Thank you, and I wish you all a productive and enriching summit.
Thank you so much, sir, for your motivating address, sir. Thank you, sir. Now let's move to the next section. For this, now I call Dr. Pooja Pandey, Assistant Professor, JSS University, Noida, to begin with the introduction of the next expert. Yes, Pooja, ma'am.
Thank you, ma'am. It is my pleasure to introduce our distinguished guest speaker, Professor Amlan Chakravarti, Professor and Director in A.K. Chaudhary School of IT, University of Calcutta, and Visiting Professor in the Department of AI at IIT Kharagpur. Professor Amlan Chakravarti is a distinguished academician and researcher with over 20 years of experience in engineering education and research. He serves as the Chief Coordinator of the International Center of Excellence for Data Science, Artificial Intelligence, and Futuristic Technologies, an initiative of the Department of Higher Education, Government of West Bengal. A renowned expert in quantum computing, he completed his PhD at the University of Calcutta and postdoctoral research at Princeton University. He has published over 200 research papers, received several prestigious awards and fellowships, and has made significant contributions to quantum computing, artificial intelligence, machine learning, computer vision, and cyber physical system. Please join me in extending a warm welcome to Professor Amlan Chakravarti. We are honored to have him with us today and look forward to an insightful and inspiring session. Over to you, sir.
Sir. Are you there? Monica ma'am, has he joined?
Amlan sir.
Just I will call him.
Check करना चाहिए.
The person you are calling is currently busy. Please call again later.
Monica ma'am, his session was from 10 a.m. So I think we should wait for 5 minutes. Okay. It is 9:53 now.
Okay, ma'am. Okay, ma'am.
So we need to wait. Actually, we have given him the time of 10 a.m.
Okay, ma'am.
Okay, so we shall wait for 5 minutes.
Okay, very good morning to all of you. I have joined.
Good morning, sir.
Good morning, good morning.
Monica ma'am, can we have one more time the introduction of Professor Amlan Chakravarti?
Good morning, sir.
Yeah, good morning, very good morning.
It is my pleasure to introduce our distinguished guest speaker, Professor Amlan Chakrabarti, Professor and Director in A.K. Chaudhary School of IT, University of Calcutta, and visiting professor in the Department of AI at IIT Kharagpur. Professor Amlan Chakrabarti is a distinguished academician and researcher with over 20 years of experience in engineering education and research. He serves as the Chief Coordinator of the International Center of Excellence for Data Science, Artificial Intelligence, and Futuristic Technologies, an initiative of the Department of Higher Education, Government of West Bengal. A renowned expert in quantum computing, he completed his PhD at the University of Calcutta and postdoctoral research at Princeton University. He has published over 200 research papers, received several prestigious awards and fellowships, and has made significant contributions to quantum computing, artificial intelligence, machine learning, computer vision, and cyber physical systems. Please join me in extending a warm welcome to Professor Amlan Chakrabarti. We are honored to have him with us today and look forward to an insightful and inspiring session. Over to you, sir.
Yeah, thank you, Dr. Pooja. And thanks to JSS University for inviting me. I saw the program schedule, though I'm pretty busy because the course started in IIT Kharagpur. Okay, so today I have 2 lectures from 3 to 5. That means after this I have to meet my TAs also. A lot of things are there in IIT Kharagpur what I'm doing, but thanks that means I've got some time, and I saw and I look into this schedule of this particular workshop, which is very fantastic, and this type of events are really very good for the researchers, for the students, for the faculty members, because we have to do an accelerated work, right, in a very accelerated pace in quantum computing, both in terms of teaching, research, and industry development. I think I have my good friend, okay, Sumant Parimal here, right, who has already pinged me that you have to start your lecture. Okay, thanks, Sumant, for reminding me, right? And the initiatives like Sumant in Gujarat, what he's doing is fantastic. And I hope that the JSS University and the entire consortium here, okay, will look forward and will make a very positive role in the quantum developments in India, quantum development, quantum computing, quantum communication, and quantum sensing developments in India. So now straight to my lecture, right? I will try to, finish this maybe within 45 minutes, maybe 5 to 10 minutes question answer session. Okay, I will try to wrap within 11 this particular talk. So, okay, so this particular talk, what I will be presenting, let me start my presentation and start delivering. So what I will be presenting today, this will be a very interesting area, which actually looks into the domain of quantum communication and how we can develop the quantum communication protocols, okay, right, very efficiently. And the good point is that means some of these protocols are already being developed in my lab at University of Calcutta, and so that is one of the things that, so if researchers and faculty members wants to connect me on this work, we will be very happy to do that. Okay, so let me start. So the title of the talk is QKD. QKD means quantum key distribution, and we are trying to the basic philosophy of QKD, the fundamentals of QKD, was our communication between Alice and Bob, which is a two-party communication. But obviously, the recent developments of QKD enables us to develop a communication which is multi-party. And what we will learn, let me go through that. So we will try to understand the basics of quantum computing and communication. Okay, very few. Due to the paucity of time, I will not able to give a very detailed discussion on that, but I will try to make a very baseline understanding, and then we will go straight into the QKD, the different forms of QKD, what are there, right? And we can try to implement that. So the motivation of my present research in quantum communication is that, okay, can we try to integrate the quantum protocols, the quantum communication protocols in the present internet, right? We can call it as a classical quantum hybrid internet, because I still believe that all the functions that are still not possible in the fully quantum domain. Still some classical functions will be there. So the motivation is that using these QKD protocols, can we develop a quantum classical hybrid hybrid network, right, which will be much stronger than what we have, much safer than what we have in the present classical computing networks. Okay, so we will discuss about those. But still, as we know that any network you come up with, right, there will be attack scenarios, and you cannot tell that, okay, I have developed a network, but I didn't consider about the attack scenarios. So I will also try to give you some understanding that what are the attack scenarios can happen in this quantum communication networks too, and how we can develop the resilience, okay, for those. And obviously this is the actual research what we are doing. We are trying to develop the application stack. We are trying to develop the mail engines. We are trying to develop the file server, file communication engines, which will be based on this QKD. And we also have a PQC research, which I didn't show here due to the paucity of time. Recently, we have also done a technology transfer, okay, with a company where we have developed this PQC-based digital certificate creation. Okay, so PQC and QKD, PQC at the static side, right, and QKD at the transit side is the perfect way how to generate the next generation of the computing networks. Okay, and I will also try to highlight what are the things going in India. Okay, so let's try to start. So so I hope my slide is visible to all of you, right? I didn't that we know whether the slide is visible. Is it visible to all
Yes,
of you?
sir. Yes, sir, it is
Okay, great.
visible, sir.
Okay, great. Okay, so quantum threat to classical cryptography in the sense is that we know that the quantum has a power, right? Quantum engines or quantum computing engines have a great power of searching the space, right? It can search an exponential space in linear time, okay, which is the crux that why we are going for quantum computing, right? And we know that the breaking a key is nothing but a search. Okay, you have to do a search in the key space, and you have to try to find out that what are the keys in the domain which matches the criteria. Okay, so there are possibility that we will have this type of attack which are called harvest now and decrypt later. Okay, so which means that you try to hack the key and use the key when it is required. Okay, and obviously trust. So what we try to do now, we have to make a sort of a scenario so that the trust on this particular very important systems can prevail. Okay, so what we try to do, what happened? Okay, so what we try to foresee is that we will have a Q day, which is called a quantum day, right? And if you look into the way the quantum systems are getting built up, okay, in the various research labs and various organizations, we are not very far that we will have a full-fledged quantum computer giving us around 5,000 qubits or 10,000 qubits or maybe 1 million qubits, right? Maybe within the 3 to 5 years time, right? And those are the times where our classical crypto system will be extremely vulnerable, okay? Because it has been proved by several researchers that that all your ECC and RSA algorithms, encryption algorithms, which are the pillars or the backbone of the classical cryptography today, okay, will be completely taken over, will be completely cracked, okay, by these quantum engines, and whoever has the quantum engines, okay, they can do a devastation, right? I think maybe some of you were there in the meeting, a meeting organized by Department of Science and Technology. I think in February this year, if I am correct. Okay, Suman can correct me. Okay, so February this year there was a meeting at IIT Mumbai. Okay, where there was a declaration of this National Quantum Mission projects, and there the people from the government, okay, from the DST, okay, DST National Quantum Mission project, who were leading this mission from India. They give a very deep, okay, but they all focused upon the need of this quantum communication and quantum security. Okay, so I think that's very important because we have to make our systems secure from quantum attack. Okay, so now we require a need for a quantum safe communication. Okay, so as we say that okay, normally when we say quantum safe security, we normally tell PQC, which is post-quantum cryptography. That is obviously a particular part of the security. But what I will try to share with you today is the quantum safe communication, which means the data on transit. Okay, so there are two types of security. One is the security for data at rest, and one is the security when the data is on the channel or the data is on transit, right? So that's what QKD gives, and QKD started with a fundamental of BB84 algorithm, and then we progressed a lot on that direction. Okay, the crux of this quantum key distribution is that you have to understand what is a quantum state, right? And we have to know that how the quantum state can be can be communicated from one end to another end, okay, from one sender to one receiver, right? And what happens to the quantum state when somebody like Ives, okay, tries to get into that particular communication, okay, right, and try to get something out of it. Okay, so this is a summary that what are the strength of quantum communication. Okay, so you see the ECC256 and okay, all these are maybe cracked by it's already, these are all latest data, right? From Caltech, from Google, right? Who have experimented and who have proved, okay, that all these algorithms will take a few minutes to few days, okay, to get cracked. So okay, so your bank server gets cracked within a few days. Okay, imagine what happens. The financial loss, the individual or the government or the state as a whole suffers. Okay, so we have to find the alternative paths that how to make our security, how to make our systems, our data safe from quantum attack, right? And QKD is one of them. I'm not telling you that it is only QKD, but QKD is one of the things which can give you assurance of the security, okay, when the data is on the transit. So if we look into the QKD, the very top level view of QKD, okay, again I say quantum key distribution. Why a key distribution is required, right? I cannot interact with you in that way, like a physical classroom mode, so I cannot ask you the question and get back, but I just try to make it clear that the key is a very important, the key exchange is a key distribution is a very important criteria, right? Of making a safe communication. If I am communicating with my friend B, I am A, and I'm communicating with my friend B, okay, then what I encrypt, okay, B has to decrypt, right? Right, and to do that, there are two ways, okay? One is called an asymmetric cryptography, where I encrypt with the public key of my friend B, and B decrypts with the private key of its own, right? And the trick is that, okay, though I encrypt with the public key of B, okay, it can only be decrypted when the private key of B will be there, and private key of B is only private to B, okay? Right, and similarly, we can go communication with B, C, D, E, and F, and similarly, they can also communicate with me. Okay, but this asymmetric cryptography is a challenge because this is a very complex algorithm, right? And also we have to maintain two keys, okay, which are not possible for a low latency communication, means where you have to do the things very fast, right? And you have not even that means you don't have much resources to compute, okay. So the thumb rule solution, easy solution is a symmetric cryptography. In a symmetric cryptography, if I'm communicating with my friend B, okay, right, I use an encryption key, right, and B uses the same key to decrypt my message. But the problem in that case is that, right, that me and my friend has to have the same key, right, and how to communicate this key, because my friend can be anywhere. Okay, so it is not possible for me. So I have to use a channel. Okay, I have to use a channel, again, a communication channel to exchange the key, right? And then my system becomes vulnerable because once I use a channel to send my key, there can be eavesdropper who will be catching hold of the key, right? And if the eavesdropper gets catch hold of the key, then the eavesdropper can decrypt all the data what I'm sending to B, right? And similarly to C, to D, something like that, right? So that is the problem of the symmetric cryptography or the key exchange protocol. So now there are some protocols like Diffie-Hellman and all these things, but it has been proved that means in the quantums in the quantum setup, all these algorithms can be cracked. Okay. So now what we do, we take the same key exchange protocol in the quantum platform, right? And that particular key exchange protocol in the quantum platform is called as key distribution. Okay, now key distribution can be various forms. Okay, first is the very simplest form, what I show here. Okay, what I show here is the two-party QKD. Okay, so there is only a key is exchanged between Alice and Bob continues communication with that particular key. Okay, it is a very secured link and right, and due to the inherent property of QKD, okay, right, it's okay, it's not possible for an Eve to understand what key is exchanged between Alice and Bob. And also there is also another very good issue in quantum communication, or QKD, is that, okay, right, if an Eve try to attack this particular channel, right, and try to measure what Alice is sending to Bob, in doing this measurement, if okay, right, if doing this measurement itself introducing a very high amount of noise in the channel, okay, and now both Alice and Bob is sensing the channel, and suddenly they find that there is a high error in the channel, and they will immediately understand that there is an attack from the Eve in the channel, and they can stop the communication. So this is very, very good in the case of this quantum key exchange. In classical, what happens, you will not get any sort of information about the attack, right? You get to know the attack by seeing some results which has occurred out of the attack. So you know that, okay, that when somebody has operated on your data, and then you know that, okay, that means my data has been attacked. Okay, my communication has been attacked. So you only get to know about the attack scenario once you see the effect, what the attack has generated. Whereas here what happens, once the attack is generated, okay, right, the basic data gets corrupted, and that corruption immediately gives a signal, okay, that attack is happening in the channel, right? And then either they can change the channel, right, or they can stop communication immediately. Okay, so this is the good point of this quantum communication, or QKD. Now QKD from the two-party QKD, okay, we actually extend it to a multi-party QKD. Okay. Now, for a multi-party QKD, the cost is enormous because it's like a mesh. Okay, because so if there are 4 members, Alice, Dave, Charlie, Bob, has to maintain a QKD with each other. Okay, then each of them has to have 3 QKD links. Okay, right, and this is costly. Okay, so it grows. Okay, the number of links goes n square order, right, and that is costly. So that is what actually makes this multi-party in this particular all-to-all QKD a very costly affair. Okay, right, and it's not only the links, you also have to set up your sources and receivers. Okay, basically this is done in the optical domain, so you have to have optical sources and receivers for each of the channels. Okay, so that is a costly affair. Okay, hardware, bandwidth, okay, network, all becomes a costly affair, right? Now, when we go in the enhancing the number of parties in the QKD, the next trend or the next upgradation is that we should go for an entanglement-based QKD. Okay, right? Entanglement-based QKD is works on a central entangler. Okay, central entangler, which can generate the entanglement among the various parties which are getting engaged in this communication through an entanglement procedure, right? And that entanglement procedure means that you make a central entangler which is costly, but you need not to maintain a very costly things going in each of the nodes, right? And that is called a multi-party QKD based on entanglement, and this is also now getting very popular. Although getting multi-party entanglement in the reality is a costly affair, but that is the direction where science and technology is heading forwards, right? To make this QKD a very, very good adaptable communication protocol for a multi-party communication. And right, multi-party communication is what is most commonly used in a network. Okay, so now we will go a little bit of insight that in to understand the QKD and all these things, you have to have a little bit understanding of what a quantum computer is, and I feel that I feel that all of you have some understanding on that because you are participating in this particular workshop. And now the quantum computing is not so unknown to the research of the students, okay, like it was maybe at least 4 or 5 years ago, okay? So we know that why quantum computing is different from the computing what we have done earlier. So the computing we done earlier goes back to history of computing, where we can see this extreme left image, which is called a electromechanical computer, okay, which were actually computers which were guided by the by electromechanical controls, right? And these were used for for some sort of automated counting of numbers, okay? Basically used for arithmetic and logical computations, okay? But the real computation started with the advent of the transistor and the silicon-based VLSI circuits, which has immensely increased the speed of computation, the amount of computation, the resources of computation immensely, right? And that has made our digital digital transformation to a great level, right? We can now do everything in a smart mobile, right? Which many of us, when we are in the college days, maybe 25 years ago, right, used to do in our big computer, right? In our Intel and in the maybe Pentium computers. The Pentium computer, the power of your smartphone is at least 5x on the Pentium computers what we used to have in our college days. Okay, so that's obviously a fantastic change, multi-core, many-core GPU, right? All this computing with low power within a very small area of your die size. Okay, it is generating a good amount of computing resource. VLSI design and VLSI technology and the silicon processing has contributed immensely. But what next? Okay, what next is the extreme right? What I show and what is actually the very top view of a quantum computer, right? A quantum computer is nothing but it actually works on the subatomic states of matter, right? And this subatomic states of matter, okay, maybe the energy of your electron, maybe the spin of your nucleus, okay, maybe the presence or absence of an electron in a particular shell, okay. It can be the polarization of your photon, okay, right? It can be a direction of your current in a superconducting qubit. So a lot of this type of states of matter, subatomic states of matter, which are quantized. Quantized means which have discrete levels. Okay, quantization means the discrete level. So when we go into the large scale of matter, right, we see continuous things. But when we go to the matter at that level, the subatomic level, we see that the electron can electron energy can only exist in some discrete values. Spin of a nucleus can only exist of a discrete values. Polarization of a photon can only exist upon discrete values. So this discretization of the states in that level helps us to identify them as some of the states of your computing, right? And what we need to next, what we need to make a computer work, right? A computer works by two things. One is that you need to have a particular rule by which you identify state with the data, okay? Okay, particular data, a particular state of the system will represent a particular data, right? And then it will also have a procedure to update the state, which means that, okay, the system can actually, move from one state to another state, which means that it is updating the data. Okay, so if you look into the fundamental concept of Turing machine, it also says the same thing. Okay, right? It has a tape and it has a transition function. Okay, so the transition function actually accepts something from the tape, right, and then transforms it, right, and writes back to the tape. So it means that each tape state, right, is a state of your machine, right? And you have a transition function which can update the state of the tape. Okay, so similarly, it is computing. So what we do in a quantum computer is that whatever subatomic states I say, right? Okay, right. Each of these possible states are mapped to a particular value. The common value is 0 and 1. Okay, as we are very habituated with classical logic design, right? Classical logic design, okay, tells us, the digital logic design tells us that we have the states of zeros and one, like transistor states of zeros and one. But what is advantageous in a quantum is that, hey, you can obviously tell, hey, the ground state, the most lowest energy state as 0, right? And some of the highest energy state as 1. But it can also exist in some discrete states which are in between this 0 and 1, right? And these states are called superposed states. And you can, mathematically, you can define that any particular state can represent as a vector, right? And the vector has a probability of getting measured as 0 or getting measured as 1, right? And accordingly, the intermediate states are being defined as superposed states between zeros and 1. So this is the state perspective of a quantum system, which is being abstracted as a quantum function, okay, as a quantum state vector, right? Let me see what we have in the follows. Okay, so we don't have much, but I will tell what is that. Okay, so this is what is a quantum computer. This is what is a quantum computer. What we have physically now, I think there are some of the facilities in India itself, right, where quantum computer has been installed. Okay, right, and we are now, I think very familiar with this type of things. Okay, the architecture. This architecture has 3 important things you have to understand. Okay, obviously there are so many things in the architecture, but you have to understand 3 fundamental things in this particular box, which are very, very fundamental. Okay, first one is the quantum chip, which sits at the base of this system, which is a qubit chip, right? The qubit chip presently this particular figure comes from the IBM quantum computer. Okay, so IBM quantum computer uses superconducting qubits. Okay, many of the quantum computer uses superconducting qubits, but having said so, it's not only the quantum technology. Okay, we can have superconducting, we can have a hand trap, we can have neutral atoms, right? And there are a few more. So now let us try to figure out this particular system, which is a quantum system, which is a quantum computer system, right? And it has 3 very fundamental things. Okay, one is the qubit, okay, which actually sits at the base of the system, right, where all the wires gets connected, right? And these are the wires, right? These are the bunch of wires, okay, right? And this bunch of wires actually goes presently it goes out of this system and are connected with a computing device. That computing device, be an FPGA or a computer, whatever it is, they send the control signals, and these control signals comes through the control wires and actually updates the state of the qubits which are there in the qubit chip. That is what is computing. So quantum computing, in one sense, is an in-memory computing. I think some of you might be knowing what is in-memory computing. In-memory computing means that there is no particular other stage of the computer except the memory. Okay, so what happens in computing here is that it will, computing starts with an initialization of the memory state, right? And then update of the memory state with some functions will actually lead to the result state of the system. Okay, so there is no, like classical computing, we don't have the flow of the data in different blocks. Like we have a pipeline, we have a classical computing, a classical processor, we have a pipeline where it goes to the different stages at different clocks, right? Right here, the different clocks will actually do an update of the same quantum state. So the qubit states gets updated by the quantum operations, which are defined by these control signals with different intervals of time. And these intervals of time and the quantum functions are defined by the quantum circuit, what we prepare, okay, in order to implement a quantum algorithm. So quantum algorithm is there. Okay, quantum algorithm is being now abstracted as a quantum circuit, which are which are the discrete quantum operations which are done on the qubits, right? And then we generate the control signals which will enable those operations to be done on the qubits in the physically, right? And that's all I can say at this point of now. There are a lot of things are there, but again, it is not a quantum control or a quantum signal discussion. I will go ahead from here. Okay, and then the two things I described, right? And the third part is the entire casing. This entire casing, right, is called a dilution refrigeration casing, right? And this is an entirely vacuum in a low temperature. Why this is done? Because we want to make this qubits, not disturbed by any external signal energy. So we reduce all the energy in this particular system by making it a very, very low temperature, and we try to isolate the system from any signals by making it perfectly vacuum. Okay, so these are the things, and right, and using this we actually work with the quantum states, and as I said, this gives a quantum speed up, right, and also quantum communication is one of the part. Though this quantum computer might not be working for quantum communication. Quantum communication will have a different type of setup, right? Mostly optical setup, but this is just for your, just for the completeness we discussed this, okay? So now let us try to discuss one more important thing, for quantum communication, which is called quantum entanglement, okay? Right, and this quantum entanglement is a phenomenon. Okay, so quantum has three phenomena which are not there in classical, okay, and that's why quantum computing is so special. Okay, right, one is superposition, what I just explained a bit. Okay, and the second one is quantum entanglement, which I've explained now, right, and other one is the quantum interference, okay, which actually tries to increase some of the state amplitudes and decrease some of the states amplitudes in a particular quantum mechanical fashion. Okay, but let us focus on quantum entanglement. So what quantum entanglement does? Quantum entanglement generates a particular state. So normally when we say a n-qubit system, right, a general superposition will generate, okay, that means an unbiased superposition will generate equal probability of 2 to the power n basis states, because that's the power of quantum computer, right? An n-qubit system will generate a distribution of 2 to the power n basis states, right? And this in a generic setting, in an unbiased setting, all of the states will have the equal amplitudes, right? When we apply some quantum operations, we actually make the amplitudes of some of the states higher, right, and some of the states very lower, but that is called quantum interference. Okay, by constructive interference of some states or one state, like Grover-Schwarz algorithm, right, to constructively interfere. That constructive interference is done on one state, which is the Mach state, and destructive interference is done for all other states. So that after some steps of this, when you measure the distribution, okay, the probability of the Mach state, which has increased very, very higher than all of the states, gets very high, right? And that is the state where measurement collapses, okay? But entanglement, this particular entanglement is a very disruptive distribution where you only generate two states. All other states, okay, vanishes out into the power distribution. So you see that this particular graph, which shows that this is a 2-qubit system. So 2-qubit system means n equals to 2. So 2 to the power n means 4. Okay, so there will be 4 states in this particular distribution. But you see that due to the entanglement, only the 2 states, 0, 0 and 1, 1 states are having a high amplitude, and all other states are having 0 amplitude. And this particular disruptive distribution can only be produced by the entanglement. The entanglement has other observations also. So this particular distribution in terms of qubit state can be represented as 0, 0 and 1, 1. Okay, that means 1 by root 2, 0, 0 and 1, 1. Okay. Okay, the typical nature of this is that you see that when I tell, okay, there is 1 0A and 0B, there's 1 1A and 1B. Now what happens if I measure this state? Okay, the measurement procedure itself tells that if there are n number of states, right, the system will collapse in any one state. And here, right, and the collapse and the probability of collapse will be higher for the state which has the highest amplitude. Okay, because probability is proportional to the square of the amplitude. So the state which is the highest amplitude, the probability of the collapse of the entire system to that state is highest. Now here there are two things, right? Right. If you see the probability of both the 0, 0 and 1, 1 is same, because both of them is half, because both of them has an amplitude of 1 by root 2, so 1 by root 2 squared is half. Okay, now the thing is that it can fall down to any of the states. Either we can get both the qubits as 0, and either we can get both the qubits as 1. But having said so, there is another catch. Is that means if I just measure any one qubit after measurement, if I find that one qubit is 0, I am pretty sure that the another qubit is also. If I measure A, right, and I find A is 0, I'm pretty sure that B is also 0. Similarly, if I find that my A is 1, I'm pretty sure that B is also 1. So I need not to measure B. I can only measure A, and I know what is the state of B. Now you try to expand it over multiple. It is not only A and B. You make A, B, C, D, E, F. What happens? So you have 0, 0, 0, 0, 0, 4, 0, 0, 0, 0, and 4, 1, 1, 1 as superposition. Because in a 4 qubit you can have 16 basis states. But out of these 16 basis states, due to entanglement, only 4 0 and 4 1 state exists. And now you find the trick. If you only measure one qubit, and if you get 0, you know all A, B, C, D, that is B, C, D, and E are 0. Similarly, if you measure A and you get 1, you know that B, C, D, E are all 1. And that is the so important thing, what happens in quantum entanglement, right? And that is there, right? Though apart from this entanglement is a special entanglement called the GHZ state, okay? So Zellinger state, okay? Greger-Hines Zellinger state, okay? So these states, but apart from this entanglement, apart from this GHZ entanglement, we can have other entanglements also. 0, 1, 1, 0, 0, 1, 1, 0 minus, right, and 0, 0 minus 1, 1. Okay, so all these are also entangled state. Okay, but this GHZ state is a very, very commonly used entangled state. Okay, right, and how we can do this entangled state is something like this. Okay, you actually make an Hadamard equal superposition and then apply a control C0, okay, with the top qubit as a control and bottom qubit as 1, and you generate this particular 0, 0, 1, 1 state. Now this 0, 0, 1, 1 state can be, okay, yeah, I just want to know from the organizers how much time I have in my hand so that I can pace my presentation accordingly. How much time? 5 minutes, 10 minutes?
Sir, it is around.
Yeah, so how much time I have? Hello?
Yes, sir.
Yeah, how much time more I can have from here?
So still you can have till 10:45, sir.
Oh, 10:45. So
Yeah.
maybe 5 minutes more. Okay.
Yes, sir.
Okay. So I have to be fast. Okay. Fine. So as I said that multi-party entanglement using n qubit GHZ state is something like this, right? Where we have a source which is generating this entanglement, generating this state, and is distributing the 3 qubits to each of the parties. Okay, Alice, Bob, and Charlie, right? And if Alice measures his qubit and finds it 0, automatically Bob and Charlie knows that their qubit is also 0. Okay, that is demonstrated in this particular thing, and that is so important, right? And we can ideally do it over n parties. How difficult it is, okay, that is only depends on how we can produce it, but this is but theoretically we can do it over the n parties. Okay, now using this we can actually develop, okay, these are the very primary things how we can develop the multi-party entanglement and multi-party communication. So multi-party entanglement, what I showed, okay, with this you can actually make a random key. Okay, I'm just making the cut short. So try to say that, okay, this 0011 is being generated by this GHZ generator over the time, right? And measurement is done randomly, right? And so measurement run randomly means if we just focus one of this particular party, Alice, she will get 0, 1, 0, 1, 0, 1 in some way, because this state will be measured, because this state out of 3 zeros or 3 1 in one measurement, she will get any one of, okay, 1 0 or 1 1. Okay, now at the same random measurement, the random measurement here will also reflect here and here. So all of them will get the same strings of 0 comprising of 0 and 1, and they will decide that this is their key, and the key is done. Okay, that is the fundamental way how the entanglement based key exchange is done. Okay, I will get a little bit more here. So these are the fundamentally 3 things that they are: discrete, continuous, and entanglement based. I will try to focus more on discrete and entanglement based. Continuous is a way by which we do the continuous state update and entanglement, but I will not discuss it much here due to the paucity of time. Okay, these are the 2 very important things, and one is called device independent is also there. Okay, which I will also try to focus a bit. Okay, so this is the fundamental QKD, which is called a discrete value based QKD, where what happens is that Alice actually tries to send this is an optical channel. Okay, it will send the photons which are polarized in a random way. Okay, now as we know that there are 2 states of polarization. One is horizontal vertical, this where the horizontal is 0 and vertical is 1. And another state of polarization is the diagonal polarization, where this diagonal is 0 and this diagonal is 1. Okay, now what happens is that Alice generates this polarization in a random way, either in a horizontal vertical form or in a diagonal form, right? And send the polarized pulses to Bob. Now Bob doesn't know that what is the actual. So these are the 2 basis of
रजिस्टर ऑफिस से
either horizontal, vertical, or diagonal. So Bob doesn't know that. Okay, now Bob tries to align his polarizer with the photon pulses, what Alice says. Now for some of the pulses, Bob gets a good value, and for the other pulses, Bob doesn't get a good value. Okay, so for the pulses with the Bob gets the good value, it means that the polarizer and Alice polarizers was aligned. And for those which Bob doesn't get a good value, okay, it is that the polarizer is opposite to the Alice polarizer. Now what happens after Bob records that what are the which pulses the Bob has received a good value, then over a public channel, Bob communicates this to Alice that maybe that okay, that means your first pulse, your 5th pulse, your 7th pulse, your 9th pulse, your 13th pulse, your 16th pulse, I have received okay. Okay, now if you tell that if somebody has this data also, suppose you tell, okay, sir, they are doing in a public channel, somebody has this data, but if somebody has this data, okay, right, he or she will not able to connect the what is there, because he doesn't know what value Bob has received, and he or she doesn't know what polarizer Bob has received. So there are 2 unknowns, right, which is very impossible to solve, right, for a string of data. But what happened, Alice knows now that Bob has perfectly decoded these polarization values. So now Alice says Bob, okay, you hold it, okay, this is what is the key I have sent you. So now you only use this sequence of polarizers in your communication, right? And I will adjust my sequence accordingly. And then what happens, whatever sequence Bob has actually generated properly will be used as decoding for the Bob, and Alice will send those sequences of the pulses, and those pulse stream will define the key between the Alice and Bob. So Alice and Bob can exchange the key that we know both of them that what Alice has sent to Bob, but with an Eve will not able to know what is there. And the second point, as I said, that if Eve wants to puncture this, right, Bob will suddenly feel that all of the pulses are now error. So now Bob will know that as all of the pulses are getting very high error, there is some attack in the channel and they will get out of this particular communication channel. So this is what is the summary of what is the DVQKD. And then I say what is the entanglement QKD, as I said. Okay, and that means I have shown with the three multi-party QKD entanglement where I said that, okay, the same, that means if we have a two parties, so 0, 0 and 1, 1. So I send either, that means I send one qubit to Alice and one qubit to Bob. But if Alice measures 0, Bob will also get 0. If Alice measures 1, Bob will also get 1. Right, and by this it can send the same information is exchanged between Alice and Bob. Okay, and this can go for a large number of large number of parties, provided you have this particular entanglement generator which can handle that number of qubits having entangled. Okay, so I will skip a bit due to the time. I will just say that I will just go into this type of process, which is a software stack for the quantum key agreement. Okay, so you actually generate the GHZ state preparation and distribution, and then the local measurements are done. Okay, based on the local measurements, you actually try to understand what is the string of keys which are being generated, right, and then you can actually settle down the key, right? And obviously there will be some errors in the channels, and those what we need to take care of. Okay, so the stages of this particular thing is something I have prepared as a protocol. So you try to generate this this GHZ state with some sort of circuit, right? And then you do the local encoding to try to understand that what is the measurement, what is the value you have got in this particular qubit, right? And then you try to understand the different rounds you generate, okay, on the different bases. Z and X are the normally two bases of measurements. Z is equivalent to the horizontal vertical, right? And X is equivalent to the diagonal. Okay, so that is the way you do, so that you actually randomly generate this particular 0 and 1, not a particular same way of generation. So the change of bases and rounds makes the things a random generation. Okay, so the key is randomly generated and it's being communicated to the entanglement states. Okay, right? And this is what is being done. And there are certain things we have to also take care of: bit error, phase error, channel noise, because this is a quantum channel. You cannot say that everything is ideal and I've communicated the key. So you have to take care of all of these. Okay, if the error is above a particular level, you have to abort it. Okay, this can be due to the attack scenario of the Eve, or there can be a degradation of the channel by itself. So we are trying to make a sort of an ML-based algorithm which will try to predict this scenario, whether a channel is attacked or a channel is being due to the error itself in the channel. Okay, decoherence of the channel. So I will try to just skip all these things. There can be error correction also if error happens, and right. So there are quantum side channel attacks which are there referred in the literature. Okay, right, and these are now needs to be handled on the top of this quantum entanglement or QKD type of communication. Though DVQKD is a very, very simple QKD. The focus is on entanglement, because as I showed, that entanglement uses less resource for each of the users, more resource on the state preparators, so you can concentrate on the central resource without actually making more resource for the users. So that is the most common scaling up QKD works on the entanglement based QKD. Okay, so I'm not getting into this attack. So this is the multi-party QKD stack. This has been developed in our lab. Okay, for an email communication, we have published in recent conference, and we are trying to get it done in the journal also. So we have developed this entire thing. The only thing, these devices we are not having. Okay. Maybe some of the labs are having the real QKD channels and QKD devices. So we are trying to use the IBM backend. Okay, which is giving this random QKD simulator. Okay, right, and we are trying to make this work based on that particular inputs. Okay, but those who have the QKD, physical QKD, they can try out this stack, and right, and if they wants to work with us, we can we can collaborate. Okay. So a lot of things we are trying to do. We are trying to look into the different types of secured IP applications and trying to involve this QKD, multi-party QKD entanglement. Okay, right, and try to get it error-free, secured, right, in different type of applications. And I'm just skipping it a bit. And there are a lot of real-world deployments. Okay, real-world deployments in Spain. Okay, right, in the Germany. Okay, right, and many countries have done it. They don't actually China also, right? They don't that everybody doesn't disclose that what they have done. Okay. Many of the countries have done long communication with this particular things. Okay, this is actually application what we are doing, which is a agnostic secure group email communication. Okay, the group email communication, you need to have a sort of the for the security, we need to have some sort of keys exchange between the parties. Okay, right, and and that can be done. Okay. A lot of applications can be done. As we know, military is one of the focused application. I think the first QKD was installed in India by the military labs, right? And then obviously financial networks. We are working with the data centers, which are also using this. We're also trying to get into this QKD. There's a lot of good application areas are there. Okay. So India, we know the National Quantum Mission, QNew Labs has developed the indigenous QKD device, and this is so good, right? They are still supporting a lot of things here. Today I got the information that SRM IST Chennai has installed the QKD facility from QNew Labs, which is very good. So we have a lot of this NQM mission going on across the country. Okay, a lot of things are there. You can try to work out. I will send up to the organizers. Okay, taking due to the time and not getting into all of this. So these are some of the things you can obviously get into. There are a lot of technology development needs to be there. Okay, in terms of quantum repeaters, in terms of quantum error corrections, right? In the communication, a lot of key management, a lot of things needs to be done in this particular domain to make it applicable in the real internet. Okay. So I end here. I will just try to expose all of you here is that what is the basic of this multi-party QKD. Okay, right? How entanglement occurs, right? And what are the things we have to take care apart from the circuit, apart from the communication channel, we also have to take care of the error. Okay, there are a lot of application space exist in space, in defense, in finance, in logistics, right? Where we require a lot of communications with multiple parties, secret communications, right? And probably the quantum communication and quantum network, okay, right, is our future. And we look forward to some good quality research and product development in this direction. Okay, thank you all for listening to me. These are the good references you can go through. Okay, thank you.
Any questions?
If there are any questions, I can answer a few, though I think I have crossed my time by 7 minutes. Okay. Yeah, sorry for that. Yeah, so if any questions.
I
Sir, I do have a
questions.
question.
Yeah, please go ahead. Please go ahead.
Good morning, sir. I'm Ashmit Singh from EC department at JSS University.
Okay.
So the question that I wanted to ask was that what mathematical concept should I focus on first to understand quantum computing deeply?
Okay, so
And
that is any next question you have, or this is the only question?
no, sir, also I'm currently starting to study quantum computing as I want to integrate it with my specialization in cybersecurity. So I also wanted to ask that which programming phase framework would you recommend?
Okay, great. Yeah. So first question is that what is the mathematical? So mathematical, obviously, you have to understand very well. Okay, the tensor calculus. Okay, the vector space. Okay, because quantum state space in terms of a computer scientist or a computer researcher. Okay, can be mapped to a vector space. Right, and you can you can do all sort of operators in the vector space. Only the thing is that you need to understand a little bit of this matrix algebra, because the entire operations in the quantum domain are unitary transforms, right? Maybe the unitary transforms are bigger in the first stage, but you need to decompose them into smaller unitary transform so that you can map the entire transform into single qubit and 2 qubit operations. So once you do that, you can actually define a quantum transformation in the quantum state space, right? And that is now decomposed into circuit, right? And there, I think you can have a good understanding that what needs to be done. In terms of programming, there are good programming platforms, right? IBM Qiskit is one of the good programming platforms. Python Jupyter Notebook supports the Qiskit extension. So you can always have a Jupyter Notebook and you can have the Qiskit extension there. For the real hardware, you need to have a sort of an API call to the IBM hardware. Presently, they give 10 minutes in a month free, but they say that if you use it very regularly, they can give some more time to you, right? Apart from IBM, you have AWS Braket. Okay, right? You have a QNuverse of CDAC, which is also coming up. Okay, right? And there are for quantum machine learning, there's Pennylen. So there are a few platforms which you can integrate on your Python, the all-around Python libraries. So you can go ahead on those. Yeah.
And so one final question, sir, is that for someone like me who is aiming a career in cybersecurity, should I spend more time learning quantum algorithms or post-quantum cryptography?
I think the cybersecurity is going post-quantum cryptography. So post-quantum cryptography, if you really want to develop quantum algorithm, then quantum is fine. But if you are sticking to cybersecurity, I think post-quantum cryptography is the thing. And also you should have some knowledge on this type of QKD and quantum internet protocols, which are coming up in the next few years.
Okay, sir. Thank you, sir.
Thank you.
Any other question? No questions. So on behalf of the Department of Electronics and Communication Engineering, I would like to express our heartfelt gratitude to our esteemed speaker, Professor Amlan Chakrabarty, for delivering such an insightful and engaging lecture on quantum communication. Once again, thank you, sir, for taking the time to be with us today and for sharing your valuable knowledge and experience. We are truly grateful for your presence and hope to welcome you again in the future. Thank you, sir.
Yeah, thank you, Dr. Gayatri. Thank you, Dr. Puja, right? And thanks to all my colleagues at JSS. Thanks to all.
Thank you so much, sir. Thank you.
Thank you. Thank you. I'm signing off. I have another meeting. Okay.
Yeah. Thank you so much.
Take care. Bye. Take care.
Thank you, sir.
Thank you. Namaskar.
Namaskar, sir.
I now request Dr. Gayatri Sakya, convener, to kindly guide us through the next session of the summit. Over to you, ma'am.
Thank you, Dr. Puja. Now I will welcome for the panel discussion, and the theme of the panel is Preparing India for Quantum Security Era, Risk, Compliances, Capability, Capacity Gaps, Opportunities, Strategic Priorities, and Roadmaps. So we are having with us the eminent speakers, Mr. Sumant Parimal, who will be the moderator of this panel discussion. And I want to introduce him first. Mr. Sumant Parimal is a founder and director of Innogress. He is a distinguished industry leader, market analyst, consultant, and entrepreneur with over 27 years of global experience spanning North America, Europe, Africa,
Hello, Gayatri.
and AI Technology Park in Greater Noida, with the vision of creating a world-class AI and robotic ecosystem. Business leaders on innovation, market strategies, and emerging technologies. His insights have been featured by Forbes and other international platforms, making him one of the leading voices in the future of technology and innovation. Welcome, sir. Welcome, sir, for this panel discussion. And now I want to introduce the next panelist, Mr. Dr. Mahesha Pandit, sir. Dr. Mahesha Pandit is the well-known face and he is the Chief Technology Officer, Canaris IT Solutions. He has accomplished CTO, Chief Technology Officer with 30 years of experience in technology leadership, digital transformation, and enterprise innovation. He holds the PhD in Artificial Intelligence and is the author of Agentic AI and is the holder of India's first granted patent in post-quantum cryptography, PQC. As a member of Government of India Quantum Technology Standard Committee, he contributes to shaping the national roadmap for secure 5G, 6G communication. His expertise spans AI, quantum safe security, cyber security, and enterprise architecture. And he has led technology initiatives for global organizations, including Airbus, Bosch, and Capgemini. Beyond Canaris, he serves an adjunct professor and is a contributor to the Quantum Technology Division of the Department of Telecommunication, Government of India. And I just want to share that he is handling the summer internship for our JSS University students this time since last 20 days. And it is very impactful training he is giving to our students. So thank you, sir, and welcome Dr. Mahesha Pandit for this panel discussion. Now,
Thank you,
next
ma'am.
I want to introduce, Professor Ajay Singh, who is a distinguished technology leader with over 35 years of experience in IT industry. Professor Ajay Singh is a prominent technology leader, cybersecurity, and former chief operating officer and head of strategy at Synergy Quantum India. He serves as a designated member on the task force of the implementation of quantum safe ecosystem under Indian government's National Quantum Mission. Safe ecosystem under National Quantum Mission. He served as the CEO of an award-winning fintech company for more than a decade and has extensive expertise in corporate strategy, governance, risk management, and digital transformation. He had successfully led the development and deployment of IT solutions across the banking, telecom, government sectors for the global market. So, welcome, Professor Ajay Singh, sir. And now I next welcome Dr. Arniban Bhattacharjee, who is an assistant professor in the Department of CSE and researcher specializing in quantum computing at SVNIT Surat. His research focuses on the design and optimization of quantum circuits, testing of reversible circuits, and quantum machine learning. Through his work, he contributes to the advancement of efficient quantum algorithms and next generation quantum computing technology. So, welcome, Dr. Arniban Bhattacharjee, sir. I think he is not here.
Yeah, thank you,
Yes,
ma'am.
yeah, welcome, sir. Welcome, sir. So, and the next panelist is Dr. Anindita Banerjee, is a senior quantum technologist and project manager for quantum technology project at CTech Pune, where she leads several national initiatives in quantum technologies. Her research focuses on quantum key distribution (QKD), quantum random number generation (QRNG), aerial quantum communication, and quantum computing applications. Previously, as quantum research head and vice president at QNU Labs, she led the development of India's first fiber-based QKD system and contributed to the pioneering quantum-safe cybersecurity solutions. She holds 4 US patents and 1 Indian patent, has authored numerous research publications and a book on quantum communication, and actively contributes to quantum education, curriculum development, and research training across India. So I welcome you all, and I just request our Suman Parimal sir to moderate the panel discussion. Over to you, sir.
Thank you, Dr. Gayatri, and thank you to EC Department and JSS University for organizing such a insightful conclave today, and particularly especially focus on the security aspects of the quantum technology. And this is the one aspect which is budging not only in India but around the world. And I think the theme which we have today for the panel discussion is preparing India for the quantum security era, and we will discuss the associated risk, the compliance perspective, capability and capacity building perspectives, including the gap and opportunities, and then strategic priorities and what kind of roadmap we as a country and we as an institution or maybe for our startups we should pursue. And we are privileged to have such a distinguished panelist here, and each of them are really accomplished person and professional in their own field. And I think the coverage which we are doing, particularly in the sectors like the BFSI, which is one of the heavily digitized sector, and the impact of quantum security and quantum computing is going to be most visible in BFSI sector. And then we have the healthcare and pharma. That's one area which we will touch here during our deliberation. And then education, research, and technology sector, because this event is getting organized by one of the leading educational institute. So that's every participant would like to know how the quantum security and quantum, cryptography is going to impact the educational sector, and not the least the defense, because once our country is secured, then only we are going to be secured. So defense is a strategic sector where we need to make sure that our critical assets and our defense lines are secure from any vulnerability which are emerging due to the power of computing. And in last session, we had a terrific presentation from one of eminent professor, Mr. Chakravarti, and he actually highlighted how the power of quantum computing can break the existing encryptions, right? And then how the quantum computing itself can, some of the features of quantum computing itself can be used for securing the quantum information going forward, right? So these are the theme of the panel, and I will start with one of the key panelists, and who is one of the accomplished panelists, and he also gives the insights to our National Quantum Mission. And I'll welcome Professor Ajay Singh. And thank you, sir. I remain following regarding your insights on quantum security and other quantum communication and other aspects of quantum technology. And it's a privilege to have you today in this insightful session. And I'll request you particularly to enrich us with what's happening under the NQM, and particularly the Government of India and RBI mandates across the quantum security, and how the country is preparing for Q-Day. And particularly, we know that recently the Finance Ministry of Government of India has directed the public sector bank to make themselves ready with the quantum security solutions and to have the strategies for any future Q-Day. And now recently the RBI has also formed a task force. And not only in India, even in the White House has also released a set of instruction to the various federal agency to migrate to the quantum safe encryption and cryptography. So these all global things built with the local national agenda. I like to have your perspective, sir, that how the various agencies and institutions of India, including the government agency and private enterprises, banks, so to actually mitigate the risk which is emerging from the quantum security perspective, and also from the quantum day that we call Q-Day perspective, and how this the entire regulation and mandates are going to impact our operations, particularly the digital tech operation, or we call digital ecosystem or digital economy, we also call, right, sir? Over to you, sir.
Very good morning, Sumanji. Good morning to my fellow panelists and to all the participants. It's a pleasure to be here. What you have raised, Sumanji, is so many questions at the same time. So let me try and decode this for our participants in the simplest possible way. Quantum computing has been in technologies have been worked on for the last 100 years. So why are we concerned now? Why is everything on the front pages in terms of quantum technologies? Why is it being considered as one of the technologies that is going to be a game changer for the whole world and for India? The reason is that there is an evolution that takes place in technology, and just like AI has been around for over 50 years, but in the last 3 years, you have seen the real impact of AI. Going forward, you are going to see a similar impact of quantum computing because it has reached a stage where it has moved from the R&D labs into commercialization. And when anything happens with the technology of the magnitude and capability of quantum computing or AI, it is going to disrupt everything that exists. Now, when I say it's going to disrupt everything that exists, it means two things. One, it's going to pose a whole lot of new risks, and it is also going to bring forth a whole set of new opportunities. So there are two sides of the coin, and sometimes the risks are more immediate than the opportunities, and sometimes the opportunities take precedence over risks. Like in the case of AI, we've jumped into AI, the risks are following, and we will deal with the risks as we go forward. In the quantum, it's slightly reversed because the risks are looming large. You talked about Q-Day. So what is Q-Day? Q-Day is the day where a cryptographically relevant quantum computer will be able to break the key encryption that we are using to encrypt our data. What does that mean? All our data in financial systems, government systems, and all critical systems is kept in an encrypted state. And the encryptions we have been using are about 35 years old vintage. So these encryptions, the key sizes that we use, encryptions like RSA, ECC, have been around for 30, 35 years, and they have served well because encryptions, it was not easy for classical computers to break encryptions. Now, with quantum computers coming, they have a faster way of breaking large key sizes, and therefore our encrypted data is all at risk, which means that the minute a powerful computer, powerful enough to break these key sizes, available to any adversary country or to any hacking group or to any or digital mafia, they are going to use it to break encryption. And when they can break encryption, you can imagine the havoc that it will create, because you and I sleep peacefully today because all our transaction data is encrypted. Just for an example, India today does about 2,000 crore of digital transactions per day. The banking system is doing about 2,000 crores. Now, apart from this, you have a lot of government data, you have Aadhaar data, you have voter data, you have so much of critical government data, schemes data, all of which is kept in an encrypted state. But this encryption is of vintage value. Thirdly, there is the intellectual property angle. A lot of our intellectual property is kept in an encrypted state. Again, the keys that have been used are the keys that are today possibly breakable by a quantum computer, which means that our entire data is at risk. So what we need to do is we need to prepare ourselves for this day. Unlike it's similar to Y2K. Y2K had a definite date. It was 1/1/2000, where computers were expected to crash around the world. So there was a lot of preparatory activity so that this doesn't happen. But in the case of Q-Day, the date when a quantum computer which can break encryption is available is uncertain. And when it is available, probably it won't be announced publicly, and people will quietly break encryption. So that is the risk. So that is why quantum has come initially as a risk. And of course, there are lots of opportunities where things which were previously not possible using classical computers in drug discovery, climate change, etc. That all that is possible with a quantum computer. So to dwell upon the risk factor, governments all over the world are concerned about risk. You talked about the US government issuing 2 circulars recently. Two recent examples, we have had 2 major cyber attacks in the last 1 month. One at the nuclear plant data got exposed on the dark web. Another was Tata Electronics. These 2 are big firms. These are very critical national data for national security. Now, this data perhaps was encrypted or not encrypted. I do not know, but even if it was encrypted using the previous keys that were available. Now, we have to make all this data quantum safe, and there is a deadline looming on us. The National Quantum Mission has fixed certain deadlines. We have advanced the deadline significantly compared to the rest of the world. So we want all critical data by 2029 or 2030 to be made quantum safe, which means post-quantum cryptography. We move to a regime of post-quantum cryptography and use newer algorithms which will secure our data, hopefully for the next 30 years, but it may not last for 30 years, but it will still last for a longer period of time. So therefore, if we want to protect ourselves, we have to ensure that all sectors of the economy, all the critical sectors of the economy, including sectors like power, insurance, defense, all these sectors have to implement and move to a regime where we implement post-quantum cryptography and QKD wherever necessary, and therefore we secure our data so that any adversary country or any digital mafia does not take advantage. They are already trying to harvest a lot of data and store it so that when they have access to a computer, they can break it. So therefore, all the sectors, as you see, SEBI, RBI, they've set up their own task forces. Their milestones have been defined by the NQM, and they will align their sectoral milestones with the NQM milestones. And hopefully, we will avert any sort of risk to our national security or our digital systems and ensure that our digital economy is not disturbed or hurt in any manner. And that is the goal of the NQM task force.
Thank you so much for enlightening us with the strategic importance of the proactive planning for mitigating any risk associated with Q-Day. And let's come to the next panelist, Dr. Mahesa Panditji. And I think your experience across the industry verticals, not only in India, but even outside India, is going to actually enrich us. You have seen various technology, how you have seen the Y2K migration, as sir was also mentioning. Then you have seen the cloud migration, and now we are coming to a stage where the mass migration from the classical computing to, particularly from the encryption side, to the quantum encryption is going to happen. I mean, it is bound to happen, as sir has mentioned, that we are looking forward for the entire quantum encryption by 2029, 30. That's the roadmap. So this is going to be a mass migration. When we talk about the global trillion economy, the economy size is I think 30 trillion, 29 to 30 trillion that is the size if I am correctly able to estimate. And Indian digital economy size is going to touch 1 trillion soon. USD I am talking about. So such a massive digital economy we have, and now we have to ensure that we are quantum safe. And so like to know, sir, how you think that our industry should quickly migrate and adopt this quantum cryptography and quantum safe encryption, and also to mitigate the risk about the few days, and the vulnerability in and how to actually, you are also developing on some of the methodology and frameworks or identifying the vulnerable cryptography systems, and how should enterprise or organizations to build their roadmap, to mitigate from the post-quantum cryptography risk. I'll look forward from you, sir, Mahesa Pandit, sir.
Okay. Thank you, Sumanji. Thank you, JSS, for inviting me for this interesting conclave. And it's an honor and privilege to work with the esteemed panelists. To address this question, Sumanji, see, over the past 30 years, we have seen several disruptions, several generations of computing. Maybe the generation may not be the right word, but major shifts. For example, the Y2K shifted something. Then the event-driven programming lifted out of the green screens. Then the cloud introduced the Java revolutionized object-oriented programming. The emergence of web. Every time the emergence of web, then the cloud, and now the quantum. It seems to be 3 to 5 years something major is changing within the IT industry, and change management. The software industry, the industries were much aware of this, and successfully mitigated and migrated the cycles within this software industry. The quantum threat is slightly different. Every time it is different, but this time the awareness is not as clear as the other things. Y2K, everyone understood. It was something simple to understand. But as Dr. Ajay Singh was saying, how much of the impact is going to happen because of this? The awareness is not much. So the industry is not really well prepared. The tools and technologies are emerging. Quantum computing is a different paradigm. We don't understand how this magical system can break everything. And so, first of all, one of my observations over the 30 years is security has always been an afterthought. Okay. Many people believe that the infrastructure, if you secure the infrastructure, then the application is secure. That's not the case in every time. Now, AI models are introducing their own security issues. For example, you may harden the infrastructure, but the poison is in the data. For example, you build an RAG system which reads a financial system that reads other documents. There could be an indirect prompt in the other documents to disregard these the original prompt. So there is poisoning, data poisoning. These are the new emerging paradigms. The industry is facing two things. One is the security of the AI and AI models. So that we have to battle. The other one is this post-quantum cryptography requirement, with regulators talking about deadlines, and then people introducing tools that may help or may not help, and the mixture of quantum and post-quantum cryptography. Actually, if you think about it, post-quantum cryptography has got nothing to do with quantum computing. They're two different dimensions actually. So preparing to use a quantum computer is something different. Repairing or strengthening your existing software and data because of the threat of the quantum is a different problem. So many CEOs do not understand. They think post-quantum cryptography is quantum computing. They are not. So the industry is not at all ready for this. There are a lot of noise in the in every platform. Go to LinkedIn, everybody started posting about quantum and post-quantum cryptography. But within the enterprise, the readiness is very weak. So I suggest that industries, even in our company, we are doing this. I think there are 4 steps they have to take. One is, first of all, understand what is it that you have, right? What kind of systems you have. Generate something called as cryptographic bill of materials. You may have heard about software bill of materials. It's a list of which technology you have, how did you build this, what were the participating libraries, what are their versions. That is a software bill of materials. It's easy to generate. But cryptographic bill of materials has to be generated by the banks and all vulnerable sectors. That's the first step. Systematically discover where this RSA, ECC, and Diffie-Hellman are actually embedded. Is it the TLS handshake or the high security modules, signing certificates, legacy middleware, third-party libraries which you don't control? So we came across a customer of ours who was surprised to find cryptography buried in 20-year-old batch job and vendor supplied software which they never audited. So the first step I suggest is do this cryptographic bill of material. You generate that, so you will know where is this encryption and what is the nature of that encryption. Once you do that, now you can think of hardening or protecting your system. Here also we have a problem. Y2K and other things, migrating to some other language, most of the time we rip and replace the code. Okay, just remove that code and insert something else. This is not a rip and replace change. So it should be consciously done. There are estimates as to when the Q day is going to happen. So keeping that in mind, you should look at your transactions, your data, and estimate the vulnerability correctly. For example, if a data or a transaction has a 2-year or 3-year value, then that's a short-term data. Now, what is the value of the data after 1 year, 2 year, 3 years? You should have a fair amount of awareness of that, and short-term, low-value data, maybe you can archive it. Don't even expose or even delete if that matters. So different strategies has to be adopted here, and all of those strategies can be designed only if you know what is it that you have and what are you trying to protect. So that is about the existing things, and we are continuously developing. The development has not stopped. We are putting out new novel technologies. So for the futuristic technologies, we have to build hybrid crypto agile architectures. Crypto agile. There are many standards that NIST has finalized. MLKEM, MLDSA, and all those are the new algorithms that will keep us safe. So this we have to adapt right from the beginning, especially in the new when we are developing the new things. And the fourth thing is, it's not one BFSI, one bank's IT department problem. No, this is an entire supply chain has to be examined, because a given bank or any institute, they don't use their own systems always. There are third parties supplying software modules. So it's not one department's problem. It's the entire ecosystem has to be looked at. So in my opinion, to prepare for this, these are the 4 steps. One, know about what is the impact or what are we talking about, that we have to understand. Is it quantum computing or is it post-quantum cryptography problem? Which one we are addressing? So what is the role of that post-quantum cryptography? And second one is what is it that you have, the quantum bill of material. Third one is understand your data and systems lives, how long this is going to be living. Retire unwanted software, low value adding software, and replace it with robust future ready better systems, because every change management is an opportunity to get rid of old things, what you don't want. So treat this also as such an opportunity to get rid of certain things. And also the fourth one is, build systems in which the security is a part of the design, not an afterthought. And so if we do this, I think we'll be in a better shape to deal with this thing. And of course, the other one is look at your entire supply chain. It's not just your department, it's your company. This threat, you have to look across the entire supply chain and see who is giving you what and how are you auditing what you are getting. So this is what I would think the businesses should take up on a priority basis. Sumanji.
Yeah, thank you, sir. Thank you so much for such an insightful, kind of how industry should adopt an approach towards migrating the post-quantum cryptography or maybe the quantum key distribution technology, and also how we can mitigate Q-day risk. And based on your experience, not only for this post-quantum era, but the classical era and mainframe era, I think you have very kind of wonderfully summarized that how important is discovering edges, edges of the vulnerabilities we have in the present cryptography. And I think going forward throughout the day, I think there are many other experts who are going to deliberate in this area, and I think one Mayank Verma is also going to have in another panel. So what I'm trying to say to the participant that remain connected with throughout the session. You'll have many other experts overview also. I think now we'll move to the next expert, Dr. Anandita Banerjee ji. So she is actually one of the key person in CDEC Pune, particularly focusing on the quantum computing and quantum technology projects. And her experience, particularly in starting founding team of QNU Labs and presently in CDEC, and her research work previously actually provided very key experiences to her to understand and work on the various quantum industry, quantum technology related problems. So I understand, ma'am, that presently you are focusing on some of the QKD projects of highly critical sectors like defense. And so, without disclosing too much about what exactly you and your team is doing at CDEC, we'd like to know actually how the critical organization like yours, CDEC, is going to assist the key sectors like defense and finance and healthcare and education sector, technology sector, to keep safe from any future Q-day vulnerability, and how CDEC is helping on protecting the strategic communications and our warfare communications, and particularly using the quantum technology like QKD and PQC or any other technology like other quantum communication, or quantum sensing from security perspective, right? So I'd like to hear your view, ma'am, and thank you so much for coming and participating in this panel discussion. Yeah, you are on mute, Dr. Anita. Looks like she dropped or what?
Hello.
Yeah, now you are audible. Please go ahead, ma'am.
Yeah. So, after I joined CDAC, my work was primarily on, how to complement or bring quantum expertise at CDAC Pune, right? So I built quantum technology prototypes. Earlier I had built, when I'm saying build again, we have to be careful. I'm talking about a level from TRL 2 to TRL 4 and 5, where I'm proving the proof of concept. And from there on, a product formulation, rather a prototype formulation takes place with the product team. So this is how the technology actually moves. We work with standardizations organization also, because standardization usually starts with TRL3. So just Sumanji, please tell me if you are able to hear me clearly, or is there some?
Yes, you are clear. Please go ahead.
Okay. So we have brought out 2 or 3 prototypes, which I would want to discuss here. One is the fiber-based QKD. So when we're talking about fiber QKD, we know that this has existed in the ecosystem last few years. But how we are making it different is we are taking it to the user and trying to discuss use cases with them, for example, particularly in fintech domain. So it looks like people are aware of this technology, that it is important, but they are struggling to find use cases and, how are you going to put this solution into their network, be it QKD, be it PQC, be it QRNG. We are having these discussions with fintech, fintech sector, from banks to industry. And the problem also lies because there is a mandate of transitioning into, or adapting the latest toolkit to make it resilient towards the AI, to incorporate AI. Now, this quantum comes along with all of it. And as you have rightly mentioned, that there is a mandate to transition to PQC quantum resistant algorithms by 2030. And this has primarily happened because of the advancements of quantum computers by IBM, where they are bringing out millions of qubits together and delivering about some 2,000 to 3,000 fault tolerant qubits. They are building quantum centric supercomputers. And that is a real concern, because you'll be realizing those mathematical problems out there, which normally takes many years to realize in a classical computer. So the threat is there, and we are talking about quantum utility area, not talking about any hype. It's no more a hype. So yes, there is a struggle, and we are trying to address that part. We can bring this prototype even to academic institutions, because also we have to think about the supply chain and also about indigenization of these products. So there also we have made an attempt to indigenize or to incorporate or to encourage IITs and R&D organizations, startups, and industries, if they are bringing up some indigenous module, to incorporate it in our solution. So that is also a part of our plan. And when we're talking about with banks, the usual use case is server to server or quantum VPN, or taking the quantum keys for some application. For example, we have done recent demonstration with IIT Bhilai and CDAC Noida, where we enabled the 2-factor authentication. And after that, QKD keys were used to do a secure encryption decryption. QRNG, we are working on indigenous solutions. We have done entanglement-based QRNG. superposition based QRNG. We are working on quantum noise based QRNG now, and these are all indigenous. Then if we take you to 2035, the quantum internet is going to be, 2030 will be a pre-quantum utility era, and there you will see people demonstrating QKD using satellites over there will not be just one or two use cases. There will be multiple use cases all around the globe. So India too would have to address this part, and this calls for quantum secure communication in a hybrid mode where you have space, aerial, and fiber. So we are working on aerial prototypes. So we have included the quantum entanglement distribution on the drone, and then we are establishing a QKD network on the ground using entangled photons from the drone. So this is a step towards quantum internet or distributed quantum computing or quantum sensing, because if you're bringing quantum to a drone platform, you open up immense possibilities. Now, we have also done drone to ground station PQC based encryption decryption. So we have developed lightweight compute boards where we are doing secure image transmission. So again, if you're talking about the entire product, this is just a part of the product where we are demonstrating this technology from the drone. Now, when we are developing these modules indigenously, we are training our team members. So this also gave us an opportunity to come out with educational platforms for universities, center of excellences, or strategic agencies to train their employees, because when you show the hardware, the transitioning or the adoption becomes easier. So when you talk about superposition, and when you have a system which generates superposition and does an application, so our CK quantum and quantum Pragyan education kits, which are on the lower side, and they provide excellent education to universities. Now, our recent project is on building, establishing a 5-bit quantum computer based on superconducting transmon qubits. We scale it to 25. Now, the project is interesting because we are working with different R&Ds of.
Ma'am, your voice is dropping in between. Could you please repeat your last few sentences? I think we missed in between.
Is it audible? Is it audible?
Yeah, so is it audible to others, or it's only my?
Sir, it's breaking, sir. It's breaking.
Yeah. So, Anandita ji,
Okay.
if you could please repeat some of your last sentences. Now it is good. अभी भी break हो रहा है ना? So
ये ऑनलाइन में ऐसे ही होगा. Internet connectivity.
Okay, so I was talking about educational platforms.
Now it is better, ma'am. Please go ahead.
Talking about the educational platform CK Quantum and Quantum Pragyan, where we are working on indigenization of critical modules there, and we are bringing it out to universities. One is on superposition and another is on quantum entanglement. It is also a toolkit for demonstrating different quantum gates to students. So when you are visualizing a NOT gate, how does a quantum NOT gate work? Along with the middleware and the backend has been developed.
So I think maybe for the next question, next question answer, you'll get some time. What I request to Dr. Anandita to re-log in between, we'll have a next question with Dr. Anirban ji. And so thanking Dr. Anandita for her perspective, particularly what CDAC is doing. And CDAC is one of the key R&D organization which supports the country strategic goals, and securing the defense communication is one of the key requirement right now. And I'm glad to see that CDAC is actually doing that. And one of our industry partner and one of the panelists was supposed to be in this panel today. The next panel. So he was also associated with DRDO Secure Communication Project. So which the BC sir was mentioning during his inaugural talk. So how the DRDO, by using the QKD technology, have secured their communication, so that's the fantastic progress happening in our country, particularly for securing the defense communication using the quantum key encryption and the quantum technology. Now I'll come to the next panelist, Dr. Anirban Bhattacharya ji. You are from NIT Surat. I think you bring a lot of educational institution perspective, and this conference is also getting organized in one of the university, JSS University, Noida. So I think we'll look forward for your insights on what most significant capacity gaps in India we have in quantum security. We discuss about the quantum and AI education, but this time we are especially going to focus on the quantum security aspect of the education and research ecosystem, particularly in terms of faculty and expertise, laboratory infrastructure, training facility, industry exposure, and then the program and curriculums, such that the faculty and not only students but faculty also get prepared, because you see the kind of problem and the opportunity we have in the quantum domain is huge. We can't only rely with the available professionals in this field, but we have to also include our faculties, as a consultant or consulting or professional expertise skills, so that they can actually consult to the industry for solving the emerging problems, because the impact of the Q day is going to be huge. So it's like war mode situation. Now every resource is available, whether it's in the R&D institution or whether it's in university, whether it's in educational institution or whether in industry. They all should be leveraged and prepared for mitigating the risk coming from the Q day. So we want to listen from you, particularly from like you are coming from educational background and having also background in quantum technology. How you recommend or how you suggest the institutions like JSS Noida to actually prepare themselves, not only the students but also the faculties and other resources to face or to mitigate these kind of emerging risks in quantum tech, quantum computing, quantum security, and quantum communication, and keeping in mind the enhanced quantum security, because these all technology we are talking about, but our focus today is the quantum security. So over to you, Professor Anirban.
Thank you, sir. Is I am audible?
Yes, please go ahead.
Okay. So, we already all know that National Quantum Mission has already established 4 thematic hubs. That is, IISc Bangalore is the Quantum Computation Hub, IIT Madras is the Quantum Communication Hub, IIT Bombay is the Quantum Sensing and Metrology Hub, and IIT Delhi is the Quantum Device and Materials Hub. But despite establishing these 4 thematic hubs, there has been an acute education. This educational system is still suffering from deep structural gaps. That is, we all know that human capital is the cornerstone for India's quantum ambitions. So building such a sustainable quantum ecosystem basically requires a huge coordinated investment in education, research, infrastructure, and interdisciplinary collaboration should be there, and innovation will be coming up, obviously. But the main important risk that we are currently facing as being a faculty, that I am also facing, is that there is a shortage of the talent pool Okay, that is now the demand for the quantum scientists, engineers, software developers, and cybersecurity experts are significantly exceeding the current supply that we can provide. That is that we have seen that there has been a rapid global advancement of the quantum technologies is happening. That has actually created an unprecedented demand for a highly specialized workforce. So governments, industries, research institutions, and startups are investing billions of dollars in quantum computing, quantum communication, quantum sensing, and quantum cybersecurity. But the number of trained professionals entering the workforce remains far below the demand. This talent gap has become one of the most significant barriers to the growth of the quantum ecosystem, especially in India. So we know that the quantum technologies are deep rooted into the advanced concepts of the quantum mechanics. Basically, it is a hybridization of the mathematics, physics, and computer science. But developing an expertise in these fields requires years of specialized education and research. So only a limited number of one of the current challenges that we are facing, first of all, is that only a limited number of universities are basically offering dedicated programs in quantum technologies. Like if I say that in my institute, that is, there has been no such yet quantum course in the form of elective has been offered yet, but I am going to launch, that is inculcate, I am going to introduce the core elective course very soon, but so far there has been no such course that has been introduced in my institution. And the same I have seen across all the colleges in Gujarat. And also the thing is that most physics and engineering curriculum basically introduces quantum mechanics only from a theoretical perspective, with having little emphasis given on the practical applications. And there are very few doctoral researchers and postdoctoral fellows that are specializing in quantum technology. So these are the challenges that we are facing. That is because of this, what is happening, the number of faculty members capable of supervising the advanced quantum research is also getting limited. Okay, so that is, if I consider my institution, in my entire institution, so I am the only faculty that has been that is having an expertise in quantum computing, except that is some of the faculty members in the physics department. Obviously they are doing some research, but their research is only from the theoretical perspective. There is no such, that is, they are not aware about quantum computing, quantum communication. So that is completely theoretical relative to the quantum mechanics. But so that is, the expertise in quantum domain are basically densely concentrated in the few leading institutions in the form of IISc, IITs, some NITs, TIFR, but the regular engineering colleges across India don't have resources in the form of faculties who understand both the deep physics side of quantum and the practical software side of cybersecurity. So there are not enough qualified faculty or teachers are available to go around. Second thing is that there is a lack of interdisciplinary training is there that connects quantum mechanics with computer science engineering and practical cyber defense. So quantum mechanics is treated purely as a physics subject, while cybersecurity is mainly treated as one of the computer science subject. So students are not being taught how to combine these two fields together. So to build a quantum defense systems, you need to train people who should understand both the physics and the computer coding. But current colleges are implementing the courses only in the separate areas only. Okay. Second thing is that we know that building quantum security tools requires a lot of expenses. It also requires specialized equipments, that is in the form of the clean rooms, cryogenic setups are needed, and optical labs will be needed. So there is a quite huge expenses needed to build such a quantum security tool based lab. So but most local and regional colleges, that is the tier 2 and tier 3 colleges, simply cannot afford this kind of hardware. So their students have no way to get hands-on practice to run realistic programs on the simulations, leaving them only with the textbook knowledge. So these are the problems, the challenges that we are having. And also our academic research is still mainly concentrated on publication of papers in the form of conferences and journal, rather than building a deployable commercial grade enterprise software or production ready QKD devices. So this is also the drawback that we are because due to that is the academic structure we are having, we are mainly focusing on the publications of the journals and conferences, rather than producing something really good quantum QKD based devices. But how the institution can address this one and build a stronger talent pipeline? The first thing that according to me, it will be very good if we can actually implement these strategies in reality. The first thing that we can incorporate a cross-disciplinary based curriculum. That is, in order to implement this strategy, what are the actions that we need to perform is like that. We might need to partner with the AICT to expand the currently UG minor and MTech courses that will merge the quantum mechanics with the network security and the cryptography. Okay, so what this will do, this will make sure that the moment a student is graduating, they don't have just the degree. They already know how to write real code to protect data from quantum hackers from their very first day on the job. Second thing that we can focus on the hardware agnostic software tracks, because it is quite beyond the imagination, beyond for any colleges to purchase the quantum security hardware. So what we can go for the hardware agnostic based software. That is, instead of waiting to buy multi-million-dollar quantum computers, colleges should teach students how to make use of free online software tools like the IBM Qiskit. Pennylen is there. Then Q Universe. It is not a free open source tool, but it is quite manageable to purchase. That is, it is quite reasonable. Q Universe is mainly having with the CDAC Bangalore, but it is the budget is not too much high, so you can any colleges can afford to buy the Q Universe. So that is the student should learn to build quantum safe digital security locks that work on normal everyday computers, that is on the traditional computer. So this will help to quickly train thousands of regular software developers to understand quantum safety, so they can immediately join the cybersecurity workforce and protect businesses, because we are lagging. That is, the talent pool is quite limited. So this way we can increase the talent pool, we can satisfy the demand what we are currently having. So the second thing is that we can have a concept of shared infrastructure based network. That is, we can incorporate a spoke and hub cloud based model. So what the thing is that since the local and regional colleges cannot afford the expensive quantum labs, what the NQM can do is that the National Quantum Mission can connect the thematic hubs infrastructure model via cloud platforms. So students from small town colleges can also log on to their infrastructure tools through the cloud and run experiments in remote. So this will facilitate the students outside of the IITs to get the same hands-on practice. And the thing is that we can also have a concept, we should incorporate this one. We should have the internship with the builders. That is, we need to make it mandatory for the students to do summer internship programs or projects with real world quantum startups and national defense labs like ISRO, DRDO, a quantum research project allied with the CDAC, that we can do. Recently, I have started this one. That is, I have started that is deploying my MTech students to work in the form of an internship in CDAC Bangalore. So they will get a real-time exposure. So what they are actually doing. So this will what the benefit that we can achieve by incorporating this one is that this will force them to work with real companies and defense teams, which will help them to learn how to build actual products that will protect the banks, military data, and useful for the national security. So these are the things that we can what are the risks that we are currently facing, and what are the things that we can go for, which will be useful enough to build the task force. So this is the thing, that is, first of all, that is, we need to develop the talent pool in a quite in a very useful manner, in a planned manner, in a planned approach, so that the higher, that is the quantum education, has been disbursed across many students. And also that is, the colleges should incorporate the quantum education, either in the form of a quantum computing or in the form of quantum cryptography, so in their departmental course, or either as a core elective in their department or as an institute elective. So I will always suggest that is to better to float those subjects as an institute elective, because it will become an interdisciplinary one, because we need students across all the disciplines to learn about the quantum science. So these are the things.
Yeah, thank you, Professor Anirbanji. I mean, it's really great listening to you, and you, since you are the part of the system, particularly in educational institutions, so you understand where are the gap areas, and you have rightly mentioned some of the remedies to strengthen our capabilities and ability of skilled resources in quantum technology and quantum security. And I know you'll have some closing thoughts, but that we will now. Our time is almost getting over, because we had only 1 hour of discussion in the panel. So what I'll do, I will skip the specific questions, and rather we will come towards the closing remark from each of our panelists. So while I'll request them, while doing their closing remarks, to cover some of the perspective which includes the missing capabilities, like Professor Anirban has actually highlighted some of the missing capabilities. So wherever we have the missing capabilities, be it industry or be it R&D organization, like our research institutes, and or in the academic institution, like our NITs and IIT, or for that matter in universities also. So these are also the point of opportunities, So what I suggest that you keep in concluding remark, keep these points in mind, that these gaps area, like what you have addressed, and how these gaps can be converted in opportunity, and including which may include some challenges also. And then what kind of applied quantum projects and infrastructure and implementation capability and capacity we should build going forward in our institution and in our industry, and what are the key takeaways or key future action items we should have before we reach the Q day, So in next 2 year, 1 year to 2 year, so that we become 100% quantum secure, and we are ready to face any Q day attack, and we are compliant with all directives coming from various regulatory institutions, including our own RBI and overseas regulations, because now the digital is a connected world. We can't prepare ourselves with only India perspective, but we have to, our institutions and our companies and our enterprises need to prepare from the global perspective, So in concluding remark, I would like to follow the same order, starting with Professor Ajay Singh Ji. Sir, what should be our next action items, in next 1 to 2 years, so that we kind of leverage our whatever capability, also build our capability, and we face these upcoming challenges of Q day, or rather harvest the next opportunity related with the quantum technology, right, sir?
Yeah, clearly there are multiple dimensions to the whole introduction of quantum technologies into this whole digital ecosystem. And it is inevitable, it is going to happen. And for the first time, I think there is a large-scale attempt to proactively address these issues, whether it is PQC, whether it is QKD, whether it is to leverage opportunities in the quantum space whether it is building talent across institutions, whether it is to build our own startup ecosystem, whether it is to build the lab testing labs for testing our future solutions that are being developed, whether it is developing applications that can make us strategically strong in the world of quantum computing. So there are all these issues on the table now, and I think each of these issues is being proactively addressed. I would only like to say that it is all about prioritization. And in a country where we have so many challenges and so many priorities, conflicting priorities at a country level, at an organization level, even at individual levels nowadays, we have lots of conflicting priorities. The thing is, this is something that deserves priority. And all organizations in whatever sphere of activity they are in have to give this the kind of priority and make this a center stage activity so that we don't miss the bus as far as the quantum technologies is concerned. We should not be an also-ran. We have an opportunity to be among the top 3 or 4 nations in the world in quantum technologies. There's no doubt about it. But there are lots of things to be done. We need to handle all of these and address all of these areas. And we are engaged in this activity. But I think it is for also the organizations at an individual level, at sectoral levels, to step up and prioritize the introduction of quantum technologies into their digital ecosystems. Whether it's on the risk side or the opportunity side, they should be ready to exploit both.
Thank you, sir, for your concluding remarks. It's really insightful. Now, the consultant like, us, including yourself and Dr. Mahesa Pandit and, all panelists are consultant here also and experts also. Now, we should be working, what I understand, we should be working on framework, how to integrate quantum technology and quantum security with the digital ecosystem presently we have. So your concluding remark, Dr. Mahesa Panditji, on these same aspects and area which I mentioned, challenges and opportunity and the roadmap for the next few years in terms of priorities, right, sir?
Yeah. So, I want to talk from the industry perspective. Today, the industry will not invest in anything where there is no money. So quantum, at least in my company, they see as some magical box. They keep postponing investment into quantum. So the problem here is, I was talking to a Niti Aayog member, like the way we have CSR, there should be some policy initiative, some incentives for R&D, for companies investing in R&D. It seems to be there, but we don't know what exactly it is. It's not straightforward as CSR. Like 2% of your profit should go to CSR. Similarly, there should be some tax incentive, some motivation for the businesses to invest in capability building in quantum. Today, it's not there, and most of the businesses do not invest because they don't see the return on investment. Now, the academics on the other side are too academic. Okay, they lack the practical aspects of it, and because we hired someone and that person was not able to was in a different world altogether, the academic world. These two worlds, there has to be some kind of a vehicle that connects these two, and that vehicle, a special purpose vehicle or a joint COE or something, should be promoted, incentivized, and encouraged by the government. Only then there will be some kind of a motivation for the industry to invest in this, and for the academics also some clarity where we are heading. The problem with industry partnership, academics lean heavily on the industry to guide. We don't have time. We don't have internships and all. Interns come with a specific ask. Tell me what I should do. Spoon feed me. Hand hold me. We don't have that time. So some bridging, this internship also, there has to be some kind of program where the academic also takes interest in internships. What today academics are doing is they are sending their students, that's it. And it's very difficult for us, the industry, to handhold these people. So somewhere we have to come closer together. The government should incentivize, motivate us to set up common special purpose vehicles so that industry can invest and academics can also get a business perspective. And interns also need another layer of mentoring, not fully leaving it on the industry. It's simply we don't have bandwidth. That's my definitely the need are well articulated by the other panelists. I'm just saying from a business perspective and also as an entrepreneur perspective. When I look for a talent from the academics, I expect them to be ready on day one. This has remained as a dream. I know it's impractical, but there is no motivation from our side to invest in this. So
thank you so much, sir. I mean,
Yeah.
it was really wonderful to direct industry insights coming from you. And thank you for mentoring students, not only from JSS, but from other universities also. I know that's a undeclared CSR we are doing. We industry people are doing. We are actually helping our educational institution, because when our educational institution grows, we also grow, right? Because they support us, they support the industry. And one thing you mentioned in the opening remark, that there is no incentive coming either from the government or for any that matter from other sources also for the technology adopters. So I think 2-3 years back when the NQM was getting launched, I in fact retained these points to the highest decision maker of the country, that not only the startups who are or university institution who are developing the quantum technology need to be funded or incentivized, but those who are going to adopt this technology, that is industry, need to be also motivated through some incentives. Until unless the industry is not going to adopt these innovative technology, the market will not emerge. Only will have product but no adopter, right? As you mentioned, that there is no motivation in industry. So through this panel discussion, again, because the NQM representation is there through Professor Rajesh Singh. So I think I'll again put forward this point that, yeah, in the entire National Quantum Mission, there need to be one aspect also for motivating industry or incentivizing the industry to adopt the nascent quantum technology, which are getting developed under the NQM, or for that matter, even outside NQM, right? For this concluding remark, I come to Dr. Anandita, for her concluding remarks, right? So, Dr. Anandita, please, now you have already listened to other panelists in terms of their concluding remark. Particularly, you are representing one of the leading research institution, CDAC. So please go ahead and have your insights, madam, which can become a solid takeaway for all of us.
So I have a few points here. First, if you're talking about CDAC, when I joined CDAC 4.5-5 years back, there was zero infrastructure and there were zero manpower. I was the first one. But today, after 5 years, 4.5-5 years, we have accommodated so many MTechs in quantum technology, right? So there is, if there is intention and there is a roadmap in mind, then the organization works towards it. There's a lot of money given from the different government organizations also, apart from NQM, the different ministries funding. So that is not an issue. Again, I would say, if coming to industry, recently we demonstrated this technology to MasterCards. So, MasterCard in India, they started with discovering, quantum was their title. Whereas in MasterCard, they had started doing POCs about 15 years back in US, right? So when you're talking about industry in India, to create a peer pressure and all, it will take time, mostly maybe, around 2030 when there will be a Q day approaching. Perhaps that time there will be certain industries who will say that we are Q ready, okay? And that time Indian industries will have a very difficult time to acquaint themselves and also for the transition, because transition always takes time. And there are few industries, because I always work with industry, who are actually coming forward and also investing, because they have a good vision about their company. So I would also like to say to academic universities and big organizations like JSS themselves to acquaint your students and faculties with the hardware. Okay, because a lot can be developed indigenously. You have different disciplines of your students, mechanical, electrical, electronics, computer science. You have maths, you have physics. So when you're developing technology, because now I'm working with different prototypes, right? From QKD, QRNJ, PQC, and now to building of a quantum computer, I can see so many disciplines coming, interplay. So there is a skill requirement, and universities should try bringing technology to their campus. And also, now again, since I'm interacting with different ministries, so when I'm talking or trying to sell my prototype, I have to engage with different divisions. So I would also insist on bringing quantum to not only physics or electronics, but also to business and arts, because you need to think out of box. So once you have a prototype ready, somebody has to design it, somebody has to design the enclosure, somebody has to think about new ways or new pitch. So MBAs or they will be actually people who will be selling them, right? So they should know about the technology. They should be good sellers. So I think we have to keep this in mind. Bring hardware technologies to academia, expose this technology to different disciplines, including arts and business development, or be different sectors. And we all need to come out of our comfort zone. I would also say, since the experts are coming from different disciplines, so from in industry, academia, R&D organization, value the experts, let them come and introduce technology, find out ways, because it's a new world opening. Everybody has to come out of their comfort zone and try to accommodate the technology and the experts and the prototypes. So I think I have made my point. Thank you.
Thank you, madam. And I think your last point, which particularly say that we need more sellers, not only scientists. That is the one job I'm doing since last 4 or 5 years. I was selling quantum tech concept to government officials and including investors. So everybody is bothered about the ROI, and until unless we prove some ROI, and ROI proving will take some time until unless someone not implementing how ROI will be established. But we can have a separate panel discussion on the quantum technology ROI. But this is the more focus on the quantum security. So I'll have last panelist here, Dr. Anirban, to conclude with his remarks, closing remarks, because now we are almost up with the time. So maybe I requesting Dr. Anirban to finish his closing remarks in 1 and 2 minutes, please.
Yes, sir. So already we have seen that is we are already facing a lot of lacking behind the talent pool, both in the form of the faculty members as well as in the form of the students interested to pursue their career in quantum education. So already that is we are already having a BTech minor course in the form of quantum technology, but that is quite limited. So that is the funding has been provided from the under the National Quantum Mission under this program, but that has been restricted to only around 100 colleges. But we have seen that it is also less than 100. We have seen the last year that is kept around 25 to 30 colleges at max. So then what will happen for the other colleges who is not getting any funding in respect to the launching these programs in their curriculum? So obviously this thing might be this initiative should be coming much more from the National Quantum Mission side, from the DST or the central government, that is to expand the awareness, quantum awareness across all the public and private institutions. The first thing, that is they should be establishing a nationwide quantum education framework with a standardized curriculum, online learning resources, and interdisciplinary degree programs. So then they can also expand the national quantum research infrastructure through shared facilities that I have already discussed, that is creating a hub and spoke cloud model. That is the colleges, the regional colleges are going to share the IIT, that is the thematic hub infrastructure via cloud. So that is one of the thing. And also we need to strengthen the academic industry collaboration by creating innovation hubs, joint research centers, and startup accelerators focused in quantum technologies. This is one of the important thing where the students will get an exposure to the real-time projects, how it is actually being done, how the real-time real-time startups how they are working in the form of defense sectors, or in the quantum startups and quantum companies, how they are working. Also, I will request that is National Quantum Mission to invest heavily in faculty development programs, scholarships, and fellowships to build a robust pipeline of the researchers and educators. As we are missing, that is, there is a less number of manpower, human resource we are having. So we need to motivate them. So that initiative also should be coming out. That is how we can address those things. So in the next 5 years, we will overcome the how many manpower that we are currently having and the manpower that we are going to achieve in the next 5 years. So we can derive all these things, and also we can promote international collaborations also while strengthening indigenous research capabilities and retaining the top talent in our country, rather than they are moving out. A brain, there is a one constant brain drain is also happening, because there is a less facility, infrastructural facility or funding opportunity, less funding opportunities. Most of the researchers in quantum technology are moving out to settling down in the outside of our nation. So we need to address all these things, and my recommendation is obviously that is launching new national quantum talent mission should be launched from the National Quantum Mission in order to train the students, researcher, and faculty members, as well as the professionals through multidisciplinary programs and these certification pathways. So this thing, I think they can take an initiative rather than making it too much late.
Thank you, Dr. Anand. So thank you so much for such a great insight. I go with it that public investment, particularly the NQM investments, are not good enough, even for the startups and for the academic institution to harvest the opportunities emerging from frontier technology and deep technology like quantum. And recently we saw the US government pumped $2 billion of additional money in their quantum initiatives. $1 is straight away given for setting up the quantum fab. Another $1 billion being given for various quantum startups and research institutions to strengthening their capability. So right now, our Indian quantum mission is around $600 million. I think at least $2 billion need to be immediately injected. This is the outcome of our panel discussion. So I think I thank you all the panelists here, and this was the great insights. And I think we are going to summarize all your insights and share it as actionable item. We may submit it to National Quantum Mission and our other stakeholders also going forward. And this all depends on the organizer here, how they will going to leverage the insights which are coming out from the various panel discussion of this conference. I'll thank you again, the JSS University and BC sir, the entire team of JSS University who have been organizing this conference, and also the entire panelists and all the participants for recently listening to this insightful panel discussion on quantum security and quantum technology. Back to you, Dr. Gayatri Sakia ji. You are muted, Dr. Gayatri ji.
Thank you to all panel members and the moderator for such an insightful panel discussion, and with so much input we have. And now I expect continuous guidance to JSS University Noida for developing quantum technology ecosystem, so that we can develop the research labs, we can develop the center of excellence, and also according to your the inputs we got from the panel discussion, we will try to open the minor degree programs as well as the MTech programs in quantum technology. So we are having like we can open in the specialized field like in quantum security, in quantum communication, like that we can pursue. So we will keep seeking the guidance from all the panelists, and we hope for the to come up with a great ecosystem in JSS University Noida with the help of you all. Thank you so much. Thank you all panelists. Thank you.
Thank you, madam. Thank you. So I'm signing off for some time from here. Okay, thank you.
Okay. Now, sir, next we have the session of Professor R.P. Singh, who is waiting since long. So I'll just hand over to Pooja for welcoming him. Over to you, Pooja.
Thank you, ma'am. Thank you for this opportunity. It is my pleasure to introduce our next esteemed speaker, Dr. R.P. Singh. Dr. R.P. Singh is a renowned expert in laser physics, quantum optics, and quantum communication. During his tenure at the Physical Research Laboratory, Ahmedabad, he established world-class experimental facilities in laser physics and quantum optics and played a pivotal role in creating the interdisciplinary atomic, molecular, and optical physics division. He is currently associated with IIT Gandhinagar as a visiting faculty and actively contributes to free space quantum communication projects under India's National Quantum Science and Technology Program, supported by the Department of Science and Technology and the Department of Space Tourism. I warmly invite everyone to join me in welcoming our esteemed guest, Dr. R.P. Singh. Over to you, sir.
Thank you. Thank you very much for introduction and inviting. To start with, let me say I'm not very fond of these online things. Okay. But anyway, since you may be running sort of resources, it's okay if you organize online, because I have a feeling that the kind of interaction you have during in-person meetings that completely a different level. And so most of the time I decline to give online, but anyway, it's fine. Hope I'm audible.
Yes, sir.
Yes, sir. You're audible.
Thank you. Let me see. I have shared my screen. It's coming. Can you see that? I've shared my screen. It's coming. Can you see that screen?
Yes, sir. Now it is.
Okay, good. Thank you. So I have been asked to talk about this quantum imaging and cryptography. When I say cryptography, mainly quantum cryptography, or quantum cryptography has two sections. One is called PQC, post-quantum cryptography, that is based on algorithm, and it has nothing to do with quantum mechanics or quantum principles. Okay, and another is quantum key distribution, and that is based on quantum mechanical principles. Okay, that quantum key distribution. So it has two. So let's talk about this quantum imaging in cryptography, and whatever work I'm going to present. There are many contributors, because when you do experiments, I'm basically experiment guy. So when you do experiments, a big lab, you need people to work on different experiments. And in that, you have PhD students, postdocs, younger faculty colleagues. So they are there. And all of them are very well placed. Some of them, like faculty members in PRL itself now, Gautam Samanta, Sashi Prabhakar, they are professors now in PRL. And some are at NST, some are Pranapa Institute. They are very at very good places. Some are like faculties in foreign universities, like Rupesh Kumar is University of York. So, and I retired from PRL 2 years back, but still work is going on. My student is there, Sashi Prabhakar, who is now professor. So I go to lab, and we are still having some experiments going on at PRL also, along with other places. And along with that association with PRL, I have a lab. We have formed after retirement. We have formed a lab, two-test lab. So we are talking of like how to train students. We are talking of using minor MTech course in quantum technology. So because I have been teaching and I have been doing experiments also. So we have developed certain educational kits like real kits for quantum technology. We make heralded single proton source. One can study what is that heralded single proton source, how to verify that single proton source, then entangled proton source. We provide that entangled proton source and characterization facility. How you characterize that, whether it's really entangled proton source. Then we make a quantum key distribution system. One can learn how to develop the key, how one can use that key, like using quantum mechanics. We make that real system, quantum key distribution system, how to make keys and how to use those keys to encrypting the message to make it secure. So all those things we make, we have supplied to few institutes already, 2-3 institutes. We are looking for more. We are looking for funds also, so that we can have some reserve kits. Somebody asks, we can supply immediately. Right now, we are not in that position. We don't have so much funds. Yeah. So basically, you must be hearing Professor Amlan Chakravarti also talked about this entanglement, and you must be hearing about superposition and all those things. So superposition is very basic to quantum mechanics. Okay, and even entanglement is a special case of superposition, like two parties. Yeah, it's a special two quantum systems, how they are correlated quantum system, superposition of that, how these correlated quantum systems live into superposition. So that's the quantum entanglement. And the idea, like it's thought experiment given by Schrodinger, this thought experiment does that suppose there is a cat in a box and along with this poison. So unless until you check the cat whether cat is dead or alive, so both the possibilities are there equally. So cat is in the superposition state of dead and alive. So that kind of state is called superposition. Although in classical world it doesn't happen, it happens only in quantum world. So in a way, he wanted to put a contrast between this classical world and quantum world, because this classical world doesn't happen. Cat cannot be live and dead at the same time. Okay, but in quantum mechanical system, system can be in two states. Okay, at the same time, an atom can be in ground state and excited state at the same time, unless until you measure it's in a superposition state of. A photon can be in two state of polarization, horizontal and vertical, at the same time, unless until you measure it. So, but in classical world, it doesn't happen. So, in the same cat example, like cat in a box along with poison, can be used to enumerate, explain the entanglement also. Like here, cat is there, poison box is there. If cat is like poison, this poison bottle is broken, means cat is dead. So they are correlated, like poison bottle and state of cat. They are correlated. If it is broken, cat is dead. Cat is dead means it is broken. Same way, if it is alive, this poison bottle is unbroken. So they are very correlated. This state of poison bottle and state of cat. So that kind of system is called quantum entanglement. Certainly, we don't have that kind of thing in classical world. Okay, but in quantum world, we have that kind of correlation. Okay, so and then another very important property is no cloning theorem. That is very important for quantum communication or quantum key distribution, because unknown arbitrary quantum state cannot be cloned. Okay, suppose this is a cloning machine and it is being represented by an operator U. Okay, and what it does, it copies a state A on a blank state. Okay, that's what it does. So after this copying, you get two copies of the state. Okay. Now this operation is explained by this cloning machine. This is operator. This is cloning machine U, and there are two states at the input, and you get this A copies. Suppose now if A is a proper quantum state. Then superposition state, A plus B, and B is another quantum state, suppose. So their superposition, A plus B, this A plus B, this superposition of A and B, that is also a proper quantum state. And it's one quantum state. Superposition of two states will form a single quantum state. Suppose you have a single quantum state like A plus B, and you want to make a copy of that. So you put here A state A plus B here, yeah, superposition state, and then blank state. Then you want to have here A plus B and A plus B, okay, copy. But if you go by this operation, what you will get? First you operate U on A, you get AA. Then you operate U on B, you get BB. You don't get this kind of. So it's very simple in simple words. It explains that it's really not possible to clone or copy unknown arbitrary quantum state. And it plays a very vital role in secure communication, because you can't copy. That provides a safeguard again. If dropping, yeah. So how do you do that quantum communication or even quantum imaging? Because I've been talking a little bit of quantum imaging also, although I mainly work in quantum communication. We started working in quantum imaging also, but we have not done good amount of work in quantum imaging. Although communication, I can say that we have sizable amount of published from our lab. So you need sources, you need transmission channel, you need detectors. So sources, one can have weak coherent pulses, one can have a single photon source, entangled photon source. Weak coherent pulse is approximation to single photon source. You take a pulse laser, you reduce the intensity in such a way. There are attenuators. Attenuator reduce the intensity. So you reduce the intensity of pulse laser in such a way that on average per pulse is not having more than one photon. That kind of source is called weak coherent pulse, and it has on average not more than one photon. But this is just an approximation to a single photon source. It's not a single photon source. When you say single photon source, it means that at a time there is only one photon, okay, for sure. So that's single photon source. So at a time there is only one photon, and probability of getting two photons at the same time is almost zero. So that kind of source, and you can measure that, you can experimentally verify that probability of getting two photons at the same time is almost zero. Then only after this verification you say that single photon source, and that's what I was telling you. We provide that kind of source through QTest lab. Okay. So and why this coherent weak pulse is just approximation? Because lasers follow certain photon statistics, that's called Poissonian photon distribution. And even if on average mean photon number per pulse is less than 1, there is sizable definite probability that there are some pulses will have more than 1 photon, 2 photons, 3 photons. So that creates problem when you are using weak coherent pulse for quantum key distribution. It may lead to photon number splitting attack, PNS attack. It's called photon number splitting attack. It's a serious attack in quantum key distribution or secure quantum communication. And here, this is heralded single photon source and entangled photon source. So you have laser, you have nonlinear crystal. Mainly we use Chi2 second order nonlinear crystal. So 1 photon of laser breaks into 2 photons, okay? And these 2 photons are produced at the same time. It's called spontaneous parametric down conversion, means down conversion. So energy is less than the pump photon, okay? So that's why this is blue, this is red, means energy is lower, okay, red one. So these 2 photons are created at the same time, and they have correlations, but you have to, they are correlated, but you have to verify in which variable they are correlated. So after verification, you can say they are correlated in this variable, they are entangled in that variable. So measurement is very important in quantum mechanics, and this coincidence, like how these 2 photons coming together, okay, you have to verify that these the photons you are going to use for technology, they are coming together. So they are coincident, they are coming at the same time, okay, with it. directed. So that you measure by timing electronics. Okay. And this very important in coincidence measurement is very important in quantum measurement. Okay. Coincidence detection. And heralded single photon source, how? These two photons coming at the same time. If you detect one photon, means a paired photon is there. Okay. Because they're coming at the same time. You detect one is, and it heralds the presence of another. That's why it's called heralded single photon source. And you know, we are dealing with light, okay, photons, communication. That's the beauty of this quantum communication or QKD, quantum key distribution, that it is like only photonic platform, optical platform you can use. You can't use any other platform, okay, for quantum communication. While in quantum computing, you might be knowing, you might have heard talks and all that one can use so many platforms. You have superconducting qubit, you have ions, ionic qubit, you have neutral atoms, you have electron spin semiconductor. You have so many platforms, defect centers like electron spin again, nuclear spin also you can use. So many platforms are there, and photonics also. So one can use photonics also for quantum computing. Photon is a qubit. So there are many competing platforms when it comes to quantum computers, but when it comes to quantum communication, there is only one platform. It's photons, optics. So that's why it's much more visible, okay, more ubiquitous. It's already being commercialized. This while when it comes to quantum computer, there is still a noisy intermediate scale, and nobody knows which platform will be the winning platform for quantum computing. Okay, till now. So, and then you have to do detection. Any experiment you do, you have source, you have transmission, probe. You probe using this source, you probe certain objects. Either you do imaging or you do the communication. So, and then you have detectors. So you have different kind of detectors. You have avalanche photodiode based single photon detectors. You have superconducting nanowire single photon detectors, okay, based on completely different principles, okay. And one is very compact, slightly less expensive. Another superconducting nanowire single photon detector. It's bulky and quite expensive. And then you have EMCC, electron multiplying CCD camera, you know, charge coupled device camera, you know, it's very common nowadays. So here you use electron multiplying CCD or scientific grade CMOS camera, okay. And then you have homodyne or heterodyne detectors also. If you are not using photons as a quantum system, okay, then you use field associated with photon, okay. There you measure field quadratures, which are continuous variable, and that is done by homodyne and heterodyne detectors. We'll be not going into continuous variable field quadrature measurements, okay. That's completely very independent of this discrete variable where you measure polarization or time of arrival. So it's very different. So we'll be confined to here in this talk mainly polarization, correlation, or measuring polarization, how to manipulate polarization, and how to measure polarization for quantum key distribution or quantum. So that's what I was telling, how you generate entangled photon source is like at the heart of either you go for quantum imaging or quantum key distribution. I will develop maybe 5 minutes. I will give like 5 minutes maybe for this, and you can ask questions in between. That will be good. Otherwise, you don't know whether. That's why I'm saying an online platform, and like I don't have much appreciation. Because you don't know somebody is listening, or they are just logged in, or they are over phone talking to somebody else, or so you don't know. So if you ask question, the speaker feels that somebody is listening at least. Yeah, he's not talking to computer. I see he's not talking to computer. So spontaneous parametric Down conversion. First thing is spontaneous. So it's a spontaneous thing. Okay, and so. And this is spontaneous emission that cannot be explained using classical mechanics. You have to have quantum mechanical concepts involved when it comes to spontaneous emission, because vacuum fluctuations doesn't play any role in classical physics. This without vacuum fluctuations, without presence of vacuum, you can't explain spontaneous emission. and spontaneous parametric down conversion. So parametric means this crystal is not affected. It's like parameters of the pump and this downward photons, and they are important. Okay, crystal remains unaffected here. That's why this parameter of this pump that's more important. So then parametric down conversion I told earlier also that why, because pump is having higher energy and this emitted photons we call signal and idler. Okay, they come in pairs, so they may have they will have less energy. Okay, and so this process follows energy and momentum conservation. This phase matching condition is basically momentum conservation. You can see that this is pump photon energy frequency, and this is energy S cross 2 multiplied. Okay, angular frequency multiplied by S cross H by 2 pi. It gives the pump photon energy, and then you get this signal and idler. One pair are like one photon of the pair and another photon of the pair. Signal and idler we call. So energy is conserved. So one photon is absorbed, okay, and then two photons are emitted. Energy is conserved. Nothing happens to the crystal. Okay, just photon breaks into two. One pump photon breaks into two. But this is not very efficient process. I must tell you. Even the best of the crystals, they have like, if you have like large number of photons, so only one photon or 10 power 6 photons, okay, will be getting down converted. So if you have 10 power 15 photons per second, suppose coming from laser, 1 milliwatt laser, 2 milliwatt laser, that are the photons are coming, only 10 power 8 or 10 power 9 photons will get converted out of 10 power 15 into like signal idea. And this is momentum conservation. You can see that like pump momentum, this is direction, and then this is signal idea. So this is being considered. These are the like review articles one can note down and then go through. And this is by Suman Karan, who has done PhD at IIT Kanpur, along with Anand Jha, and this Ali Anwar, who has done PhD with me. So they have written a good article, and one can go through that, how to make entangled photon source, okay, using crystals, nonlinear crystals. So this is one of the setup, very compact setup. You can see that. Yeah.
Excuse me.
Yeah,
Sir,
yeah.
I have small questions about that.
Yeah, sure.
So what is the PIM diameter when you are supposed to be set up with this entire experiment? Is there any specific?
Yeah,
or,
this is around,
samples?
yeah, it's in millimeter, 1 millimeter, or maybe 100, 500 micron, 200 micron, depending on the crystal size, like what is the crystal size you are having, what is the aperture of the crystal. So it is 1 meter to 500 micron, something like 0.5 millimeter, something like that. You have to do loose focusing, okay, of the laser. So this is the setup. Yeah. Pardon?
Pulse repetition rate?
If we are making this weak coherent pulses, here this entangled photon source, when we are making, here we are using CW, but one can use a pulse also, not a problem. But here we are using CW pump. And pulse repeater rate, you can be have like megahertz, gigahertz, whatever.
How to increase the generation rate if you're talking about the free space? Sir? I mean, the optical is something is different philosophy, but if you talk about the space, so how to increase the generation rate?
So you have to design new nonlinear crystals which are more efficient, or some new material which can produce single photons at a higher efficiency. Till date, you are not able to produce entangled photon pairs or even photon pairs more than 10 power 8, 10 power 9 per second. Okay, out of that 10 power 8, like 10 power 8, 10 power 10, like million, 1 million, 10 million, 10 million beyond, people are not able to go. So out of 10 power 7, these entangled photons which are correlated, they will be around 10 power 4, 10 power 5. Okay, so that is the limitation. So you have to design new materials. That's what I'm saying. Either the single photon or entangled photon, which will be more efficient. Yeah.
Okay. Thank you.
So this is very compact, 1 feet by 1.5 feet, something like that, whole setup. Okay, and This is Sagnac interferometer, and okay, Sagnac interferometer, but it's just one of the experimental schemes. You can use there are number of schemes. If you go to review article, I have suggested there are number of schemes which can be used to generate entangled photon source. This is not the only scheme. Okay, this is one of the schemes which is very efficient. Okay, and popular. But it's your ingenuity that you can use any configuration to produce correlated photon pairs. That's what you have to do. You have to produce two photons which are correlated. You have to measure the correlation, and then you have to see that which is much more efficient process. So here this is pump, okay, at 405. This is blue, okay, and this is half a plate rotates the polarization, okay. Suppose is pass axis of half a plate. It has 22.5 compared to the polarization axis of pump. So it will rotate the polarization by 45 degree. Okay, so that's the half a plate does. It's lens. Then you have mirrors. These are the analyzers, like polarizers basically. You can rotate the polarizers to analyze the polarization, to find out the polarization. So this polarizer analyzer, and this and these are the filters to cut out the, like, this is detector. Okay, you can see that single photon detectors. To cut out the stray photons, background photons, you use filters. Okay, narrow band filters, plus minus 5 nanometers or plus minus 2.5 nanometers. So you use filters. Then again you have to couple your output. These are the entangled photons. That's what you are measuring correlation. So then you couple to the fiber using this lenses and all. Okay, microscope objective fiber collimators. So this is single mode fiber. You connect to the single fiber. So what it's doing, this pump is coming and it's passing through polarizing beam splitter. So what is polarizing beam splitter? It's polarizing beam splitter, not normal beam splitter. Normal beam splitter, what it does, it divides the light into two parts, reflection and transmission. And what this polarizing beam splitter does, it divides into two polarizations, like horizontal and vertical. And this is D here. So D is like dual. Dual means there are two wavelengths. It works for both the wavelengths. Here you can see that this is blue and this is red. So there are two wavelengths. It works for both. And then this light passes through this half wave plate. This is again dual half wave plate, means work for both the wavelengths. And then it passes through nonlinear crystal. I have told you, you use nonlinear crystals. This is one of the nonlinear crystal, PPKTP, periodically polyKTP crystal. And you have to maintain the temperatures to like when I was discussing here, so you can have this correlated photons or these biphotons which are coming, signal idler. You can have in same direction. Okay, that's called collinear. You can have in the same different directions, non-collinear. And then you can have same wavelength, degenerate. You can have different wavelengths, non-degenerate. Okay, and but all these things like either non-degenerate or degenerate, collinear, non-collinear, or same polarization, orthogonal polarization, everything has to follow this energy and momentum conservation. Okay. So here we are dealing with degenerate, okay, degenerate and non-collinear, okay, spontaneous parametric conversion. So this comes to the crystal, and the one photon of the blue light gets converted into two photons, and that is like detected here. Okay, and you measure the polarization of both the photons and see that whether this polarization is correlated, even they are far apart. You see that in the lab also they are far apart. And we are trying to make this kind of entangled states. Means what is the meaning? If these are separated photons, okay, if you measure the polarization of this photon, if it is H, polarization of another photon is also H. H means horizontally polarized. If it is vertical for this is also vertical. So we have made this kind of entangled state, and then we verify. That's what I told. Coincidence measurement is very important. So we do the coincidence measurement. We get and whether they have arrived at the same time. That's the coincidence. Or because you can't have exactly same time, 0 time in delay, then you fix very start time interval like few picosecond, 20 picosecond, 80 picosecond, or 1 to 2 nanosecond, we say that if they are coming in that window, we say it's coming together. So that's what's being done. You fix the angle, one of the polarizer, and then you rotate the other polarizer. And if you do the coincidence counting, so coincidence counts will come like this. Okay. Here, this is one polarizer, one laser fixed as horizontal. Okay. And then another is being rotated. Here, one is fixed at D, diagonal polarized, this polarizer, and another is being rotated. So you get these two curves. It's like interference structure. So this is basically two photon interference, and you are looking for polarization correlation. So in normal interference, what you do, you must have done interferometry experiments. You do study field correlation. Okay, there you are studying field correlation. You get this kind of fringes. Here you are studying polarization correlation for two photons, and you get this kind of fringes. So one can measure the visibility of this interference pattern, and this visibility one can use to derive Bell inequality parameter. So, and then this is very robust. You can verify rather what you wanted to make, okay, whether you have got same thing. So for that, you do quantum state tomography. State tomography means you take number of measurement, what is done in CT scan. You make number of measurement using a scan like X-ray, and then you combine them to reconstruct the like body part which we are being CT scan. So same way you make number of measurement on these two photons, and then you combine all those measurements to see that what is the state of the photon. That's called quantum state tomography, and that one can do and then verify whether you have got the state which you intended to make. Okay, so we have verified. So it's very close to the state which we wanted to make. 0.975, like 97.5%. It's same state what we wanted to make. Experimentally, it's very difficult to get 100%. So we are very close to that. So that can be done. Okay, and it's very robust. There is not much fluctuation over the time. C3 36 seconds. Your counts are very stable. So these kind of sources, entangled photon sources, one can use in space also. This design, very robust design, to beam photons for quantum communication, quantum key distribution. So not only that, it's further, this design has been further modified to make it more robust against fluctuation in wavelength, robust against fluctuation in crystal temperature, robust against this deviation in crystal angle, optics. So how one can make it more robust? This combination of this hexagon, this is special kind of optics, like triangular thing instead of lens, circular, oval thing. This is triangular structure, and then this combination of this hexagon and lens, it produces the perfect ring. Here, this is SPDC photons. Okay, they come as a ring. Okay, and then if temperature is changing or crystal why it's coming like this? Our crystal angle is changing, some vibration is there on a platform, our temperature is fluctuating, environment is not very stable. So ring size changes, you see that. Okay. And if you make perfect ring, it doesn't matter if there is fluctuation in wavelength, small fluctuations, very tolerable, 404, 405. And if there is crystal angle fluctuation, it's very robust. It maintains the same. And why this maintaining the shape is very important, because you couple, if you have seen that, I was explaining you couple to the fiber. And fiber are very small, this core diameter, few microns. If they are changing the size, you won't be able to couple through the fiber your photons which are being down converted, and you can't take for your application where you want. So that is the problem. So you have to make it robust so that always you get good number of photons coupled to the fiber, and this is this technique makes it much more robust so that more photons get coupled even if there is small fluctuation in temperature or wavelength. Okay. And then how do you measure? Already I have indicated, you do the coincidence detection. Okay, coincidence measurement, you fix some time window, small time window, and these 2 photons are coming there in that time window. So you say they are considered, they are coming at the same time. So for different polarizer and analyzer angles, different polarization angles where you are looking for correlation, like alpha, beta, you do the coincidence measurement. Another angle, you do the coincidence. So another angle, you do the coincidence, and by measuring this coincidence counts, okay, these are coincidence counts for different polarization and analyzer angles, you can find out the correlation coefficient. And once you have this correlation coefficient, you can find out the Bell parameter. Okay, this is called Bell parameter. You plug in this correlation coefficient here, and if this Bell parameter is more than 2, okay, it's bounded. Maximum value could be 2√2. More than 2, it's entangled, and if you get very close to 2√2, it's a maximally entangled. Okay, so that's the thing. So that's how you verify whether you have generated entangled photons or not. So how these entangled photons can give you advantage in imaging, like normal imaging, there is laser beam or full emitted light. It goes to object, you use some imaging like some lenses and all those things, and then you detect the intensity. Photon detectors basically intensity detectors. So different numbers means it corresponds to different number of photons distributed. Okay, so that's correspond to intensity. So photon detectors, single counts. So it intensity, how it is changing. So that regard gives you the image plus. But in quantum imaging, you have these 2 photons, and then you have to do coincidence count. That's what I'm always emphasizing. So this coincidence counting that gives you advantage. So you have 2 detectors and you do the coincidence counts. This is the object. Because why this gives advantage, you cut out the background because the coincidence. Okay, these 2 pairs you are only looking at, and stray photons are out. And there are other advantages also, like entanglement. Like if you have 2 photon entangled photons we are using, it gives better resolution 1/2 compared to 1. Okay, suppose single photon or single source we are using. And then if you have 4 photons, like then 1/4, okay, 2 square. So you get more better resolution if you have a higher number of entangled photons. So that is again you will improve the resolution also, which is not possible using. So you go beyond Rayleigh limit, okay, this resolution. So this is one of the schemes like ghost imaging. One can have this quantum ghost imaging. Here you see that signal, like signal idler photons, okay, and this is nonlinear crystal. There it was PPKTP, here it is BBO, another nonlinear crystal, okay. So here pump beam, okay, and that's converted into this 2 photons, paired photons, signal and idler, I and S, and then one is passing through the object, okay, but object with light, which is our photon, which is passing through object, this is not having any special information. This is bucket detector, single pixel detector, okay, it is not having special information. While the photon, this photon, which is going to the camera, it is not having any object, okay. And then once you do the coincidence detection, you get this image, okay, the object image. This is like when you are measuring position correlation, okay, of the photons. Then you get this kind of image. When you are measuring momentum correlation of the photons, okay, through coincidence detection, you get this image. And one can have undetected photon imaging, quantum imaging. How and where it is used, you can see that if you look at it carefully, it will tell you how it is useful. You have pump, okay, pump is like green, okay, and then you have nonlinear crystal that's converted into 2 photons, okay, one is yellow and one is, you see, this is non-degenerate, okay, not degenerate, this is non-degenerate, both are different colors, different wavelength. Detectors are available for this visible yellow, but this is infrared like light red, it has been shown infrared. So for this infrared light, detectors are not available. Now you see that this infrared light, which is like sensitive to the, suppose you want to do night detection, so this object is there, which is like sensitive to the infrared, and then you are, what you are doing, this is passing through this, okay, infrared, but it's not going to camera. You can see that it's going here, okay, and this yellow light it's going to the camera, to camera, and then you do the coincidence, and then you get the image of this object. Okay. So here you are using this yellow wavelength photons to get the image, where you have efficient detectors, while this infrared you don't have detectors. So that's the undetected photon. This photon is not, which is passing through the object for imaging, it's not being detected. Another photon of the pair is being detected, and that is giving you the image. Okay. And then quantum imaging through stray light. Even stray light is present, you can have very good image quality because of this coincidence thing. Okay. And there are many other advantages for quantum imaging. We will not go into that. Okay. But that's the advantage. Okay. If it is classical image, so this stray light lot of dots, you see these stray photons are coming. But if you are doing coincidence, all these stray photons are cut out, you get the very good quality. Let's go to the quantum cryptography. Cryptography, you know that what is cryptography. You guys use WhatsApp. Almost everybody uses WhatsApp or Telegram. There you see that end-to-end encrypted. Your message is end-to-end encrypted. What does it mean? Like you use some encryption key, and then you use some decryption key. Okay, that's the cryptography. So it can be like based on symmetric key, where this encryption key and decryption key is same. It may be like as symmetric key and asymmetric key, where encryption and decryption keys are different. Okay, so that's the like even if you are sending, nobody can read. That's the hiding in plain sight. Okay, it's visible, but you can't read it. That's it. So symmetric cryptography, here you can see that encryption, and this is ciphertext, this is plain text. After encryption, it's called ciphertext. And then you ciphertext, it goes, and this decryption key, and you get, this is symmetric. So both encryption and decryption same. Decryption is just inverse of encryption process. And you can see that encryption is like K to S. Then for decryption, you apply K, this Y thing, you apply over K, and you get the yes. Okay, that's what you have encrypted. You get it. So these DES, data encryption standards, and AES, you might have heard this advanced encryption standards. AES scheme is used for present encryption. So AES is used, so that they use this symmetric distribution. Okay. Symmetric and then asymmetric. Okay. So this asymmetric key distribution, your keys are different. You can see that. And this RSA, where this internet transaction banking, they use this RSA thing based on like large prime number factorization, prime factorization of large number. So that's the RSA algorithm, and it's very strong algorithm. And whole this quantum computing thing came in response to that, because Shor developed an algorithm, quantum algorithm based on this quantum mechanical principles. Peter Shor developed an algorithm, and showed that if you implement this quantum algorithm on a quantum computer, you can break that RSA encryption scheme. So after that, a lot of research started in this secure communication and quantum computation, because it was really like a big threat to the security of any agency. So this Peter Shor basically told that one can break RSA, and then there was a lot of like noise, a lot of work started in response to that. So this is like a classical thing in quantum. What you do, you can have like weak coherent pulses. One can use fiber or free space. As I told in the beginning, it said with photons, photon can travel through fiber or free space. Anything one can use. One can use, like here it is shown how one can do with free space, a long distance like communication using satellites. So you have weak coherent pulses which are generating right at producing entangled photons, here entangled photons, or here weak coherent pulse, like generating different polarization states. Here this device is there which is generating different polarization state, and then it is sent to the ground station, which is like telescope. Okay, and pointing acquisition and tracking system, that's like optical ground station. You have to have right pointing acquisition and tracking system to get signal, quantum signal at the ground. which is being sent from satellite hundreds of kilometers away, 5 to 800 kilometers away. That's LEO, low Earth orbit. One can have medium Earth orbit or GEO also, but most of the experiments are being done using LEO. So you send this population state, you make measurements, and now both the stations like satellite and ground station is having KA. Satellite goes to another ground station and then delivers the key KB. Now satellite is having KA and KB, both the keys is there with satellite. Keys are there with satellite. And then satellite, there is a device encryptor which can encrypt like K and KB. And then another this operation, your operation will give you the K. So now both the ground stations are having this K, or one can have KB, both the stations. And once they have same key, like I told, this quantum key distribution is still a symmetric key distribution. Then once you have key, secure key that is being developed using quantum mechanical principles, being distributed and developed using quantum mechanical principles, one can encrypt and decrypt, and that's how one can have secure quantum communication. And this kind of a scheme is called prepare and measure, because here states are being prepared and here it is being measured. So prepare and measure scheme. And these they use most of the time weak current pulses of single proton source, although it may lead to some problems, serious attacks, but it's still weak current pulses are more popular for this kind of schemes. Here, this is called a trusted node, means you are trusting that nobody is, satellite is not leaking key information to some other person or other satellite. So this is trusted node. Here, this is satellite is having just entangled photon source, and these two photons are coming, these paired photons are coming here and here, two stations. This is Bangalore, Ahmedabad, it can be any two stations far apart. And then you make measurement on these two photons, and by making measurement of two photons, you develop the key. And this key, once developed, you can use for quantum key distribution. Okay. So this is called untrusted node, because here key information is not there with satellite. Okay, so nobody can have like satellite cannot leak. Okay, and nobody can hack the satellite to get the information. So this is untrusted node where you are using entangled photons. So how much time I have? Excuse me, Dr. Saikya. Anybody is there? Or I'm just
Yes, sir.
talking to
Yes,
computer?
sir. Sir, till 1:15, 5 minutes ago.
Okay, fine. So this is one of the very popular protocol, BB84 protocol. So this is prepare and measure protocol, Bennett and Brassard, and 1984. That's why it's BB84. In 1984, they discussed this protocol in Bangalore, IC Bangalore, in a conference. So this is BB84 protocol. Here this L is one of the transmitter or any party name just L is, and Bob, it is like stuck to the communication since telegraphic days. Okay, L is Bob, Charlie, all those things since telegraphic days. That's why it's called L and Bob. Otherwise, you can call Ram Sita anything like transmitter receiver. So it's being prepared random states, like dice is there. It presents like randomly you are preparing these states. And this is RNG, random number generator you're using. Okay, instead of dice. So these vertical, horizontal, diagonal, anti-diagonal. So you assign these bits, okay, computational bits to these population states, and then you send. And here this Bob selects the random basis selection. This is like rectilinear basis, means horizontal and vertical, two-state basis population. This is diagonal, anti-diagonal. This is called diagonal basis. Okay, so Bob selects randomly these two bases, rectilinear and diagonal basis, make measurement. And if Bob selects the right basis, you get the key. If Bob doesn't select the right basis, you don't get the key. So if it is like here, you see this is diagonal, and Bob is measuring in rectilinear basis instead of diagonal basis. So you don't get the key. If this is diagonal and Bob is selecting this diagonal basis, you get the key. Same way for others also. Okay. So this is called shifted key. After that shifted key, you do the error correction and privacy amplification. And those are the error correction and privacy amplification. These are the classical communication protocols. Okay. beyond this point, it's all classical. Up to this point, you call shifted key or shift. It's quantum mechanical principles are being used here. And this is the experimental stream. Okay, quantum channel means you're sending quantum states, photons, which are like collation states. You're sending, you have prepared and you have sent, and then they are collected, and then single photon detectors, timing electronics. Okay, when it was sent, when it was detected, that's very important to develop the key, so that you are not detecting any other photon. The photon which is being sent, you are detecting that only. So time records tell you that. Okay. So it's very important. So this is a scheme here. You can see that this random number generator, we have used electronics for that. These are 4 laser diodes. They are randomly being switched on. These half-wave plates, they prepare the polation states. This is PBS, and this here you get horizontal and vertical polation. This is half-wave plates. So here you get diagonal and anti-diagonal. All these 4 states are combined at BS, beam splitter, and they are directed to the bar. If you want to have the fiber base, this is free space setup. If you want to have free space, you are using this optics. Okay, free space optics. You are using difference laser or Bacon laser for alignment. You're using optics here, collection and transmission optics. Suppose you want to have fiber base instead of this free space, you connect. Okay, this where you are combining, you do the fiber coupling. Okay, you connect to the fiber using fiber coupler, and again you couple near to this at the receiver side. Okay. So you bring that fiber here, and then you can analyze the light. Okay, so that's fiber. Okay, so they are very similar. Principles are almost same. Okay, so and then timing electronics will tell you. So these detectors, you know, these how basis selection is being done. This beam splitter here, so it does the random basis selection, because single photon it doesn't know where to go. Sometimes it will go randomly. It will go this side. Sometimes reflected. Sometimes transmitted, because you are dealing with single photons. So here this half-wave plate, so it does the DA selection, DA basis. So these 2 photons measure D and A polation states. This is PBS, so it does horizontal and vertical. Okay, horizontal and vertical D and A. So you know which detector is getting which photons, and then you the timing electronics you use. You prepare a setup on optical breadboard. You go to the field and do the transmission. Like you prepare the states in one cabin transmitter, and then you send to the reflector and then get back again. So that's how you get 200 meters. We were limited by the line of sight available in our campus. So it was 100-meter line of sight clear. Then that's why we use 200 for 200 meters. We have done reflection. So you receive that, then you measure. Here you are preparing the state, you are sending, then you are measuring, and that measurement tells you the gives you the key. So this is timing electronics. I'm always emphasizing. You are using 200 meters. Suppose you have sent this ELISA sent S polarization state, and if you see the counts in detector which is receiving S polarization at Bob side, you get high number of. This is around 400 plus, around 450, and then this vertical thing you get very small. You see that your numbers are small, so very small. If you measure this vertical counts, you look into the counts at vertical detector which receives the vertical polation. But good thing you notice that in diagonal and anti-diagonal you get almost equal, 200 plus something, and horizontal, if you're measuring in horizontal, it was 450 something. So horizontal, you can rise a superposition of D and A, equal superposition of D and A, diagonal and anti-diagonal, horizontal equalize light, you can write. So if you are getting equal number in D and A, means your setup is working fine, and this setup can be used for deriving the secure key, quantum keys. And for deriving the key, you should have all these parameters: channel transmittivity, detection efficiency, mean photon number per pulse, or entangled photon pair pulse generation per second. You should have idea. Then repetition rate of laser you should know, and based on those parameters you can derive the key. And here this shifted key rate is 200. This is the like detectors transmitted. Okay, that's many photons are being transmitted. These are the detectors. Then these many shifted key you get, and these are the error bits. Okay, so error bits, these errors are coming, then you do the quantum bit error rate. So this is like shift key rate, then you do the error correction and privacy amplification. So it reduces. So you get secure key smaller number, okay, compared to. You can use entangled photon same way. You make different bases to select and do the measurement. Here entangled photon, both Alice and Bob measuring at the same time. Same different random basis selection for population measurement, and then get the key. So similar setup, except that here it is entangled photon source being directed, okay, to two parties, Alice and Bob, one like nearby, one far, and then again timing becomes important. Okay, this is again breadboard setup. One can do that entangled photon based quantum key distribution. This is detailed schematic. This is Alice and Bob getting reflected coming here. This is like entangled photon source going to Alice, going to Bob. Okay, and then you measure the entanglement after 200 meters, distributing 200 meters apart these photons, and they are still entangled. Okay, and then you check your this counts. Okay, and again the filtering is very important. If you notice that 648 nanosecond here, that there it was 689 nanosecond. Why? Because now Alice and Bob, they are sitting in the same room instead of different rooms, so distance has changed. That's why this nanosecond. So timing is very important. If you are away by 1 nanosecond, you will not get this kind of counts. Okay, so even 1 nanosecond it changes, reduce the number. So because you are you have produced HS plus PV state kind of thing, that's why this diagonal thing will give you the key. Okay, that shifted key, and again you have to do error correction and privacy amplification to get the secure key. And these keys are affected by this atmosphere. Okay, if atmosphere is dirty, there are a lot of aerosols, you get lesser key. If like clean, you get higher shorter distance, more key, longer distance, less key. All those things you can verify. Then you have fiber and free space. You can combine free space and fiber to develop the network. Okay, so that's what is being done. You have satellite base or free space keys. So that's PRL Alice, PRL Bob. Okay, this K2 key. Okay, both are having K2, K2. This is like C dot. They have fiber based quantum key distribution system. They have K1, K1. The same principle as I told in satellite, you have K1, K2 here, and then you do the another JOR operation. You have K1 at both the places. Once you have K1, you can do this is the network, okay? Free space and fiber-based network. So that's how you plan to develop, one plans to develop this quantum key distribution network. That is very important. Okay, I will stop here. China, just I will tell you, China is the leader, and they have done all sorts of experiments using free space and fiber. Okay, they are the only country having satellite-based quantum key distribution network, not just two stations. They have network now, satellite-based quantum key distribution. They have established in collaboration with Austria and South Africa. They have developed a ground station, and they can have secure communication across the continents. Okay, so in communication, they are the leaders, either fiber or free space. Okay, I will end that. Okay, please ask question. Feel free to ask question. Yeah. Thank you. Hello.
Any questions?
Anybody having any question?
Sir, if you want to develop a trusted node between sender to receiver like Alice and Bob, so how many gates supposed to be? Is it possible to make one Franklin gate is sufficient to develop for the trusted node in cloud?
So using computer, quantum computer, you don't develop the trusted node. Okay, as you have seen that. Okay, quantum computer, you can do the simulation. Okay, like in classical, you do simulation in computer, then you do the experiments in lab. Okay, or do the field deployment in classical. Same in computer also, quantum computer, you do the simulation. You can use Franklin gate, whatever you develop that thing. Okay, but when it comes to field deployment, you have to generate entangled photons, distribute it, or whatever recurrent pulse or single photon source. You have to, yeah. So that's just simulation you're talking about. We are into.
Okay, because I read one paper, but that is basically the teleportations method. The first the entangle
just
with Alice and
computation
Bob
simulation of those protocols. Okay, it's not like real implementation.
Really is not possible. Okay, okay. Thank you, sir.
In real, you have to do these things. Yeah, that's what I was describing.
Okay. We'll try that.
Okay. Any other question? I think you are the only one who asked 2 questions. Rest are I don't know whether they have followed a bit or not. And there is point
At the
of
room
having this.
temperature, is it possible to generate a photon generation, sir? Like a graphene quantum dots and all?
Yeah. This is room temp. Depending on the material, some material will have a lot of noise, okay, background and all. There will be like electrons, vibration, all those things if they are not, if they are at room temperature. So depending on material, okay.
So I'm
You
using
can
a
have room
graphene.
temperature
Okay.
or
It's under the resolution.
cold. Pardon?
I'm using the graphene, sir. Graphene quantum dots.
Graphene quantum dot, then you have to verify whether you are getting either you need like cryostat or at room temperature. Graphene I have not studied, like I have not gone through the results. So without going into the results, I cannot comment whether you require room temperature or cryostat for getting single photons or integral photons. Okay. So depending on,
Basically, we are trying
depend
at
on the
room
material,
temperature.
yeah. Whether you require this cooling or you don't require cooling.
Yeah, okay. Okay, sir. Thank you so much.
Oh, Dr. Gayatri, Sakya, you have any question? You are convener. Or Monica, do you have any question? Or you guys are around? Or,
Yes, sir.
yeah, tell me if you have any question. I will not close unless until you ask question, being convener.
Yes, sir. Yes, sir. We'll just ask me, sir.
Yeah, please ask. Yeah. You're taking too much time in asking question. Any question you can ask. There
Yes,
is
sir.
no question, a silly question. Yeah.
The question is, how is quantum imaging, just a minute. How is quantum imaging different from infrared or thermal imaging?
So you have seen that this coincident detection that gives you all the advantage. Okay. So here this coincident detection you do, you generate these pair photons which are can be correlated in position momentum. They can be correlated in polarization. They can be in time bin entanglement. So depending on different kind of collisions, and you do the coincidence detection of these kind of photons after they pass through the object. Okay. And that
Yes.
coincident detection gives you the quantum imaging and all those things. Yeah. That's the crux of the quantum imaging. Okay. And that gives you all the advantage.
Yes, sir. Thank you, sir. Any more questions?
So entangled photon are the basic resource, very important resource in quantum technology. Okay. And one should study it much more like presently, time to study this entangled photon source. And this QTS lab makes entangled photon source. It's very open. It's not closed box, black box. One can see that how it's being produced and how it is being detected. Okay. So if your college wants to set up lab, you are welcome to use that kind of setup to learn how entangled photons are produced and detected. Fine.
Yes, yes, sir.
Thank you.
Thank you, sir.
On behalf of the Department of Electronics and Communication, I would like to express our sincere appreciation to our esteemed speaker, Dr. R.P. Singh, for delivering such an insightful and engaging session. Once again, thank you, sir, for graciously taking the time to be with us today and for sharing your invaluable expertise. It has been a privilege to learn from your experience. We sincerely appreciate your presence and look forward to welcoming you again in future. Thank you so much.
Thank you. See you.
Yeah. Now I request Dr. Chaya Dalena ma'am, Associate Professor, Department of Electronics and Communication Engineering, to guide us through this next session. Over to you, ma'am.
Thank you, Dr. Pooja. Good afternoon, everyone. It's my privilege to welcome you to the one of the most engaging segments of today's summit, the fireside chat. Although we are late little bit, but this interactive session brings together eminent experts to share their experiences and vision on the evolving landscape of quantum technologies in security. The fireside chat session will explore the real-world security implications of quantum technologies, separating genuine risk from exaggerated claims. For this fireside chat, I invite our distinguished panelist, Dr. Abhishek Tiwari, Associate Director and Scientist Staff at the Center for Development of Advanced Computing, CDAC Noida, Mr. Mayank Verma, CEO, co-founder at Curipshield Startup, and Dr. R.P. Singh as renowned expert in laser physics, quantum optics, and quantum communication, working in free space quantum communication projects under India's National Quantum Science and Technology Program. As moderator, I invite Dr. Kumar Gautam, founder and president of QRACE Quantum Research and Center of Excellence, founder and director of eGreen Quanta, and a leading expert in quantum computing, quantum machine learning, and deep tech innovation. To lead this insightful conversation, it's my pleasure to introduce Dr. Abhishek Tiwari first. Dr. Abhishek Tiwari has made significant contributions to India's Advanced Computing and Semiconductor Initiative and played a key role in the successful implementation of the Design Linked Incentive DLI scheme under the CHIP-in program. In recognition of his outstanding contributions, he was recently appreciated by the Director General CDAC at the DLI CHIP in May 2025. Welcome you, Dr. Abhishek Tiwari, sir. Now I feel proud to introduce Mr. Mayank Verma as a panelist. Mr. Mayank Verma is the CEO and co-founder of Curipshield, where he is building India's next generation post-quantum cybersecurity platform to secure enterprises, government organizations, telecom networks, financial institutions, and digital public infrastructure for the quantum era. He has extensive expertise in 4G, 5G, OpenStack. At Curipshield, he is spreading innovations in quantum safe migration, AI security, and multiple patent pending technologies, strengthening India's readiness for the post-quantum cybersecurity landscape. Welcome you, sir, Mr. Mayank Verma. Now it's my pleasure to introduce today's moderator of Fireside Chat, an accomplished quantum technology expert, researcher, and entrepreneur, Dr. Kumar Gautam. Dr. Kumar Gautam is the founder and president of QRACE Quantum Research and Center of Excellence, and the founder and director of eGreen Quanta, as well as a key partner at Innogress Ventures. His expertise spans quantum computing, quantum machine learning, and optimization algorithms. He actively leads industry collaborations to accelerate the adoption of quantum technologies and deep tech innovation in India. I welcome you, sir. Dr. Kumar Gautam, sir, as moderator for today's fireside chat. Over to you, Dr. Kumar Gautam, sir. Kumar Gautam, sir.
Yeah. Thank you so much, ma'am.
Thank you, sir.
Thank you so much, and thank you so much, Professor Singh, sir, Abhishek, sir, and Mayank, sir. So welcome to the quantum era in the quantum security particularly, and really it's a quantum technology. It's a very promising advance in computing communication these days, and not even the industry, the government, the entire world is basically looking to working on specifically the reason, the security side. So at the same time, this is a sufficient powerful quantum computer. Obviously, everybody is waiting for the FTQC based quantum computer, and which is really, it's a very majorly challenge. And thanks to Professor Singh, sir, it was really a very insightful your session, and This is really helpful for all the users also for taking the understanding of the, obviously one side is the photon generation or communication, and second side is basically the computing and cryptography side for the digital era or quantum era particularly. So this is very important sessions for understanding about this, the quantum hype and the reality. So first, sir, Professor Singh, sir, I'm asking just one questions. The first is, really the quantum computing is frequently, right now the people are describing the both revolutionary terms, the many protocols is already is going on. And some of the industry are recently I visited to some of the industry, the maritime, they are really, it's somehow they are not accepting the reality of that particular, the potential dangerous or not. So how much this the terminology is basically the realistic in the term technology progress, and how much is hype, means how it's both the sides, sir.
On there is some hype, like if you have industry, there will be hype. Okay, if industry is involved, otherwise they can't sell, they have to get investors, they have to market the products. So there will be some hype, certainly, if it is industry, associate industry is there. But quantum computing research is progressing very fast, and in India, industry doesn't invest in research, but if you see developed countries, Europe and USA and other countries, they invest heavily in research. Okay, this Google, IBM, they are private companies, they invest heavily, along with government institutions. Okay, there NSF, there is like DARPA, lot of funding, not just one agency. Okay, DAE, they are also Department of Electronics, so they invest heavily. So they are investing heavy, and things are moving very fast when it comes to at present is still the noisy intermediate scale quantum computer, but they are moving towards better and better error correction codes. Okay, earlier suppose this is physical qubits. Okay, and then for 1000 physical qubits you used to have one logical qubit, means the logical operation which you would want to do, like not operation, suppose you want to do. So is from 1000 qubit you can get only one qubit operation. Now it has reduced very fast, it's reducing. Now 100 qubit physical qubits, one can have one logical qubit. So things are moving very fast. And then with few thousands qubits, 3000, 5000 qubits, you can have very good codes which will give like sufficient power to quantum computer with those kind of error correction protocols. So people are expecting like quantum day when a good computer can break this RSA and all those things, 128 to 56 bit RSA thing, or that kind of bit, suppose. So it's not very far. Okay, it's not very far. Maybe 5 years or down the lane, it may be reality. And problem is that some countries, suppose developing, they will not tell you that they have like cracked your encryption scheme. Only after cracking they will inform. Okay, all the information is, so one has to start this quantum security right now. And quantum computing, some hype is there, but progress is pretty fast. So many private and government organization involved, and they're pumping a lot of money, human resources there, and there is no scientific like blockage. Scientific principle doesn't say that you can't achieve that. That's the best thing. So only this technological improvement, right? So it will be achieved. There is some hype, but it will be achieved maybe 5 to 7 years.
Right, sir. And nowadays the many industry has already adopted and trying to adopt also.
Yeah.
It's a really. So Abhishek sir, thank you so much, sir. This session, and lots of progress is already going by the CDAC, and you are already involving the many use cases particularly. And so this is very, I mean, for the user, they can understand about the what is the present day of the quantum computer. If you're talking about the, because the recently the CDAC Bangalore is just some updates, and they are signing in the many like outside the company. So what are they still unable to achieve, or what are that actually the CDAC is? I'm talking about the more concern about the CDAC prospect. What is the actual the view about this present day of the quantum computer? Actually, what will do that particularly, or what is exactly we are doing?
Sure. Yeah, good morning to all. Good morning, to Vinaji. So with respect to this, see, quantum computers, what CDEC actually is doing, mainly, we are working on a hybrid platform. So as everyone knows, whether we talk of quantum computer, but sooner or later, it is not a single computer which is going to do all the core tasks. Quantum computer is actually meant for some specialized tasks. So there has to be some computer. It may be a HPC, it may be a means high performance PC kind of thing, which is finally has to be connected to a supercomputer to offload the task. So that is one of the main thing in which CDEC is actually working, which actually is reality also. We are going to get a 108 Rigetti quantum computer in CDEC Bangalore soon, and that Rigetti system is going to be connected to our HPC infrastructure, so that we can offload the compute intensive tasks. So when we say what actually present day quantum computer do, see, scientific research with respect to physics, to protein folding, computational fluid dynamics and all, where a lot of metrics, multiplication is required, a lot of iterative kind of task is there, that surely we are going to offload there. And we have at present, with a basic study, some comparison with QPU and HPC has been already done by CDEC, which shows that these tasks are actually well meant for a QPU, and where we are going to get the benefit, that also is documented and tested on a simulator mode. So with respect to how much parameters is there, and with respect to how much memory or RAM is required, in these two areas there is a huge gain if we move for a quantum computer. And simulation is anyway a hybrid interface. So that always, whether it is a Quniverse or it is a FPGA based simulator which we have made, or which IBM is using, D-Wave is using, this all simulators or emulators on quantum computer is working on a hybrid framework. So that also is there in picture. And secondly, optimization. Wherever there is a optimization task going to come, where we are going to solve some factory related, whether it is related to supply chain or it is related to financial portfolios, these all are very good tasks where optimization is involved, and quantum computer is going to play a very major role. Yes, as this one day workshop is with respect to quantum security, so quantum safe cryptography is one of our very best use case for this, and CDEC is working on all three areas. But in the last, I just want to say one line, that hybrid framework is only the future in quantum computer which is going to happen. So wherever this facility is to be developed, it has to be in a hybrid itself. Standalone quantum computer will not be the full solution if someone is expecting that. Thank you.
Yes, sir. I agree with this, Abhishek, sir. Really, it should be start from the hybrid, and many organizations and industry is also trying to working on this hybrid mode and all. Sir, Abhishek, sir, actually these days the organization is overestimated immediately a capacity of the quantum computers, and while the underestimating the long-term security implementation. So my concern is also about, is there really this the organization has is somehow used high pressure on this to estimating the fix the the NIST and as well as the government of India is also working on, and Mayank Verma is one of the pioneer. He's also. So, sir, Professor, what exactly your overview is? Is really your organization is overestimated these days?
Organization is overestimated in the sense, this is not very clear-cut question. You talked of PQC and all those things. So why government is emphasizing on PQC? Because this is basically algorithm based, and you don't require very extensive hardware. Okay, so you can implement it with much less resources, with less expenses, and you can implement it all across the network very easily. While when it comes to quantum key distribution, you require a lot of hardware. Okay, you have to do the hardware upgrade, and more resources, more money is involved when you go for QKD. That's why government is going for PQC, and as I told, these quantum computers are going to be reality. So that's why they are planning to move faster. Okay, government is saying within 3 years you shift to PQC by 3 years. Okay. So that PQC means what is the estimate, whatever progress, it's just assumption ki whatever progress is being made in quantum computing. So at least 5 to 10 years, you will not have such a strong quantum computer which can break algorithm based PQC algorithm. Okay. That is again an algorithm and supposed to be very difficult to crack even by quantum computer. There is no proof, scientific proof, no physics-based proof or mathematical proof that they are secure against quantum computer. That's assumption. They are very hard to break. So, but based on that assumption, they are shifting to PQC. Okay. And because expenses are less, and that's why this 3 to 5 years you have to shift to PQC so that you are safe, even if some quantum computer is there, working quantum computer is there. So that's what. And quantum computing, more often they say that because we are aware of computation. Okay, everywhere you use a laptop, you use desktop, everything computation. So that's why people don't take the name of quantum computation sensing, because computer you're well aware, you know. So everybody does just quantum computer, but quantum computer means it's just one of the verticals of quantum technology. There are other verticals also. But since we are aware of computers, we are quantum computer. That's
right, sir. Yes, sir. So I agree. Sir, Meng, sir, you have a vast experience about from the industry to you are already running now, started the startup and got congratulations for the immediate recognitions after you started. So what are the application of the quantum technology are most likely to produce and practical benefit first in computing or in security? Like you are expert in the security, so I am the user or they are listening about the more concern about the security side. Sir, voice is not audible, sir.
Muted somehow, maybe.
Mute करिएगा तुम.
Still we can't hear him.
Sir, no, sir, no. You are not audible, sir.
Can I connect again?
Yes.
Now you are audible. It's okay. It's okay. Now you are audible. Yeah. Go ahead, please.
Yeah. The question is basically regarding the use cases of quantum in the form of security. Okay. Right. So as I've heard so many experts here, definitely the future is, as per Professor Dr. Abhishek is telling, the hybrid. Okay. First of all. Second, the use cases is definitely very high for the quantum computing, like as RP sir said, the quantum imagine. Okay. The protein synthesis. The use cases, just you have seen the use cases in the physics, the algorithm findings. But in the form of security, if you're talking about the security, is a very hype word. Okay. As per industry perspective, if I'm telling, the industry is looking just it isn't like a Y2K effect. Okay. Because the industry is looking for the immediate benefit. Right. The immediate benefit here, there is a two things. One is demand, another one is supply. We all are talking about the supply side. In industry, the demand is very low, very low. The regulations is definitely formed. Everybody, every regulators, other RBI, IRDA, TRAI, everybody is talking about the quantum security, PQC. Okay, they are busy in formulation of the documentation. This is not mandatory, right? So from demand side, there's very less demand in India. We need to generate the demand, whether in the form of, as one of industry expert, Mr. Pandit was telling, we have to some CSR type of things so that the demand should be generated. Once the demand should be generated, definitely the academia and all will integrate, right? To fulfill this demand. Demand is extreme. Okay, demand is the supreme, right? So in the near future, as RP sir said, the 4 to 5 years, it will take at least 4 to 5 years, even beyond that, to break the cryptography and make the some sense to industry come forward and doing some research, integrating with the academia, and pushing some value, some money to make the system.
Can I interrupt for a minute here?
Okay, sir.
When you talk of industry, I am really wondering why industries are not waking up. I get inquiries from Indra, Spain, okay, defense group. They get inquiry for entangled proton source, how I can secure. I get inquiry from Atlas Fabric. I get inquiries from like Italy, okay, I get inquiries from Romania. They want to have security. Till date, I have not received any inquiry from Indian industry.
Yes, sir. This is the
Not
same
a
thing.
single industry has approached.
Yes, sir. This
how
is the
we can
same
do.
thing. Even we are getting the inquiry.
Indian industry has to wake up. They are not
Yes, sir.
waking up.
The same
That's
thing,
a problem.
sir. Even we are getting the inquiry from Europe and US, but not a single inquiry from the India. This is the same. That's why I'm telling the demand and supply. There's no demand from India. We are talking to the supply, increasing some expanding on the university research or all, building some product. We already built the product, but we are waiting for the sandboxing. Okay. So we need some sandboxing to test the real scenario in the BFSI, in the defense, everywhere, the PQC applications, so that we can get a confidence whether this system is working on the industry setup, and this is crypto agile. How to make the crypto agile? Once you test the present solution with the legacy system, and then you can tell this system might become a crypto agile. Right.
Right.
Agree. Yeah. So you're right, and about that, what exactly the demand? RP Singh sir said that really it's very the big lab, and I visited to some of the maritime industry, and I like the Kandla port, and they showed that we are facing the security issue, RFID and all. So I already conveyed this information to Kandla port, even also the Ministry of Port and all. So you have many people, many industry and academia, they are working on this cyber.
I can't tell the name. Even I can't tell the name. The big university, big industry in India, the PSU, okay, in railway and all, they are deploying lots of things, but even 1 month engagement and convincing this is a new thing, you have to take care of the cryptographic security at the present stage and the initial stage, so that our system should be crypto agile in this manner, and we will be not going to be replaced and all within 2 to 5 years or 10 years. But still nothing from the industry side, just because the security is a freeway, okay, until this is auditable.
Right.
Okay. So once it will be auditable, then the market will generate.
Agree. So Abhishek sir, we discussed many times and about the threat, particularly for existing encryptions methods. So what is your view about that? Because this policymaker, you are also one of the policymaker and the industry leader to talking about so that listener can understand what type of threat and what really, if the quantum computer come into the picture, is really it's a breakable something, the existing encryptions method.
Yes. See, it is true actually, because means everyone knows how quantum algorithms, even this is a domain which has been quietly matured now. at least PQC, QKD, and this new NIST standards also has came now with Kyber and all other protocols, which actually is already proved that they have a capability of breaking the conventional, securities. Now, what policymakers has to do and how we should go ahead, that surely is required. So many industries, startups, even government research and development organizations are parallelly working in this domain. What I am feeling is a mismatch. There is an integrated thing which is getting mismatched. Like we should understand the difference between threat mitigation and how we can actually, what is the emerging sub solutions are there. So there should be a difference between threat and mitigation. That is not there. Like we know that we have a threat of breaking our RSA. Okay, but now how which quantum algorithms are best suited for this? And if I'm going for a real time quantum computer, what kind of physical qubits or logical qubits is required? What can be the length and width of the protocol? Those things still has to come up. And weaknesses we should know. In case of threats, what are the weaknesses? Actually, the core weaknesses in our conventional algorithm has to be known. Like every use case is not a quantum use case. So as far as, if I just say some financial sectors, now RBI is keenly looking for startups and even research and development organizations. They know that this is a threat which is coming out, how to mitigate it. So they are actually keenly looking for mitigation activities or mitigation framework for that, whether it is a PQC based, or it is a mesh based encryption, or it is a multivariate or univariate kind of, many ways are there which CDEC is also doing. And if I thought for post quantum, it can be lattice based, or it can be QD based. How it has to be done, that is actually required. So policymakers and government organization and even startup should first differentiate between threat mitigation and solution, and parallel work has to start in all three domains. What are the threats, how to mitigate that threat, first to know the ways to mitigate, and then solution. Like that, encrypted effort, integrated effort is required. So split wise we have done many things. C dot has proved, CDEC has proved, Chennai SETS has proved, and even startups like you people has also done a good work. But that integration approach is required. What I feel, there only the policy makers, government things comes to give an integrated solution actually. Thank you.
Yes. Yeah, I agree. Definitely, sir. You are writing the right and indicating the right point. What exactly about this industry leader and the policymaker about this, the hype of this, whether the breakable or not. So, Meng, sir, I am just asking about you are already associated with IT Kanpur, and now coming to the private organizations, specifically, I'm putting the word is the private organizations. Should all this many private organizations is now ready to invest? So I'm asking the two questions right now. One is, should the organization invest this right time? This is the quantum readiness, which is all you already claim, and you are working on the cryptographic protocol. Second is, because till now we don't have a full-fledged quantum computer. So how this your existing cryptography system can be actually fetched with the real-time quantum computer?
First of all, yeah, this is right time to invest, because you see the Infosys scenario, Sikka sir and Infosys, that was the right time once to invest the AI system. Now, this is the same thing here, the right time to invest in quantum, because if we don't want to miss the bus, we have to prepare our mind and integrate, as Abhishek sir said, we have to integrate efforts from industry, academia and all, okay, to prepare our own systems, okay, because definitely in the world, the supply chain constraint will come in the, because this is the quantum security. And at that time, we don't have the time to prepare, right? Your second question, what was the second question?
So I'm saying you already working and you are claiming some existing cryptographic system. How this cryptographic system can be fetched
Yes,
to
yes.
the quantum computer?
Definitely, this is the theoretical, this is the mathematical theories because and peer reviews based on the peer review and NEST criteria, these algorithm has approved, and definitely nobody is able to break it right now with the existing system. So these all are mathematical system. These all are proven by the mathematics as algorithm. Okay, we can't claim at we are going to break and check whether this is the new security and we have developed and we can have the proven system, something like that. So nobody claim it. Okay.
Right. You are right. Abhishek sir, I am just small curious about it. If you are supposed to be, I mean, talking about what technology breakthrough would be required before the quantum computer could break widely use the public key encryptions?
See, these are the final, use cases of quantum computers. Before that, I think whether it is India or abroad, everyone is struggling with basic functionalities of quantum computers. What are basic functionalities? What I am able to understand, converting physical qubits into logical qubits. Like, in any quantum computer, physical qubits, converting physical qubits to logical qubit is one of the biggest tasks. Then only we can talk of any real-time use case, whether it is finance sector or it is a CFD, computational fluid dynamics, or it is any use case related to this. So that in itself is a huge project, and that it itself requires a big control electronics. It is not a software work. A hardware design and development work also is going to come in this. So that is point number one. Second, as everyone knows, decoherence. Now, decoherence and getting these stable qubits for a very short time, like that superposition and entanglement features of quantum computing actually changes the state of the qubit. For that, what we do is the QEC. So everyone knows quantum error correction is again a big building block to convert a physical qubit into a good logical qubit. So these are the points where much work has not been done. A lot of talk on PQC, QAC, and other things are there, but these are the core of any quantum computers. And if we see the full stack of a real-time quantum computer, the control electronics is one of the core part which actually does these tasks. So QEC will also come into that, and then improving the connectivity. Like, we have a superconducting quantum computer. Someone has a neutral atom, someone has ion, trapped ion. How the qubits can be collected from different types of quantum computer to make a big logical computer hub, that also is very much required. So once we have this infrastructure, then we can surely go for breaking PQC or implementing any real-time use case. So these are the three building blocks based on my real-time things what I've understood.
Yes, sir. You are right, sir, and I agree with that. So you have to also explain. It's a very layman term. I mean, student and researcher are very time confused about this. The significant, particularly the word is the harvest now, decrypt later. So which encrypted information is collectively today for possible to descriptions or decryptions in the future?
So this is mainly this is a very important term nowadays. No, it is becoming a very big hype, which is, in short, it is called HNDL. No, so that surely is required for us to understand, and we need to mitigate this. Like, we need to see how organizations are going to mitigate this. For this, we need to adopt PQC framework, like these new NIST algorithms with the KEM and all, Kyber and DSA. They are actually made for secure asymmetric key exchange. This will actually help to mitigate this harvest now. So in starting itself, we need to adopt this framework, which is not fully quantum, but making us safe from post quantum kind of issues. And hybrid key exchange deployment is also one of the things which normally in classical also we do, but everyone is not doing this. So that also we should do, and we should actually work on this this HSM kind of framework. Nowadays a specialized hardware of HSM, which is known as hardware security module, it is coming chip based, it is coming PCI based, it is coming Ethernet based. These are the things which will, any hardware module will surely help us to save from any software threats, whether it is quantum also. So HSM kind of infrastructure we should move. These points what I'm telling, CDEC is already working and in a very advanced states. So with respect to this harvest now, decrypt later, these 3-4 points we should surely consider, and I'm sure it is going to work.
Yeah, so thank you so much. Really, you explained very later on to people can understand and to how actually the word is meaning. So Professor Singh, sir, I mean, you already explained about, and I saw your presentation, you mentioned symmetric and asymmetric and QKDs also. So as expert, you are one of the pioneer of this, the quantum computing domains or communication particularly. So how this is expert reliable for the cryptography relevant, the quantum computer, which is maybe available in the future or maybe in today, how you are actually thinking about, and which of the like a reliability, like a symmetric key method or asymmetric or QKD? What exactly your point of view?
So when you come to this quantum security, basically it is like QKD. Until date it is symmetric, but you can't say that it cannot be asymmetric. Somebody may come with some protocol which is like having asymmetric key distribution using quantum mechanical principles, but till date it is symmetric key distribution. So that's what quantum key distribution, and that's what provides security. As I told earlier also, PQC, there is nothing quantum, it's just an algorithm, another algorithm. Okay. There is no quantum mechanical principles involved. While QKD is based on quantum mechanical principles, it's future safe. Whatever be the status of quantum computers will remain safe. But PQC, you can't say that it will remain safe. It all your ingenuity. Okay. You can break. If you are some genius, mathematical genius comes, it can break. Okay. So that is the thing. And so till date, this new QKD protocol comes, which is asymmetric key distribution. It will remain symmetric. So till date, they are symmetric key distribution.
Yes, sir. And I agree with that also. So I am just one more thing. I mean, Abhishek sir said that hybrid methods is more, reliable for. So is it possible to merge with the ECC with any of the NIST protocol, whether it's the Kyber, HAS, DAS, or ISOGEN?
That I don't know how practical implementation will take place. Still, people are talking up what will be the practical, how to do that, because still most of the organization is just testing phase. Okay, how practical implementation will be done across the network, still it's not clear. Okay, whether how much hybrid, how much not hybrid, those things have to be worked out. People are talking of hybrid is very good, but you don't know how it will be implemented. Still, it has not been implemented in complete organization or network. So time will tell which will be better. I can't say right now.
So one more thing.
But to be very precise, very precise, I go and give lectures. Today I didn't emphasize. If it has to be practical, this quantum key distribution or secure quantum communication, it has to be global network. Okay. And this global network, it cannot be based on weak coherent pulses and all those things. Okay. It has to be entangled photons only. Okay? Because it has to be, you have to store the state, you have to retrieve the state. When you say weak coherent pulse, it's not very well defined state. Okay. It's a mixed state. Okay. And you can't store something not very well defined. You can't, how you are going to retrieve. You can't compare. So it has to be single photon based or entangled photon. Entangled photon based are much better for developing quantum internet, global quantum network, because you can have quantum teleportation and then swapping. That kind of protocol you can't have with single photons. So it has to be quantum entanglement-based quantum key distribution or quantum communication, which is going to prevail in coming years. Because if you want to have this global network, and just securing 2 points doesn't make sense. Okay, if you want to have practical utility, it has to be global secure network. Because if today I am in Ahmedabad, I may be there in Bhubaneswar, I may be there in Kolkata, I may be there in Bombay, I may be there in Berlin, I may be there in London. So within a month, okay. So people are mobile. So any strategic communication, you see our Prime Minister, Defense Minister, they're going all over the world. So if you want to have secure network, it has to be global to practicality, and that is not possible. What we are talking about is frequent pulse, QKD, and all those things. And frequency also, there is no surety how long it will remain secure. So those things have to be kept in mind. It's still a lot of work needs to be done. It's not like we have reached to the maturity and all those things. Okay, either quantum communication, quantum computing field is opening up. There is a lot of scope to work on. Okay, if we work properly, we can be a leader because field is opening up. It's still not mature. Okay, so a lot of work needs to be done. We are still very, very far behind. A lot of things have to come here.
Right, sir. So, just small suggestion from me. If suppose the organization is ready to adopt the quantum safe alternative or any like that. So, I mean, if suppose JSS is supposed to be there ready to. So, how you are supposed to be like, and just basic understanding to any of the university, where to start and how to start to set up the quantum safes?
Quantum safe, depending on resources available with you. Okay. If you don't have much resources, you go for PQC, okay, for immediate requirement. If you have resources, you develop this quantum key distribution system across your network in your campus. You can do as a test bed, okay. Because I am telling you again, this GSSS University also is connected to the network, okay. Their students, their faculties are moving around. So in the network, suppose you want to have 3-4 offices, you can develop this QKD, and then you can have secure command just for checking this test bed, okay, and not for any practical utility. Okay.
Right, sir. Yeah.
So depending on resources.
So, Mayank, yeah. So, Mayank, sir, could it migrate the PQC? I mean, people are talking about the realistic and when it will be the development. So what is your point of view? How much time it will take to develop the capable quantum computer and how it migrate the PQC? Your voice is not audible, sir. Mute.
Yeah, to develop the capable quantum computers, as RP sir said, 5 to 7 years, because the work is very, very high speed from 10,000 physical qubits to 100 physical qubits, and lots of algorithm is developing to how to error correction and all. So I can't say how much time it will take, but definitely this is the near future when quantum computers will be able to do this cryptographic breaking. Okay. The second thing, how much time it will take from migrating PQC and any organization, it depends on the how much legacy systems, how much legacy software they have, how much vendors they have. This is depends on the organization to organization. It's strength, its legacy systems. Okay, what type of software they are using, how much CBOM exposure they have. So because the hybrid PQC, if you're talking about the hybrid PQC, we are developing the hybrid PQC and crypto agile manner. What is the meaning of hybrid PQC? The classical and the latest one, the lattice-based PQC systems. Okay, but here we need to rigorous testing. Okay, because the key size is very high. So the hello message and handshaking is how much time it will take. So rigorous testing is required to make this crypto hybrid PQC industry ready. Second thing, the crypto agility. Okay, how much time it will take if any system, if any algorithm is going to break in near future, how much time it will take to replace the latest algorithm with the existing system. So changing in the legacy system, running system, because industries can bear the security lapses, but cannot bear the total collapse. Okay, so this is two things. Change requirement, say CR and patching in industry is very, very much efficient and very much sound. Okay, so industry need first the system should be validated in the lab, then their sandbox system, and then a small POC, then full migration, right? And this 4 stage take their own time, depends on the industry. Say BFSI and defense have a very huge ecosystem where multiple vendors doing the multiple things. Their systems have different cryptographic postures. So identify the postures, then creating the CBOM, then crypto agile migration. These all are a different thing, and it will take their own time, their own time frame. So there's no one word and one line to say which type of industry take how much time to migrate. That's why you have to start today to test, to identify the lapses, to migrate, and to then monitoring.
Right, sir. So has India begun identify the cryptographic systems or the protocols?
Yeah, in the RFCs, now the CBOM and HNDL is depicting in RFCs, but the awareness required at the higher level, because they are just mentioning the CBOM and HNDL, but they don't have the awareness about what is the meaning of this, right? Second, only putting in the RFCs, you have to start the POC itself. Okay, you have every industry, whether it is the government organization, BFSI, defense, telecom, they need to make their own sandboxing, right? To test the solutions.
Right.
Start, because I have engaged with the one of UK major bank, and they starting to testing the PQC solutions, hybrid solutions last year. Even we have contacted us and we have given the solution there last year. But in India, we need to galvanize the things at the CISO level, at the top level, so that they can start the things to understand what is the meaning of crypto agility, what is the meaning of migration, monitoring, these all things.
So if I'm asked to which sector should be prioritized first for the quantum risk, I mean, for the assessment?
Definitely, there's a two sector which need to be prioritized. One is defense, and second one is BFSI, because the transactions are definitely, though there is no HNDL effect right now, because the transaction is real time. Transactions real time to getting the data and making harvesting later, harvesting today and then decrypting later. No, there is no meaning at all. It means there is no economical meaning, okay, in the very precise way. But we have to secure our systems, because this is the economy is based on the trust, and if any lose in trust, we definitely have problem in BFSI. So first is BFSI, second one is defense.
Right. And already the RBI is also
and the government.
Yeah. Yes, sir. And RBI is already constituted the committee, and they are working on this the safe quantum particularly for this. Right.
Yeah, we already engaged with the IT wing of RBI.
Right, sir. Thank you, sir. So, sir, RP Singh, sir, how to right now to prepare the India to protect the digital infrastructure against the future quantum-enabled cyber threat, which is basically China is always, and people are many times confused about what type of attacks and so on, or quantum attacks particularly. How the India is now ready to? What is your point of view for?
India is getting ready, and right now we don't see any worthwhile quantum attack happening. As unless until you have good quantum computer, you can't have any this quantum attack happening. There is no point. So so India is making good progress, and we are not very far behind. And then this PQC. Here, this Mayank Verma ji is here. So, as far as I understand what is happening in PQC, if you read the NST documents, because they have only standardized and all, only one particular implementation, and which is from IBM, that is supposed to be secure. NST says that implementation by IBM, which is a proprietary item, that is only secure. Whether other implementations are secure or not, NST doesn't guarantee. So I don't know how this PQC, either it is going to be IBM only doing implementation, or they will be giving petty contract to other bodies and all. How it's going to be done in PQC, that I'm not clear, and I'm not algorithmic guy and the software thing. I am basically QKD and all. We do experiments, real experiments. So that part is not clear to me how it is going to happen. And near future, it has to be PQC only. You can't have such a huge resource, at least in India, so that you can just in 3 years you can have QKD and all those things.
Right. So many researchers and young mind is right now working on this the cyber side and PQC side. So what are your suggestions? How any like a researcher can actually develop a indigenous quantum hardware or software for this for the cryptographic solutions? I mean, this is the very basic suggestion to advanced level.
Anything, suppose you want to develop, it has to be standardized and it should be approved by like International Telecom Union, ITU, or European agency. It has to be standardized and approved by. It has to be a global acceptance, because you're integrated globally. You can't be aloof, okay, cut off from the other. Okay, this internet is. So it has to be approved. Anything you develop, it has to be approved. So a lot of hard work is required if you want to have like implement in the network. Okay. Testbed is fine, sandbox is fine, but if you want to implement in the network, it has to be standardized, it has to be approved by ITU and other agencies so that it has global acceptance. So NST has global acceptance same way, whether you develop something, suppose, whether it will have global acceptance, ITU will not agree with that. Okay. So those kind of tricky issues are there. It has to be sorted out. Okay. So those problems will come certainly when it comes to like when you develop.
So any Indian agency, any Indian agency is all there who can actually verify or certify it for this?
SETS is there. SETS Chennai is there. They are for basically Society for Electronic Transaction Security and all. Then they are working along with CDAT and all. So they are there. But there also, I go there because being advisory board member of SETS. So there also, it's not clear how it will be done. Like it's IBM thing.
It's a mute, sir.
Mute, sir.
Mute, sir.
Got muted in between. So I was telling ki there also it's not clear whether it will be just one implementation, IBM implementation will be taken, or their implementation is as good as NST. So these things are not clear. Only top like guys, technocrats, PS and others like they can decide how to go about it when it comes to the migration to PQC.
Right. Thank you, sir. Abhishek, sir, it's a very famous questions, and even the global and India is also looking. What role should be the International Quantum Mission play in the strengthening of the India's safe quantum or Indian security of the preparedness?
Yes, actually, it is very common question, and I think our answers are also very common. So as based on this communication, know what we have this all chat. There should be a structured approach, which I was trying to tell. Like in case of post quantum cryptography, which is a stable domain now, a lot of things are there. But how can we have a framework, a documented framework with respect to threat, with respect to mitigation, and with respect to solution? Like, can we have an integrated framework that their NQM has to play the role? because for a problem statement, funding has been given to many. Many institute also is working on PQC, many startup are also working on PQC, and many research and development organization is also working on PQC. But what are the solution wise? Can we have a benchmarking, or can we segregate it based on threat, mitigation, and solution? Then we can say that in PQC at least we have this solution now. If there are any gaps, the funding and support can be given based on those gaps. It may be algorithm wise also, because if you see, many people are working on Kyber and all those things. But as you asked a very good question, that how ECC and QKD is going to merge, like that kind of solutions, I'm not sure still a very serious solution is there. Okay, so that also, those type of gaps has to be found out, and funding has to be given based on that, instead of duplicating the funding and duplicating the solution, which will not give us a mileage. That is one. Second, indigenous quantum communication hardware. Like now, a lot of things of PQC, QKD, stack, and all those things are there. But do we have any end-to-end hardware? Like just take an example, CDOT has made many things in quantum communication hardware-wise. But at present, CDOT is one and only one, government organization where a good tabletop kind of solutions are there. I am not sure if they are commercially used solutions. That also we need. So on hardware, we should move to the domain which is stable now. Quantum communication is quite stable. Now we should go hardware wise. We should also explore if any specialized QPU or chip is required. Okay, so that we are not only a software providing nation, we should have end-to-end solution. That is one. And nurturing the startup is still much more required. See, we give a seed funding, and then whether their technologies are going to market or not, it is very tough for these startups to get an end user. Okay, getting a fund from government was one of the biggest bottleneck, that somehow at least some breakthrough is there because of NQN. Now, if a technology is made, end user is required. Like you actually, Gautam ji is working with such a specialized solution with Indian Navy, ports, and all. Now you got an end user. Once you get an end user, then you develop and deploy. That approach is totally different. Instead of just getting a funding and using it, keeping in your lab. So end user is the area where NQM and team and government should focus, find out the end user and allocate it to startup. These are not the tasks which a startup should do. I think I will not take much time. I have already put my points.
Yeah, sir. So continue the same. Again, I'm putting another questions. Many times the university, startups, and small industry, they're confused about that, or maybe they have no clear about how they will collaborate with CDAC. Particularly, I'm specific for the CDAC. How CDAC is looking for this, and what are the adequate things or platforms they can able, or they can get that, or they can associate with this.
Yes, so this I will continue with my last thing. Like for us also, we develop quantum technologies to a lab level. However, seeing the outside environment, government is asking CDAC also to go commercial. But as per any bylaws and all, we are a research and development organization. We develop technologies, give it to startups to finally deploy, update, make it more sophisticated and sell. So that is one mode which can still be used, like our quantum simulators, whether it is a Quniverse or CDAC Noida has also made a state-of-art FPGA based simulator which doesn't use any GPU. Okay, so this solution is also done now. Everything is working in the lab level, but now we are in another project, because once one project in quantum ends, government gives us another task, and both are not interconnected. So that domain is completed. Now we are working on some domain. Now we need someone to take that solution, put it to universities, give it to scientific fraternity colleges, so that they can learn more from them, they can implement algorithms. So that is TOT is one of the mode which surely, and in collaborations, any startup and CDEC can complement each other. If there are some call for proposals, like ANRF is nowadays having startup research and development and institutional call, there we can sit together, divide our work, divide funding, and we can work together. So those things are also there. Thank you.
Right. And I know that the Abhishek sir is very open about this. If you have an idea, they're always ready to and welcoming to all this the idea. Sir, Meng sir, this is the one. Another question is about the regulatory and policy. How the intervention should be required to ensure that smaller organizations.
Yes, definitely. This is a very good question. Regulatory and policy. Right. As you know, the DSCI has released their report, and task force under DST also released the regulatory some regulations. Okay, this document is very comprehensive. This document is very comprehensive, divided in L1 to L4, divided the classifications of the industry, the timeline, everything is placed in India. There's no issue at all. Now we have to, again, we have to centralize the industry. They generate some work. Okay, as Abhishek sir told, they have developed the technology. Startup also developed the technology. CDOT developed the technology. But you look the QNU, the same technology have developed and get the market from the defense, though it is government due to government bindings, and now they have capacity to export the solutions, right? Here also for PQC, for crypto agility, for all this, we need to set the timeline and audit so that the market will generate, and these all academia, industry, and technology development players like CDAT will club together to make the foolproof solution. Okay, not a single person can develop the end-to-end solution. We have to integrate. We have to integrate, collaborate to make the solution industry ready. Right.
Yeah. Okay, sir. Really. Thank you so much, sir. And now I'll start the rapid fire. I will ask to each panelist 2 questions, and this is one-line statement. No need to explain. Already you explained everything about that. So the first, Meng sir, the most quantum security myth, if you are supposed to be, you are putting this, the one line. The biggest quantum myth is
basically a myth. I could say the it's going to be break.
You can put it in terms of the PQC.
HNDL, something like that. Okay, it's hype, not a myth, but hype.
Right. And most underestimated quantum risk.
We are safe.
Yeah, thank you. So, Abhishek sir, it's a 2 question for your side. The most important capability the India currently lack. Abhishek sir. Abhishek sir, are you there? Meng sir, you will take this question.
I'm sorry, I just got a call.
Okay,
yes.
sorry.
Sorry.
Okay, no, sorry, sir. Okay. So, most important capability India currently lack. This is a rapid fire, one-line statement just.
Capability with respect to quantum actually.
Indian currently lack. Yes. Where we are lacking.
Yes. We are, as I told you, we are still lacking in a full stack solution. Things are being developed in bits and pieces. Someone is working on algorithm, someone is working on simulator, someone tries to replicate a quantum computer. But how the full chain is starting from a dilution refrigerator to control electronics to QPU, if I talk in a hardware way, that is missing. Number one. If I talk for a quantum communication, we have developed many algorithms. But again, the full framework with respect to use cases and hardware wise, we are missing. So Like if you take an example of NVIDIA develops multiple libraries. Even IBM has developed multiple libraries for simulation. They have their own kernel. They have their own backend C++ file. They have their own UI. They have developed their own gates also. Now what we are doing, we are using all those things to develop an application. Then what again? So nothing is full stack we don't own. Like I will give you my example. As I told you, we have developed a FPGA based simulator without using any GPU, anything. Like without using any foreign hardware. As you know, FPGAs are a reconfigurable hardware. Whatever you put, the IP and hardware becomes your own. So their full end-to-end stack is there, starting from the kernel files, starting from compiler, transpiler, UI, application, even framing of gates and APIs, everything. So that integration is required. Working in bits and pieces will only make us again solution, but not a full stack solution. Thank you.
So you already said that the end user, if you have, so I am asking the one line statement, which sector is right now to suggest to all the participant to choose or start the immediate?
End user, now again, it depends on, domain. If I talk of end user with respect to quantum, you have already tapped the
PQC side or CQC side.
Whether it is PQC or any, you have already tapped the very good end user. You are working with ports. See, these ports are for supply chain, portfolio management, all those route optimization, everything. Multiple solutions are there with these ports and all. So they are one of the end user. This solution is already there. So defense is always a very good end user. If a new technology comes, the defense is in. With respect to bank, I will say RBI is one of when we talk of quantum security, RBI is one of the best. Not directly the banks, because SBI and all these banks have a lot of integrators and aggregators in between. They don't own the technology, they are outsourcing everything. It is always better to go to Reserve Bank of India, because they are only in enforcing. So RBI is one of the good end user if you go for five financial things. Thank you.
Thank you so much, and thank you so much all the expert. It was a very insightful interactions on, and you explained very well about the every prospect. So I will take some question from the participants. So if you have any question, please open, just unmute and ask, please.
Any questions from the audiences?
Your
Any question?
The voice is not audible, so loud, please.
Any question from audience?
Yeah. Any question from the audience, please ask to Mayank sir, Abhishek sir, and Aspi Singh sir. Or anybody want to collaborate, how to collaborate with these all the people are very big and they are doing on the big organizations.
Yes, sir, I do have a question. It is an open question from everyone. Whoever so can answer it may answer. Me being a student and getting into or venturing into this field of quantum physics or computing, which is very uncertain, to be honest. In next 5 years, what would be the normal users demand, like if quantum is applied in every field? So how could I prepare myself as a student to be ready for the upcoming demands of the community in next 5 years? Because at this point, venturing into this field, investing my time comes with a very high risk of uncertainty. So that's my point. If even I start my stepping stones at this point, at this age, I don't know in next 5 years, maybe it would reach that point that it requires my skill or experience. I'm just asking how to deal with this uncertainty of whether it is going to be a successful venture for myself to invest my time in it or not.
Yeah, Krishna. Anyone, please just take this question. Yeah, Mayank sir.
Hello, can I take this question?
Yes, please, sir.
Yes. Yeah, the question is very, very right, because quantum itself uncertain to making the certain things from uncertain. So if you are talking about the future, so definitely I'd say you should go with integration of quantum and machine learning. Okay, because the use cases is very huge. Whatever the AI and normal systems cannot do, the QML can. I'm not telling the right with the formation. Okay, the can be do. So the use case is very high, from pharma to defense to supply chain to physics, everywhere. So you should collaborate and combine the AI knowledge and quantum knowledge to make your career. This is my advice as a starting point.
Right, sir. Main sir, and really, Krishna, it's not, don't be scared about that where the opportunity, it's not. You have to invest your time on quantum and somehow is too. It's a very highly demandable sector, and startups, all the startups are looking the young mind, and really they have also facing this talent. So don't be scared. It will change. We people all are living in the quantum era, and definitely we'll do that.
Thank you, sir.
Sir, one question from my side, if you allow, sir.
Yeah, please, ma'am.
Yes, please.
Yeah, actually, sir, our motto of having this summit is that we want to have the ecosystem of quantum technology in our campus. So, what should be the first and foremost step that we should follow for having, like, we want to have the minor courses in quantum, we want to have the MTech courses in quantum. What will be the prerequisite of that? Means we are having the BTech in electronics and communication, we have the BTech in CSE. Now what should we do for having the something we know we want to start in the quantum? So how should we proceed for that?
Yes, sir. Abhishek, sir, you have to, if possible, you can explain, please.
Okay. Ma'am, it is a good question. See, so the domains in which BTech is already going on in college, they are very good and very much sufficient to start any quantum. So nowadays in BTech, whether it is a final semester or final year, we are having minor and major kind of things. It is everywhere. At least in semiconductor and quantum, these are two domains which AICT is pushing very hard. Okay, so many colleges have specialized or full-time courses on quantum and semiconductor also, but in starting it is not allowed because the market is just growing, and we can have a good major and minor selectable subjects for the last year, like whether it is BTech CSC is one of the best suited domain for quantum, who has the core specialization in AIML. So what I feel is best suited, because they will be suited for quantum machine learning also and for quantum application also. And going down the line, the other, see, as I always told, that we have to put parallel efforts to develop our strength in not only the software but hardware solutions also. So your BTech EC and triple domains now QPU, quantum processor unit or quantum processor chip, is also one of the very required things which actually country needs now. If not now, after 4 years and 5 years, we need it. We should start from now, else again we will be the same semiconductor issue will come, which is at present going in country. Like now we are putting our fabs when already 5 nanometer chips are there in market. We are still working on 189 nanometer. So you can surely start good course. We can suggest the syllabus or modules and all that can be done for sure parallelly in quantum CSC and AIML, which will lead to quantum application and quantum use cases, including quantum communication also, and your hardware domain of triple E and EC. If you have VLSI too, they can work on control electronics and FPGA based solutions, because any chip cannot be developed directly. First, we have to test it on some prototype hardware, and that is always FPGA, whether it is a classical or it is quantum. Because we are doing it. We have already done a lot of things on that. So these two courses you should surely start from now itself. Start thinking what modules are there. We can formally help you to do that. So I think that will surely make JSS a different institution compared to all, because that uniqueness in BTech courses can be done. And with such a startups there in country, in quantum, VLSI and all, I am sure your manpower will get good placement. There is no doubt. Thank you.
Thank you, sir.
Thank you,
very
sir.
much.
I express my sincere thanks to our esteemed panelist, Dr. Abhishek Tiwari sir, Mr. Mayank Verma, Professor R.P. Singh sir, for their engaging discussion.
Ma'am, your voice is quite low.
Okay, just a minute. No, it is. It's full. Mr. Mayank Verma, Professor R.P. Singh, for their engaging discussion and for sharing diverse perspective on the future of research, innovation, and industry collaboration in domain of quantum security. Thank you very much, sir. Thank you, Dr. Gautam, sir, for such an insightful and engaging fireside chat session with a spotlight on readiness of India for the quantum security era, the preparedness of the government and industry initiatives to build a secure and quantum resilient digital ecosystem. Thank you very much to you all. This discussion has clearly demonstrated how quantum technologies are moving beyond research laboratories to address real-world industrial challenges. Thank you to you all. Now we continue with our next session for the industry use cases with Dr. Gautam sir and Mr. Mayank Verma. Should we continue, sir? Or we take a lunch break for the 15 minutes?
Take a break, sir.
Take a break? Okay, sir. So we take, this is 2:35. We meet again at 3 p.m.
Sir, I think Dr. Kumar Gautam will leave he is having one urgent meeting, so he will not be able to give the talk. So we are having the talk of Dr. Mayank Verma only. So,
Okay.
So
So
after,
for that we meet at 3 p.m.
3 p.m. Okay, ma'am.
All
Yeah,
meet.
we'll meet at 3 p.m. for Mayank Verma's sir talk. Thank you.
Okay, sir. Thank you very much. Thank you.
Attending.
Hello.
Hello.
Sir, shall we start?
Yes, we can start.
Yes, sir. Sir, just a minute, sir.
Yes. So,
Sir, just a minute.
good
Sir.
afternoon. Yes, shall we start now?
Yes, sir. 1 minute.
Your volume is very low.
We now begin our industry use case spotlight and warmly invite Mr. Mayank Verma, sir, CEO and co-founder of CryptShield, to share their insight on real-world application of quantum technologies. Our expert need no further introduction, as we have the privilege of interacting with him during the previous session. We are delighted to have him continue with us for this segment. Now I welcome you, sir.
Thank you. Thank you very much, sir. Basically, This PPT is based on the huge cases of quantum cryptography, PQC applications, right, in the various industry. Because my company working on the post-quantum cryptography, that's why this PPT is only confined to explain the security area and its business cases and the market. So, you know, the encryption is the last line of defense and it's invisible. Presently in the industry, no cryptographic visibility, what type of cryptography they are using. In the SBOM, there's some paper is going on in the mention some TLS 1.3, 1.2, but nobody's known whether the downgrade attack is happening or not, whether actually this version is using in the system or not. So, you know, the classical cryptography is just a minute, please. Vulnerable, and most important, HNDL. HNDL means harvest today and decrypt later. Okay, harvest now and decrypt later. Right. It means the adversaries are harvesting your data, and once they will be capable to decrypt it, they will decrypt and expose your data to the world. It might be defense data, it might be telecom data, it might be any personal data of higher authorities. So this is the problem. This is the timeline. The quantum aggression clock has started. Just for a quick review, the market, and then I'll cover the use cases. The market is very growing. Okay, the global PQC market 2025 to 2033, 1.58 billion to 29 billion as per international agencies, Grandview Research. Its CAGR is 37.8, but multiple research have multiple market agencies have displayed the CAGR is 38% to 61%. And India, it might be after 1 to 2 years, it will grow more than 61%. Okay. The target verticals in India is BFSI, telecom, government, and PSUs. I'll explain the use cases: defense, healthcare, and secure satellite communication. So, my full screen is visible?
Yes, sir. Yes, sir, it is visible, sir.
Yes.
Yes, sir, it is visible, sir.
Okay, okay. So, the use cases of telecom, the cybersecurity. Right. I can here in this PPT, I explain the worldwide operator progress and business generation with the PQC and where India is right now. The pioneer live development deployment is SK Telecom, South Korea, BT Group, UK, European and Middle East leaders like Orange, Desktop Telecom, Esitlat. These all they already developed and deployed the PQC system. But in India, you can see here the Reliance Jio and Airtel, they are planning. So there's a huge business in telecom domain for the PQC and security, quantum security, right? Moving to next use case, government and public infrastructure. You know, the government have the massive, especially in India, the massive database of Aadhaar holders, ABHA, something ABHA, digital cards, digital, say, DigiLockers, huge data centers of the government data. So these all infrastructure need in future the post-quantum cryptography, QKDs, all are cryptography, quantum cryptography need to be placed in these public infra like Aadhaar, UPI, PKI, NIC, e-governance networks, digital rupees. You know, the RBI is planning to make a CBCD, digital rupees. So without quantum cryptography, you cannot imagine the digital rupees, land records, and DigiLockers. You know, the even the PQC is going to be implemented in the blockchains. So blockchain also need PQC type of thing, security. So, and recommended product, if you say the products, PQC network, as Abhishek sir was telling, the HSM hardware security modules. So PQC network HSM, PQC smart card, PQC TLS accelerator, PQC USB tokens, and TPM 2.0 modules like your ATMs, like your passport. These all need in future the PQC enabled security chips, and PQC enabled the softwares. Defense and strategy system. This calculation, the business calculation say 6.2 billion. These all are from the internet data, CIPRI ARMS DB 2024, and the calculation is based on the total value, total business of defense, 7 to 12% of this business going for the security. So the calculation is based on this total value. The total business is coming is 1300 CR in defense sector from the security perspective. So the huge cases of security, post-quantum cryptographic security, high security links, authentication, tactical battlefield communication, satellite communication, drone and UAV swarm authentication. As CDAC person was telling, they are using QKD for the drone. So you can use the QKD, PQC all in drone communication. Okay, drone authentication and swarm authentication. Say making a mess of the swarm of the drone and communicating a secure communication between the drones and the ground station. Now here, here also the HSM required, but this HSM is different. This is a military grade PQC HSM, PQC secure radio, SDR, PQC RFID asset tag, lightweight drone chips, PQC COMSIC module, communication security module. So these all hardware need to be developed in near future for cryptographic, quantum cryptographic security solutions. If you see the telecom domain, 5G, 6G, ad hoc networks, and isolated networks. So lots of huge cases here. 6G physical layer security. You know, now the 5G are beyond 4G. These are stack-based solutions. They are communicating to each other by the APIs. So the layer to layer, the security between 6G one layer to second layer need to be quantum safe. So PQC for ultra low latency 6G RANs aligned with the ITU-MTU 2030 framework. So here every security needs need to be fulfilled by the post-quantum cryptography. Whether it is software based or any hardware oscillator required, you have to develop the hardware oscillators. So that's why here the recommended PQC products which need to be developed are we have to, Indian industry have to purchase or need to be developed in India. The PQC network HSM, PQC IPsec VPN gateway, PQC TLS accelerator and IC cards, and 5G SoC cores. So definitely the near in coming time, the security quantum applications going to be increased with a CAGR 60, more than 61%, might be double in a year. So business is very huge. In BFSI, banking, financial services, and insurance, you know, the UPI value in January 2026, 23 lakhs crore transaction in a month. This is the NPCI monthly statistics. We have to safeguard with software and with hardware to these transactions. So India, you know, the UPI is a very huge infrastructure created and deployed and used by Indian population. So we have to secure this type of public infra. And to securing this public infra, you need to be first you need to be develop the quantum secure solutions. In India, presently 257,000 ATMs as per RBI handbooks deployed. We have to secure all our transactions from the ATMs. So there is a huge market only in India. I'm talking to only in India. I'm not talking the world around. So, right. Now come to critical infrastructure, CII, OT and IoT, edge devices. There is a 250 million, 25 crore smart meters proposed to be implemented, deployed in up to 2027 by Government of India. This proposal is already floated by the Government of India. If you see, if there is a single chip required to secure the R smart meter, the PQC, we need 250 million chips only for self-consumption. We have already 24,000 kilometer ATP railway, right? RFID tags in the railway. If we need to update, we have a huge business from the railway itself. So this is the coverage. Oil and gas, SCADA, nuclear, instrumentation, these all setup need quantum security. If you see the healthcare and medical devices, healthcare, ICU, life care devices, hospital networks, implementable device security, these all need cryptographic, enhanced cryptographic quantum security in near future. Its value come to something 3,000 CR in India based on the reports, FICCI Health Sector Reports 2024. I have calculated with the 7% security hardware share. If calculate only 7%, the whole market, whole business, 7% of this business, it coming around 3,000 crores. So hospital networks and medical devices also have the market. This is total calculation based on the reports. PQC ASIC hardware's market is 22.7 billion approx. Crypto agile migration services, BFSI and all is 2.4 to 4.6 billion. Certificate lifecycle management means PKI, okay, quantum hybrid cryptography based PKI monitoring 9.5 to 11 billion, and quantum communication and satellite communication QKT systems $5.5 billion. So there is a huge market in India itself. What we are offering, a quick summary, what we are offering, the discovery asset, discovery, accessing, migration, migrate and monitor. It means there is a 4-phase to identify your loopholes. First, to discover what is going on in your system, in your industry, to discover the things, discover cryptographic posture, then assessing what to be changed and what to not to be changed right now. So assessing the your readiness, your benchmarking. Then after 1 year, it will take 1 to 1.5 years to assess, discover, and getting approval. Then migrate from classical cryptography to post-quantum cryptography. And after migration, after 2 to 3 years, you have to audit yearly. So monitoring the things, whether the cryptography is actually quantum safe or not. Is there any downgrade attack? Downgrade attack means your vendor or your partner downgrading your configuration, and it might exposing your system to the internet for attacks. So I'm skipping these all things because this is our product overview. Thank you very much. This is the use cases of quantum cryptography and business, whatever I have explained. If you have any question, please.
Sir, I have one question.
Okay.
Actually, Sir, actually, I just want to know that since we are the faculty here, so what quantum teaching strategy we must, apply? Can you just suggest that? Because these use
We
cases we
already
have.
engaged with UP Forensic Science Institute, Lucknow, to
Yes.
guiding them to make a say elective subject.
Right.
Okay, quantum security. So there is a two thing. For CS background, for electronics background, lots of IITs already started based on the professor interest, hardware development and software development. Okay, so there's a in software development post quantum cryptography, QML. Two things is very important. For hardware development, as Dr. Abhishek was telling, hardware development from end to end, FPGA based. Okay, there are lots of COTS product available where we can develop the things and test. Okay, so from here we can start developing, and there should be interdisciplinary, say mechanical student collaborate with the electronics student to understand the what exactly the product should be. Not only developing the things, what exactly products should be. You need some insight from the mechanical also. So mechanical, computer science, electronics, electrical, they can club together and start QML, post quantum cryptography, right? This say development of say benchmarking of the algorithm based on the available COTS products, right? FPGA boards. So from here we can start.
Thank you, sir. Thank you, sir.
Thank you. Thank you very much.
Thank you, sir, for such an insightful and engaging industry use case spotlight talk. I would now invite Dr. Aanchal, Assistant Professor, Department of ECE, to introduce our next distinguished experts. Over to you, Aanchal.
Thank you, sir. Good afternoon to everyone. I welcome you all to the panel discussion of today's summit. It is my pleasure to invite our moderator, Dr. Anirban Bhattacharya ji, Assistant Professor at SVNIT Surat, whose research focuses on quantum circuit design, reversible circuit testing, and quantum machine learning. Joining him on the panel is Professor Pelli Subhakar, sir. He is a distinguished academician and professor at Department of Computer Science and Engineering, MNIT Jaipur. With over 25 years of experience in teaching, research, and academic leadership, sir has published over 120 research papers and supervised numerous PhD scholars. We also have our next expert, Nikhil Mitalia, who is a technology leader and innovator working at the intersection of quantum technology, advanced electronics, and next-generation systems engineering. With a strong background in translating deep technical concepts into real-world applications, he has been actively involved in enabling cutting-edge research through high-performance signal generation, control, and measurement solutions. We are also delighted to welcome back Professor Ajay Singh, who is ex-HCL and quantum technology expert. So now, without further delay, I invite Dr. Anirban Bhattacharya ji to take over other proceedings and lead the panel discussion. Over to you, sir. Dr. Anirban Bhattacharya ji. Sir, are you there?
Dr. Anirban Bhattacharya, sir. Just make it available, just wait.
I will call him.
Yes,
Gayatri, ma'am, you are muted. I think you are saying something.
Yeah, I'm calling him. Okay. He's not here, no?
Yes, yes, ma'am.
Okay, I'll call. He is not picking up the phone. So what we can do, just we'll wait for a few minutes, and then after that, what we can do, Achal can take the questions. She can be the moderator for the session.
Okay. The questions that already shared with you.
To Achal. Just wait for 5 minutes, na? If he can come, then it will be better for us. Huh?
We'll wait, ma'am.
He will be joining in another 2 minutes. Actually, the time is 3:30, so he is now it is around 3:25, right? So in another 5 minutes, he will be joining.
Yes, ma'am. We'll wait, ma'am.
Yeah, another 5 minutes he will be joining.
Sure, ma'am.
Hello, ma'am.
Hello, sir.
Yes.
Sir, shall we start? Good evening, Bhattacharya sir. Hello, sir, shall we start?
Sir, are we audible?
Yes. Rajesh, if you can wait me.
I'm calling.
It is not muted, I suppose. No. Sir, you're not muted, sir. So kindly unmute yourself.
Yeah, hi, this is Nikhil.
Monica ma'am, he will rejoin.
Okay, ma'am.
Shubhankar sir is with us. Nikhil sir is also here. Shubhankar sir is here. And Dr. Arniban, he will join in a moment. And one more person was there, no?
Ajay Singh, sir. Professor
Ah,
Ajay Singh.
Professor Ajay Singh, he will be joining shortly.
Okay, ma'am.
I'm already there.
Okay, sir is there already. Sir is there.
Hello, ma'am.
Yes, sir. Yes, sir. You're audible, sir, now. Sir, we can start, sir.
Monica ma'am, we have
Yes, ma'am.
shared the latest profile of Professor Ajay. Please, you can read
Okay.
once.
Okay, fine.
I welcome you all. So I welcome one of our panelists, Professor Ajay Singh. So Professor Ajay Singh is a globally recognized thought leader in cybersecurity, quantum computing, AI, and digital transformation with over 40 years of experience in the IT industry. A former CEO of an award-winning fintech company, he is a certified corporate director and fellow of Institute of Directors. He serves as corporate advisor and mentor to organizations worldwide, and since 2019 has been a visiting professor at leading management institutes, appointed Professor of Practice in 2024. He is also the editor of QDayReady.com, a portal dedicated to advancing awareness of quantum-safe systems. A prolific author and a sought-after speaker, his forthcoming book, Cyberstorm, Unleashing the Power of Quantum Computing and AI, has just been published by Universities Press, Orient Black Swan. Professor Singh is a member of India's National Quantum Mission Task Force, the Academy Advisor Board of Pace University, New York, and the IEEE Committee on Cybersecurity for Next Generation Connectivity Systems. Welcome to you, sir.
Thank you.
Over to you, sir, Dr. Anirban Bhattacharya ji.
Okay, ma'am.
And I request you to lead the panel discussion. Thank you, sir.
Okay. So the theme for today's right now panel discussion is building a quantum safe ecosystem, policy, industry, and academia. So we know that quantum technologies are rapidly moving from scientific exploration to real world application, with the potential to reshape computing, secure communications in the different sectors like healthcare, finance, defense, and critical infrastructure. Their impact could be as transformative as previous technological revolutions, creating new opportunities for innovations, economic growth, and national competitiveness. So at the same time, advances in quantum computing present important cybersecurity considerations. As quantum capabilities mature, they may eventually be able to break many of the public key cryptographic systems that are currently underpin digital trust, secure communication, and sensitive data protection. Responding to this emerging landscape requires a comprehensive approach. Beyond advancing quantum computing itself, nations must invest in post-quantum cryptography, resilient communication networks, research and testing infrastructure, skilled talent, supportive policy frameworks, and strong collaboration across government, industry, academia, and the research community. So this panel discussion explores how we can prepare for the quantum era while ensuring that innovation and security progress together. So my first question that is on building related to that is building a quantum safe ecosystem. So my first question will be to Ajay sir, that is, what actually does a quantum safe ecosystem mean in practical terms, and where does India currently stand in building such an ecosystem?
You are on mute, sir.
Good afternoon, Dr. Bhattacharya. Good afternoon to distinguished panelists and participants. It's a very important question that you asked me to decode what is a quantum safe ecosystem. So let me dwell on the word safe. What is quantum safe? Why are we worried about quantum safety? You just mentioned about how encryption can be broken by a significantly powerful quantum computer, and therefore the data that we so carefully preserve, so carefully encrypt and save, which is the backbone of our digital economy, digital systems, digital defenses, is at risk. So what is at risk? If we break it down further, there is data at rest, which is the data that we have accumulated over the years. There is data in motion, and there is data in use. Data in motion is typically what moves over the internet. And data in use is the data that is used by applications. Now, all three, if encryption is broken, all three are at risk. So what can we do about it? We have to secure our data, because everybody from an individual level to an organization level to a government level two issues of national security. Everybody is going to be impacted if encryption is broken. So therefore, the whole idea of migrating to a post-quantum cryptography era is about migrating your data at rest primarily, so that your data is secure and is safe from a quantum attack at a later date. It's not going to happen today, but it will happen when there is a significantly powerful quantum computer. Second, data in motion. That is where your QKD comes in, where your key exchanges are involved, where digital signatures are involved, where messages are involved. That is where QKD comes in. It secures your data and makes it quantum safe while data is in motion. The last and the most difficult, and perhaps not yet, the world is not ready for using encrypted data in use because of the overheads and all involved. And there are attempts at the research level to do that. But right now, the focus is on data at rest and data in motion. So we need to move to a quantum safe ecosystem as a country, as various sectors in the country, like your banking sector, your financial sector, your power grids, your insurance sector, your defense sector, every sector of the economy which is called as critical infrastructure in this country, your telecom sector. These are all the critical infrastructure any country has. And in some ways, they hold very valuable prized assets of data of the various citizens and transaction data. So all this data has to be secured, and we have been using algorithms which are about 30-35 years old, and these algorithms are breakable potentially breakable even today by a quantum computer. There have been some experiments which show that they have been broken in a small way. But having said that, initially the estimate was that we would require millions of qubits to actually break encryption. And in recent times, that has been brought down to as low as 10,000 qubits. So which means that we are not far away. We are already playing with 1,000, 2,000, 3,000 qubits in various different types of hardware, quantum hardware. And so 10,000 qubits is not far away. So there are also algorithms that help in breaking key sizes, like the Shor's algorithm. So that works on a quantum computer to reduce the key size and break it. Now, given all this, the threat scenario and the announcement of the major players in the world, the big tech as they're called, all the big tech players are in the quantum field. They've invested heavily into quantum computing. Not because quantum is going to replace classical computing, but it is because it's going to coexist alongside classical computing and solve problems which were not solvable by classical computers. Having said that, the biggest threat is now data security. And therefore, what is important is that we secure our data. Now, the third word that is used is the ecosystem. What is an ecosystem? An ecosystem consists of the hardware supply chain, the software supply chain, the infrastructure supply chain, the data centers. All these form a complete ecosystem. And all the ecosystem players have to now move towards quantum security and quantum safety. Not just a few algorithms. People sometimes mistake that we just have to plug in some new algorithms, remove some old algorithms, and then we are going to be quantum safe. It is not so. This involves a lot of effort. It involves a lot of time. We have the benefit of time today. A stage may come when organizations, sectors don't have the benefit of time, and they'll be compelled to do it. And that is when quantum computers will be available with significant powers to break encryption. Yes, Dr. Bhattacharya.
Yes, sir. Thank you, sir. But, sir, as we all know that most of the financial organizations are basically using that is elliptical curve cryptography, RSA, that is once we are going to have a sufficiently powerful quantum processor, they are expected to be broken. But there is one hurdle that we are having. That is how the different sectors are cryptographically agile. That is the most of the one of the biggest obstacles that is adopt post-quantum cryptography in the banking, financial services, and insurance sectors is the widespread use of legacy banking systems. And these systems were developed years or even decades ago, and they were using the cryptographic standards which were considered to be secured during that time. Now the encryption standards that they have followed, they have been deeply integrated into the entire application, into the entire system, into the entire infrastructure. So replacing it will be a very much more complex, so it cannot be done overnight. So according to you, sir, so how that adoption to post quantum cryptography should be done, that is when should be done and how it should be done, that is the entire system cannot be replaced at all quite easily, quite rapidly, because that is if we want to change the cryptography, then it is going to affect the payment processing system, encryption, authentication, all those things are going to be having an impact on it. So how the changes are going to be adopted, how, whether it should be a gradual in a phased manner, if it is in a phased manner, whether should be any backward compatibility should exist to the previous earlier systems. So according to you, sir, how it should be like that?
I think you have raised several questions, and I think a lot of what you have said is absolutely true. One is the challenge that we have, challenge for the banking system, the insurance system. In fact, RBI has been very active on this. 2 years ago, they had invited me, typically in the month of July, actually, probably to the day, when they had sensitized all the bank CEOs to the way forward to handle post-quantum cryptography. Having said that, there are lots of challenges. You mentioned lots of challenges. I recently spoke with the managing director of the Insurance Academy, and he was telling me that the longest standing data is in insurance. Forget about banking. What about insurance? Insurance data has to live for our entire lifetimes. So there are various sectors. We have also seen the importance in the defense sector, where it's so critical to secure our communications, to secure our data, because the geopolitical scenario is so volatile. So there are various sectors at risk. There's no doubt about it. So how do we go about it? And as you rightly said, there are so many moving parts that have to be changed. This is not a quick upgrade. There is no easy path to this. And as is said, that a journey of 1,000 miles has to begin with a single step. And that single step, I would say, for all these organizations is primarily to prioritize PQC migration before they get a mandate from the regulator or the government. The NQM has not yet issued a mandate. They have sensitized the regulators to actually encourage organizations to start their migration process. The NQM has set milestones, and those milestones have described how step-by-step process can help organizations move towards PQC. And the question is, there will be a whip. One day, if these organizations don't move fast enough, the regulators will issue the whip and say that you have to do it by a particular date. When that will happen, I can't say, but it may happen sooner than later, especially because of what happened with Mythos a few weeks ago. When Mythos claimed that it can unearth thousands of exploitable vulnerabilities at infrastructure level, suddenly there was panic, not just in India. There was panic in the US first. The Treasury Department there called for a meeting of all the bankers and told them to move to PQC immediately to ward off or at least minimize the threat from Mythos. There was a similar meeting held by the finance minister in India, and the same message was given to banks. So prioritization willy-nilly will happen either by organizations themselves or through the sectoral regulators or through a national mandate. Now the question is, what is the next step? And the next step is given in milestone 1. The milestone 1 actually, which the NQM has published in its roadmap, says that first step is to create awareness in the organization, not just at the leadership level, but at all levels. Second, to create a cryptographic bill of material. That cryptographic bill of material, today it's not a major exercise. You have software that actually runs and gives you the cryptographic bill of material. It will tell you all the places where your cryptographic algorithms have been used, and organizations need to call in either an organization which has the software which can run it for them, or they can do it in-house if they have the technical expertise to do it. But the point is to create a cryptographic bill of material. Having done that, you will come up with thousands of items where cryptography has been used. Now, what do? You can't, again, do everything in one go. So therefore, you have to break this up into 3 levels. Your high-risk data, your moderate-risk data, and your low-risk data. If you break this up into these 3 levels, then it's obvious that the first line of attack for you to secure, or the first line of defense that you have to secure, is your high-risk data. So therefore, the first step that is recommended is to move towards your high-risk data. As you start this process through either a POC or a pilot project, bringing in either a vendor or a consultant, you will realize that there are other pieces also to be handled. There are protocols, there are hardware that need to be upgraded. So you need to then move into your infrastructural upgrade requirements, identify what your infrastructural upgrade requirements are. So, and you also have PQC will definitely, as you rightly said, impose some kind of overhead. Now that overhead, are your systems able to handle? So all this will be proved in a pilot project. And once these pilot projects are successful, then we are talking about going in for a regular full-scale deployment, again starting with high-risk items and then moderate risk and low risk. So when we talk about high-risk items, we're talking about 2 things now. We're talking about critical infrastructure. We are talking about high-risk items. Now, if these 2 are completed by 2029 and by 2027, if we just have the cryptographic bill of material ready and we have a high-risk, moderate risk, low-risk classification, we are good to go. So by 2029, we would have completed a pilot. We would have completed maybe migration of some of the high-risk data at least, so that we are quite secure. And by 2030, we hope to complete migration of all the high-risk and moderate-risk items. So this is the way we have broken it up. This is the way we have issued guidance. It is for the regulators to add guidance of their own, and they will, technology is an evolving science. Things are happening on a daily basis. So if anything new comes in, that also can be incorporated. But the point is, when do we start? We need to start yesterday. And if we have not started yesterday, we need to start today. So that is key, and that's where the prioritization comes in. And that is solely dependent on the leadership of the organization to say that this is risk. In the earlier round of discussions, there was a very, very interesting point that was raised. Where is the ROI? Why should I do all this? Obviously, organizations are driven through profit motives. They will say, what is my profit? But have you seen what is the risk? Have you seen what is the risk to your reputation if your data is exposed? Have you seen what is the risk to your reputation if your constituents or your customer data is exposed? Have you seen what risk you can put the country at? Now that is your ROI, your security. We are able to sleep tonight because we know our encryption is not going to be broken today, but tomorrow is not the case. So therefore, it is important that people look at ROI slightly differently. Avoidance of risk is a bigger ROI than a profit-making ROI. Of course, there are profit opportunities that quantum computing will bring. And naturally, as organizations move into quantum computing, they will be able to leverage those opportunities as well.
Thank you, sir, for your valuable insight about the migration that needs to be done, when it should be done for the BFSI sectors and all. So, and also, sir, the thing is that India is also lacking a dedicated quantum cybersecurity testing environment where the financial institutions can validate the migration strategies. Because as and when suppose the financial organizations will be migrating in a phased manner, so obviously some changes are going to be happening. So before full deployment, So these changes must be thoroughly tested in a control environment, and such control environment can be provided in the form of a cybersecurity testing laboratory can be there, which will be useful to provide such a control environment, which will allow the organization to evaluate the quantum resistant technology and to also validate the interoperability, also to assess the performance, and also identify the vulnerabilities without disrupting the banking operations, the live operations they can have.
No, so very well spoken. Actually, you've raised a very, very important point. One of the tasks of the NQM is to set standards.
Yes,
And
yes.
we have to set standards for PQC. And two, we have to provide the test beds, sandboxes, testing environments where quantum security or quantum safe, as we claim it to be, a lot of vendors will claim that their software, hardware is quantum safe. But how do you know? How do you know? You have to test. So therefore, I think these form a part of our report that we have already been released. It's in the public domain. It involves the setting up of a large number of testing laboratories, both in the private sector as well as in the public sector. These testing laboratories will take anywhere between, my estimate is between 8 to 12 months to set up and procure all the infrastructure that is required for testing. But the testing procedures also have been identified. They have been listed out. The document contains the entire testing procedure. So the testing procedure is in place. Individual testing of hardware, etc. Work is going on doing that. The Department of Telecom has a task force to do that. The PQC testing standards, the standards have not been defined yet by India because we are still don't have cryptography, our own indigenous cryptographic algorithms. So we may have to follow the NIST algorithms, which are approved and tested over a period of time. However, when they are deployed, many vendors may include these algorithms, so they will have to be tested in a wholesome environment, and that the testing facilities will undertake. So we are about 10 to 12 months away from the labs becoming operational, by which time actually we are hopeful that the entire exercise of cryptographic bill of material and POC and pilot, etc., would reach that stage where even a pilot can be tested out. And yes, as you said, we are working with a lot of moving parts. Some of it is entirely in the government sector. Some of it is in the public-private partnership sector. The government itself will set up several sandboxes across the country, and it will have the procedures that have been defined will be used there for testing. But it's a learning process. I think, as you rightly know, that unless we go further down the path, we will not be able to make a perfect testing environment, a perfect testing process. And we think we will have to iterate a little bit once we reach that stage. But it is a very important step, and things are moving in that direction.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much. So my next thing is regarding the regarding strengthening the quantum education and research perspective. So my question will be to Pillai sir. So sir, according to we know that according to you, what are the major challenges that are preventing the universities and the colleges from establishing quantum computing laboratories, interdisciplinary academic programs, and skilled workforce development initiatives? And how can academic research in quantum technologies be better aligned with the needs of industry, government, and national security to accelerate the innovation and real-world impact?
Yeah, thank you for inviting me here, and thank you for these questions. A lot of them actually. So let us look at the present quantum awareness as we see, like how artificial intelligence has been spread across our country. There is a lot of efforts that have been put in for quantum awareness. So we see that people are more aware of quantum computing, but as Professor Ajay had rightly pointed out, we don't have any native research work, lot of research work on post-quantum cryptography. And there are only few institutes or few researchers few individuals who are doing this work, and the scale at which we need to establish and we need to work is very high. So there is a clear gap. And that is what the report that Professor Ajay was also mentioning, which was prepared by the National Quantum Mission, the Data Security Council of India. They have put up this report released in February 2026, couple of months ago. And then there are a lot of things that are listed. And the first year is actually to make make and create the awareness. So as government invests, so we see that again very few takers, as we see, or the way at which the government can proceed is also not very fast. It will take quite some time, as Professor Ajay is pointing out, that there will be a 1 year time, but I think it will take more time for the government mechanism to set up and help handhold the institutions which would like to take up. And also as I would say that though we are very good in mathematics as an Indian subcontinent, our country is very good, but then we see that very few cryptography researchers do exist. So the requirement is too high, and people who are working on quantum key distribution or post-quantum cryptography are very less. Of course, there are quite established and notable researchers, but the scale that is required for our country is definitely not matching. So and then of course, as we look at to really set up the post-quantum cryptography may be easier, because we need to develop the algorithms, we need to develop the mathematics, and we need to develop the agility, we need to develop the cryptanalysis, we need to develop some of these mechanisms for testing. And as we look at, most of us also look at NIST and their series of algorithms to test our own systems. So there is need for sovereign mechanisms or sovereign algorithms, or algorithms which are developed and made in India. The thought process behind it is totally Indian, and also it is competing at a very international level. So, but then of course we are having a very aggressive plan, as we see in comparison with other countries which have taking more time than us. But I'm sure if we really put in the effort, and if the educational institutions, the researchers, they follow the National Quantum Mission timelines, they take things seriously, they devote the time, then we will be able to match up. Otherwise, we are already running behind schedule. And though we are trying to set up many labs by the National Quantum Mission in undergraduate teaching, there are about a few labs that are being set up in this few months, 1-2 months. But then as we look at the research labs on post-quantum cryptography or quantum key distribution, especially on the hardware lines, because most of us, we have a lot of work going on simulations, a lot of work going on testing, but we do not have the required hardware. And as you yourself have pointed out, the migration will take a long time, and many of the agencies are now being made aware of. And hence if the people who are going to be affected are still being made aware, just imagine the research community and the people who need to take on this load of trying to give solutions, trying to build algorithms. It will take more time. And then there are very few institutions who are able to understand and handle, and also whom the government can entrust with these resources, the funding that is required. So many of the people who are here, and you are from different universities and different so this is the time to start. As Professor Ajay pointed out, the time was yesterday, and if we don't start even today, then we will miss the bus. We were just about time for AI, and if we don't take it seriously, we will lose the quantum advantage. So I hope there has been a great awareness that has been spread. We could train about 1,000 faculty in 10 courses continuously, and it included a lot of quantum communication and quantum computing content being covered and given, and demonstrations being done and shown. But it requires a lot of investment, and government wants to invest, but we have very less takers. So it's time that academia take it seriously. And of course, we are also working on. Ministry of Information Technology, Electronics and Information Technology had assured us that we will set up a lab in MNIT Jaipur, and our director had been in touch with the ministry, and we are working on that. And they have also specifically asked us to come up with requirements on quantum key distribution, post-quantum cryptography, and many of the quantum safe ecosystem requirements to set up a hardware lab so that we will train faculty who will go back and train students. So this is the a big opportunity for us. Also, of course, government is looking for institutions to take up such work. So, but then we need to prove ourselves. We need to do some commendable contributions before government can entrust us with these things. So, especially the hardware will be very costly. The resources that will be spent. Okay, we may set up the lab, and if nobody works on it, nobody uses it, or nobody does research with it, then what will happen? There's a huge investment going in, but then the return of investment will be what government will be looking at: development of sovereign algorithms, development of Make in India kind of research, and enhancing the research, and competing at world standard, and that is the challenge before us. So I think the private universities can take a lead by setting apart some profits to set up these quantum labs, so that the faculty who are part of these institutions can do the research there and then slowly take up. Of course, there will be many organizations like CDAC, CDOT, DSEI, many of these institutions which will be government organizations will be helping to handhold them and build them. And of course, National Quantum Mission. Of course, I have also come across multiple startups, very young and bright students who are also looking at developing these aspects. So slowly the ecosystem is coming up, but then I think we need to work together, and that's a big challenge as we see in India. We would like to work as silos, but it is time that and NQM and most of the projects that are being given are given on a consortium basis. So consortium is a couple of institutions, couple of individuals coming together and working. And I think this is one big challenge for all of us. We need to look outside. We should not only look at who will get the project, who will become the PI, who will become the first author, but we should see how our country will benefit. So let us put aside some of these things and let us come together. And if some of the teachers take this up seriously and master some of these contents, and then slowly we can pass it on to the students who can be the resource, who will be able to match the scale of quantum researchers that are required, or quantum product, quantum key distribution product development, or post-quantum cryptographic quantum development. Maybe bring it to what do we say, the algorithms that are required, the quantum resistant algorithms, quantum resilient algorithms that are to be built in. So that requires a big challenge, and that is something that is to be there. So we have very less models or less individuals who are able to achieve something for us, for our country. So I think we need to increase the workforce, so that, and also increase the collaboration, so that in the days to come we will have what is called what is built in India, what is made in India, what is a sovereign work of ours. We need to develop our own testing mechanisms, which will be like what the government has also put in as the tier 3 sovereign grade PQC testing facilities. So that's part of the maybe you can visit the site postquantum.in and look at India's own challenges, and of course look at the report of the task force on post-quantum migration released in February. So I will encourage all of you who are faculty here to take this up and take up the challenges that are mentioned, and maybe the private universities as a vision to part with some of the profits to set up a post-quantum cryptography lab or a quantum key distribution lab, especially the hardware part of it, and then see how the faculty can progress. I think this is something that is there in my heart, and I hope that we'll be able to achieve this in the future.
Yes. Thank you, sir, for your valuable insight. And also that is the main hurdle, is that there has been an insufficient practical and laboratory exposure for the for the students, that is quantum education should combine the theoretical learning along with the practical experimentation, simulation, and hardware interaction. Also, that is, and there has been the curriculum that we are having should be much more industry aligned. So it will be better for the students after completing their graduation or or post graduation. So that will be beneficial for them also. And already we are the quantum awareness is currently very much going on. That is very rapidly going on. We can also enhance it further. Like suppose it is my idea. I don't know whether it is that is if it can be implemented, it will be very much useful. That is still a lot of regional areas are not aware about this concept, the quantum education. So what we can do, that is we are already having 4 thematic hubs. So if we can establish like regional sub-thematic hubs accordingly, so I think the awareness will be enhanced further. So even all the colleges will be having will become aware about the quantum education, the quantum principles, the quantum computing, quantum communication, everything will be coming. So thank you very much, sir. And also, sir, according to you, that is what collaborative models you can suggest the universities and research institute can put forward, can effectively share the laboratories in computational infrastructure. What the collaborative models you can suggest, sir?
Basically, what I would say is most of the universities which have established research should handhold the other agencies. There are training programs which are conducted by IISc and IIT Delhi on many of these programs, and participants should be able to take interest. So what happens is a lot of information is being shared. People listen to it, and we are not taking it seriously. We are not working on it. I think that is where the gap comes. People are willing to share information and handhold, but people are not really able to work on your behalf and do something. So we have to own it up. Whatever information we are getting, we need to work on it. We need to get our hands dirty. We need to work hard. We need to spend sleepless nights to get into technology. Most of us are aware of what do you say, afraid of cryptography, I would say. We are aware of cryptography, but we are afraid of cryptography. So this is time now for our country, as a lot of our critical infrastructure, like our banking system, insurance system, or any of the the critical infrastructure that we have, maybe the data centers, a lot of these things depend on security. And if anybody can break in, they can take control. And if they take control, we are at a great loss. We have a security issue. We have a what do you say, it is a kind of a war kind of a scenario, but we need to protect. And if we have to protect, it is a war footing, I would say. So we need to have these about 150 institutions who are already working with NKM to handhold the younger institutions, private institutions, and students. And they should, the private universities or the lower tier institutions, to take up very seriously, to invest and to share and to work on these challenging problems. We have lot of population, we have lot of intelligent people, we have very good mathematics mind, or what do you say, the skill that I would say. And we need people who will take it up seriously, because the bright minds will leave our country and work for somebody else. They will develop some of these things, and we see that we are missing out on these. But then I hope it is time that we need to really come together as various institutions, state government, central government, NITs, IITs, IIMs, many of them coming together and working on multiple problems. Of course, we are today discussing only one aspect of security, but then in quantum, there are multiple aspects of development, creation of quantum hardware, computing hardware, if you look at, and then creating of quantum processing units. Variety of techniques do exist in quantum hardware. So not only quantum cryptography or quantum safe ecosystem, but there are multiple requirements. So we need multiple groups working together, but then we need to come together. who will get the benefit? India should benefit. So that is what we should look at. If you look at India first, or India as a quantum first nation, then as we look at, it's not only when a project is to be submitted that institutions should come together. Institutions should come together as an interest. So I should find out, if I'm interested in QKD, I should find out who is working in QKD in India. I should be able to read their papers, try to talk to them, work on what they have done, and also try to showcase something that you can do and come up. So once, if something you are able to demonstrate, many people are interested to join you. Many startups are interested to join you. Many good institutions are able to join you and then submit new projects. And NQM is very much willing to fund. Now, they want the right people, and we are finding short of that. So you see, there are so many resources, so much of work to be done, but there are hardly any takers. The right people are not there. Many applications do come in, but the right applications, the right projects, the right ideas are not coming. So that is where the collaboration should come in. We need to take things seriously. It is not that everybody wants to get a project, but nobody wants to work to submit a quality proposal, to publish few papers before we submit a quality proposal, right? So if somebody gives money, okay, let me try. So that's a very easy way out. But then if I can demonstrate something, then I get something. That is what we should be looking at. And we should try to look where the information is, where people are working, who can help me, and then try to tag along with them and then do something, prove to them that you are very keen. And then you will see that there are so many things coming into your own institution. Your institution also will be willing to support once you show that you are able to demonstrate some good work. So I think the things is to change our mind, to not only be viewers of something, but actually get into the ground and play. We are all very good spectators. We are all very good users, consumers of things. Somebody develops, we will use it very well. But I think it is time for India to actually develop things, to build things. So that is the very serious challenge for us. We need to put our efforts, time, and money into it. And I think that is the direction forward. So where to collaborate? Collaborate wherever possible. The first thing is to find out what you want to do, and then do something which you can actually look at who is doing. There are so many in India who are doing. Look at various profiles, look at various papers, you will get them. You tag on to them, try to do something with them, show them that you have done something. They will definitely offer you work, and then offer you opportunities to work along with them. And then you, over a period of time, will be able to help others. I think that is the way forward. Thank you.
Thank you, sir, for your valuable suggestions regarding how collaboration can be established among the universities and the research organizations to effectively share the laboratories, computational infrastructures, and enhance the faculty expertise. So now I have one I have a question to Nikhil, sir. So it's the theme is based on the quantum startups and innovation. So what role can quantum technology startup is going to play in accelerating the development, deployment, and commercialization of practical quantum safe cybersecurity solutions in India? And what are the most significant challenges that are being faced by quantum security startups in secure funding, validating technologies, accessing test beds, and achieving market adoption?
Yeah. Thank you, sir, for giving an opportunity to talk. I hope I'm audible enough.
Yes, sir.
Yeah. All right. So just to start with, like startups, startup will have their own, of course, way of operations in terms of with a limited funding, as well as limited capacity in terms of either human resources or any technology which can be easily adaptable. So to start with, like where startup can basically play a good role is bridging the gap between the researchers, as well as getting out the commercial product to as a production level, TRL9, what we call, right? So that is where the major, the startup should play a role. They, of course, should spend a lot of time in researching the ideas, collaborating with the academia, because academia is one where the major research happens, and collaboration, with the help of collaboration, having an individual strength of the academia as well as industry, which will easily help to come out with the product very faster. As Pillai sir mentioned about the sovereignty as well as the Indian own algorithms, and that's where the major challenge comes, is about the hardware-based funding. Hardware-based funding for deep tech is like little very low, I would say. And that's where probably the government can help us a lot. Looking out, let's say currently we talk about QRNG or as well as QKD devices in terms of a hardware. But currently, let's say, for example, what we are working on is the post-quantum cryptography, but that also we are trying to bring it out onto the hardware platform so that it can become, the semicon chip sets, as well as then, that can become a part of a lot of the secure network itself, on the mobile devices. So these mobile devices will be penetrate into any aerospace, defense, as well as security aspects, where PQC can be running directly onto those devices and secures the connections, or let's say provides some sort of the whole environment, putting them into the basically the blockchain, also later stages to the enhance the tokens, etc. So this is where I would say the PQC as well as PQC on the hardware, which is like a new concept which can be will really utilize well. We already have two missions, which are National Quantum Mission, of course, as well as Semicon mission. So these both are like a very common to this, and government should look after having their own semicon facility which can build up this kind of chipsets, as well as our own algorithm to validate on those hybrid as well as PQC hybrid platform. So this is where I would say that the research collaboration between academia as well as the industry as a startup will be really able to penetrate a way. The same way I have mentioned about the challenges also. The challenges are like not only in terms of funding, but I would say the research where the academia, the master students or the PhD students who are willing to do, building something, that's where, the collaboration between academia and industry will be really helpful. Now, this collaboration in terms of can be an internship or the project based offload or outsource some of the works to the academia to work towards that nation, toward that particular mission. So that's where the bridging the gap between these challenges can be easily addressed. Currently, the other challenges could be is we should have a regional setup also. For example, some remote places, some startup is working where he do not have a major facility except available for the testing aspects or something, or some other. So we should have a regional, the small centers where they can easily go and can access these kind of facilities, either on remote or if it is a hardware, then it has to be a physical. So these regional setups were really helpful, catering to multiple test facilities. Otherwise, everyone has to. I have seen in my past like few challenges into the device product and certification aspects. So every product has to pass through the EMI EMC, and then there were only few labs which were there, and then we had to wait for one turn, like almost 1.5 month to pass the test. And that kind of like, again, if that test fails, reconfiguration, and after then again, like it goes very longer cycles and delays the product to come out. So this is another the pricing area where we can probably work it out and make a regional setups accessible to everyone. Yeah. Yeah, so that's what I wanted to talk about.
Yeah, yes, sir. Yeah. So, sir, one thing that is, according to you, that is how stronger partnerships between the startups and the universities, research institutions, and the industry will help to translate the cutting-edge quantum research into commercially viable cybersecurity products?
Yeah. So, say the researchers and the academia, yeah, with the help of it, like, we can put the product to somewhere like into the prototyping stage or testing phase, like which is, let's say, TRL 4 or 5, and then, the industry comes in and then, make it to the TRL 9, either in terms of, the technology transfer, or as I said, like it can be some sort of outsource, project-based outsource work also. So, yeah.
Okay, okay.
Definitely,
Okay,
a talent pool is always required, a good talent pool. So this will bridge both the things together.
Yes, exactly, exactly, exactly. So, thank you, sir. Thank you, Ajay sir, Pillai sir, and Nikhil sir for sharing your valuable thoughts and ideas. So, before closing the panel, so I have one question before ending the panel. That is, we already aware about the attack called Harvest Now, Decrypt Later threat attack. So, what is the single most critical policy, industry standard, or the academic initiative your sector must implement in the next 18 months, 18 or 20 months to prevent a systematic vulnerability during the transition? So I request each Ajay sir, Pillai sir, and Nikhil sir to address it. That is, given this attack, so how that the most critical policy, the industry standard, the academic format, the initiative must be taken in the next 20 months to prevent to prevent this vulnerability during the transition?
See, as far as the Harvest Now, Decrypt Later attacks are concerned, this is a matter of routinely upgrading your cybersecurity. This has got actually nothing to do with quantum computing. It is just that hackers have found a way, since they can't break it, they can't break encryption now. Let's pile up some data and we will decrypt it when we have access to a significantly powerful quantum computer. So the question is, AI has actually played an important role in this. And Mythos particularly, since they have announced publicly about thousands of vulnerabilities that they can, exploitable vulnerabilities that they can raise. Companies have literally scurried around to actually block the gaps in their security. For a simple example, I'll give you a vendor like Firefox. We often consider Firefox to be a very secure browser. Among the rest of the browsers, we feel Firefox is very safe. Now, Mythos partnered with Firefox and they found 281 vulnerabilities. And now every day Firefox is updating their vulnerabilities. So therefore, this kind of activity has actually spiraled into lots of testing going on in various places. And people are using AI today to actually bring out vulnerabilities. May not be Mythos itself because they may not have access to that. But the point is that this is something that a CISO is doing on a day-by-day basis. New threats will come tomorrow. He'll have to take care of those threats. So it shouldn't be confused with what you are doing with PQC, migration. That is on a separate, that's a longer term issue. Right now, protect the data, what you have in the way you can. For example, instead of you using RSA key, if you probably use an AES 256, you will be relatively safer than an RSA 2048. Now, there are simple solutions like this. Lots of people are already using AES 256, which is relatively safer as of today. So therefore, there are these things that you can do to actually save your data from breaking from future attacks and from future breaking of encryption. And this, I would say, is a regular activity which a CISO or a head of security has to do on an ongoing basis now. The threat environment is extremely volatile.
Yeah, looking at the major requirements as we try to understand the security landscape, the surface, attack surface, is to be understood. So basically, one of the things that we should immediately begin is trying to look at some of the things that Mythos has pointed out. There are many others that also are there, and we have felt that things are very secure now, and there was a kind of a rest period. But now is the time where we need to not only see how the present attackers are thinking, but we need to look at what will be the kind of attacks provided they have the quantum power. So now trying to understand what will be the scale, what will be the requirements, how I can develop. So that's what is post quantum. So a few questions that you had asked is what should be a policy? The policy is to see, understand the attack surface and the vectors that will be there. So that is the one thing. And if you look at what we should prioritize in understanding the hardware development to match the requirements. So the quantum key distribution hardware, the compliant hardware which will be needed to run some of these post-quantum algorithms, and that requirement will be there. The capability that we can look at is students and faculty and researchers coming together and getting aware, like how cybersecurity was taken very seriously a couple of years ago. Now is the time where we look at taking the PQC, QKD, and other aspects seriously is what we need to look at. And the area that whether it should be PQC or QKD, I would say it should be hybrid, and it should be working together, because some things will be solved by PQC, some will be addressed by QKD. Both should be together working. So these are some actions that I would like to suggest. But I think we need few volunteers, few few people who have that passion to take it forward. I think the time is not to rest. Now the time is to jump into action. And I think we need to see how we can try to bring in this change of bringing a big workforce or a big set of volunteers into it, who will be able to be willing to work for India and develop things for India. We can't hire, we can't buy these tools or techniques anymore. We need to develop it within our own country. That is the biggest challenge. Now, how do we do it? Is to bring all these people together, create that ownership that is to be taken, and also we need to be more philanthropic in the sense that we will not look at who will benefit, but how India will benefit. I think that is what I would like to leave it. And this policy is what we need to really push in. Thank you.
Okay, mine will be like very much on second on what Professor Ajay talked about, is about like PQC is the one where we can keep migrating, but at present, like whatever the encryption method which is H256 which is available, we should start using it. And there has to be some sort of the group which should flesh out key stakeholders into the security aspects about the threats. So because many people do not aware about, rather having a daily habit to read out, okay, these are the threats and etc. So there has to be some sort of the group which should flesh out these threats and keep talking about this. This is where the starting point should be.
Yes. Yeah. Thank you, sir. Yes. So as we conclude today's panel discussion on building a quantum safe ecosystem, policy, industry, and academia, I would like to express my sincere gratitude to our distinguished panelists for sharing their valuable insights and experiences, and to all the participants for their thoughtful engagement throughout the session. So today's discussion has highlighted a clear message, that is the transition to a quantum safe future is not solely a technological challenge, it is a collaborative endeavor. So the emergence of quantum computing presents unprecedented opportunities for scientific in advancement, while simultaneously requiring us to rethink the security of our digital infrastructure. So preparing for this transition demands coordinated efforts across governments, industry, academia, and standard organizations. So we have explored the importance of developing quantum resistive cryptographic solutions, creating supportive policy frameworks, fostering industry adoption, investing in research and innovation, and building a skilled workforce capable of addressing the challenge of post-quantum era. None of these objectives can be achieved in isolation. So strong partnerships between policymakers, researchers, technology developers, and end users will be essential for building resilient and secure digital ecosystems. So as researchers and practitioners, we also have a responsibility to translate scientific advances into practical solutions that can be deployed efficiently and equitably. By encouraging interdisciplinary collaboration, promoting open innovation, and investing in education and capacity building, we can accelerate the development of a trusted quantum safe ecosystem that benefits society as a whole. I hope today's exchange of ideas serves as the beginning of new collaborations, research initiatives, and policy dialogues that will shape the future of quantum technologies and cybersecurity. Thank you once again to all our panelists, organizers, and audience for making this discussion both insightful and inspiring. I wish you all a productive conference and look forward to continuing these important conversations in the future soon. Thank you and have a wonderful day.
Thank you, sir. Any questions? Any questions from the participants? Sir, I have one question. This is actually regarding that how can institution with limited funding can participate in such type of quantum technology? As in fact, Shubhankar sir also was talking about the involvement of institutions. So I just want to have a one information about that also, sir.
Yeah, you can contact some of these 4 hubs that are there. Look at the work that is going on. So I would suggest IIT Delhi and IISc Bangalore. You can visit, and they have a series of workshops, training programs being conducted, and few faculty members who are researchers. So please read through their work first, try to do something, and once you are having some awareness and hands-on, after it's like doing a simple MTech dissertation or something on one paper. And then once you do that, and then you will be able to converse with them, and they'll be very happy to get involved. But of course, the scale of involvement will not be as much, because there are few researchers and there may be so many people like us being approaching them. But then if we do something, then there are quite a good number of people, because we have about 120 faculty from across the country who have taught in various quantum courses conducted by MNIT Jaipur. So in similar sense, so at least 120 people are there who can say something or who can help something on something. So and then there will be people definitely to at least point out to you can talk to them, or you can talk to this company, or you can talk to these persons who are working. So that kind of guidance will be there. So the starting point is to first get ourselves acquainted. Nobody is going to spend time with us and teach us or tell us that you do this, do that, and like that. But we need to at least spend 2-3 months in trying to get hands-on with certain things, then take it forward and approach them. Then once as of course Nikhilji was also mentioning, we need a lot of people to work on. So once you approach any company that I have done this, can you help me with something, they will immediately be very happy, because once you know some things, they want such people. Yeah, please come, we will train the remaining things. So the point is, you can't go to them and say, please tell me what to do. Nobody can tell. You can go to them and tell, this is what I did, now can you suggest? There will be so many people who will be willing to do that, and I have definitely experienced that help. So I encourage most of the faculty members to do something. Maybe for me it took 3 months, for you it may take 6 months, but that's not an issue. We need so many people, and I don't think your investment in quantum will go waste. That's what is my suggestion. Thank you.
Thank you, sir. Thank you very much. As we conclude this insightful panel discussion, I would like to extend my heartfelt gratitude to our esteemed moderator, Dr. Anirban Bhattacharya ji, for expertly steering the discussion and ensuring a meaningful exchange of ideas. I also sincerely thank our distinguished panelists for sharing their valuable insights and expertise, especially making us aware about the institution involvement in the Quantum Task Force. Thank you very much, sir. Now with this, we'll be moving to the last section of the summit today. I would like to give the vote of thanks. Yes, Gayatri ma'am, shall I?
Yes, Monica,
Yeah,
your
yes.
voice is just very low, so just
Okay.
try to
Okay.
increase your voice. Yeah.
Okay, fine. Respected Honorable Vice Chancellor, sir, respected Summit Chair, distinguished speakers, moderators, panel members, faculty members, researchers, students, and all esteemed participants, good evening. It's my privilege to propose the vote of thanks at the conclusion of this one-day summit on quantum technology in security. Today's discussion has provided valuable insights into quantum communication, post-quantum cryptography, quantum imaging, cybersecurity, and India's journey towards developing a secure and quantum-ready digital ecosystem. On behalf of JSS University Noida, I express our sincere gratitude to our Honorable Vice Chancellor, sir, for his encouraging inaugural continued guidance and unwavering support for research, innovation, and emerging technologies. I extend my heartfelt thanks to our Summit Chair, Dr. R.S. Jagdish, sir, Dean of Student Welfare, JSS University Noida, for his inspiring words, leadership, and valuable guidance. Throughout the summit, I also acknowledge the dedicated efforts of our summit convener, Dr. Gayatri Shakya, and all faculty members who have helped organize and coordinate the various sessions. Our deepest appreciation goes to all distinguished speakers, Professor Amlan Chakravarti, sir, for enlightening us about the quantum threat to classical cryptography and road towards post-quantum security. Dr. R.P. Singh, sir, for sharing his expertise in quantum imaging, quantum cryptography, and quantum communication. Mr. Sumant Parimal, sir, for skillfully moderating the roundtable discussions. Dr. Mahisha Pandit, sir, Professor Ajay Singh, sir, Dr. Anirban Bhattacharya, sir, and Dr. Anandita Banerjee, madam, for their insightful deliberation and quantum risk and opportunities in BFSI, defense, health care, education, and research. Dr. Kumar Gautam, Mr. Mayank Verma, and Dr. Abhishek Tiwari for their valuable contributions to the fireside chat and industry-focused discussions. Professor Pili Shubhankar, Professor Ajay Singh, and Dr. Anirban Bhattacharya ji for their thoughtful perspectives on building quantum-safe ecosystem through collaboration among policy, industry, and academia. Your expertise, practical experiences, and forward-looking recommendations have greatly enriched this summit and offered us unclear understanding of challenges and strategic priorities involved in preparing India for quantum security era. I convey our sincere gratitude to the Department of Electronics and Communication Engineering, the organizing committee, session coordinators, moderators, rapporteurs, technical support team, administrative staff, and all faculty and student volunteers. Their meticulous planning, teamwork, and behind-the-scenes effort ensured the smooth conduct of the online summit. I also thank all researchers, academicians, industry professionals, students, and participants who joined us today. Your active participation, thoughtfully questions, and enthusiasm made the deliberations engaging and meaningful. Finally, I express my sincere appreciation to everyone who contributed directly or indirectly to the success of this summit. Let us carry forward today's discussion and work collectively towards building a secure, resilient, innovative, and quantum-safe India. Thank you all for your gracious presence and valuable contribution. Thank you very much.
Thank you, all of you. So now we should, shall we end the meeting? All done?
Yes. Thank you, sir. Thank you.
Thank you. Thank you all of you for joining.
Thank you. Thank you all.
Okay, thank you.